Hello and welcome everyone. This is Manish from Skillable India, and today we are going to start our new series on geometric dimensioning and tolerancing. So this series actually we are this is the part of product design and development master program. So this is the continuation. So this actual GD&T we will be covering all the topics of geometric dimensioning and tolerancing from the basics. So at the beginner level, if you are a GET or if you are a student, so I'm going to cover all the topics from the beginning. So you don't have to worry about that it is a very complex topic which is geometric dimensioning and tolerancing. So don't worry about it. We are going to cover it from the beginning. So I'm also letting you know some engineering terminologies because students gets confused that what are datums, what are features, if I'm talking about feature of size. So there are a lot of definitions in that. So you don't have to worry. I am going to cover each and everything from the basics, and then we will go towards the intermediate where we will be learning some usage of or how to implement GD&T into the engineering drawings, and then I will take you from the towards the advanced level. In that you will be particularly understanding that how to apply GD&T and in which cases. So some of the case studies I am going to cover, and in those case studies definitely I will be telling you most of the usage, let's say position or under the location control. So multiple things we will be covering in this particular course. So this is the just an overview of the geometric dimensioning and tolerancing. Now I'm going to start with the fundamentals of geometric dimensioning and tolerancing. In that I'm going to cover I will say the history, the brief history. I will tell that where actually the geometric dimensioning and tolerancing has been originated, has been introduced, what are the conditions when the problem came into existence, and the engineers who have developed GD&T and give this solution to overcome that problem. So I will be letting you know towards that problem also, and in the next part of that of the video of the fundamental of GD&T, I will be letting you know all the topics which we are going to cover in this particular course. So stay with us. Now we are going to start our course on geometric dimensioning and tolerancing. Oxygen is not a choice, it's a necessity. Hi, this is Manish Sharma, and in today's session we are going to start with the fundamental of GD&T. So what is geometric dimensioning and tolerancing? Why we are going to use this GD&T, and what's the need of using GD&T? So I'm going to cover this course of geometric dimensioning and tolerancing from the basics, all the topics which students don't know about. So I am not considering that you are a working professional and you know the basics. I am covering this course from the basics, that I will be telling you that what are datums, what are feature of sizes, what are limit of size, limit of tolerance. So all those things I am going to discuss with you in this course of geometric dimensioning and tolerancing. As I have already told you that this is the continuation of product design and development. So this is the continuation part. So in this particular course you will be connecting a lot of things which we have already discussed. So I have already told you that manufacturing or engineering drawings, that manufacturing drawings are very important document. Actually they communicate the part requirement precisely. That precision, in the starting I have told precision is not a choice, it's a necessity. Whenever we are going to manufacture any part or any component which we are going to manufacture, so to control all the sizes and the shape, form, orientation, and all the related things into that part, we use geometric dimensioning and tolerancing. If I write it down over here, one of the important note, so to define the size, shape, or relationship between the relationship between the surfaces, or we can say surfaces, and total allowable variation, and total
allowable variation in a part, we use geometric dimensioning and tolerancing. So this is very important thing which we need to take into account, that why we are using the geometric dimensioning and tolerancing. So, in this particular session, first of all, we will understand that what are the standards we are going to discuss in this particular course. So, we are going to discuss about the ASME standards. Although there are lot of standards around using around the world, but why we are understanding about more, why we are focusing more about these standards, I will let you know that what specific topics we are going to discuss in this particular session. So first I'm going to erase this. So what are the different standards used are all around the world? First of all, there are ASME standard. So what standard we are going to understand is of ASME by 14.5 2018. So ASME stand for American Society of Mechanical Engineers. So this is the organization, or this is the standard organization which has provided the standard, which is Y 14.5. So Y 14.5 is the standard, and 2018 is the year updated. The latest update which comes into the year is 2018. So the latest update we got in 2018. Although ASME has previous standard, ASME by 14.5 2009 standard. I will tell you that what are the differences between the 2009 standard and 2018 standard. That there are two geometric characteristics which are symmetry and concentricity, which are being removed in 2018, but they are till 2018, as per the 2009 standard, we are using those geometric characteristics. So I will also let you know that why in the recent standard those characteristics are being removed. So one by one, all those things we are going to discuss. And other than the ASME standards, there are ISO standards, there are JIS standard, which are the Japanese standard, there are BIS standard. So there are a lot of other standards are also there, but as per the organizations which are using right now, so 90% of the companies which I have seen are using the ASME standard. Why they are using? Because their standard is more practical in nature, and what ISO standards are more theoretical one. So more from the practical aspect, if we see, so ASME has given some practical scenarios to understand these standards better. So that's why we are going to learn about ASME standards. So particularly, first of all, I will give you an overview, and I will tell you some of the brief history of geometric dimensioning and tolerancing. That why there is a need of using the GD&T. So the first question arises in front of us, that the when the concept is being generated, the concept of GD&T or the geometric dimensioning and tolerancing was introduced by Stanley Parker. So Stanley Parker is from the Scotland, and this concept he has made in the late 1930s, after the Second World War. So what problems he has faced into the Second World War? He was actually an engineer in the munition department under Britain. So there are a lot of armor manufacturing at the time of World War. So at that manufacturing time, there are a lot of assemblies are going to be done, but as the time of inspection, the lot of parts are being rejected. So he was working in a munition under Britain. Torpedoes and other ammunition parts were rejected when inspected using a traditional tolerance system. So whenever we are using the traditional tolerance system, a lot of parts at that time are going to be rejected under the inspection. So in 1938 he developed the concept of position. So only he has started with the location control, which comes under the position or the true positional tolerance. During World War II, companies had to outsource part because of the large quantities and tight schedule. So that's why they are manufacturing at a lot, I will say, lakhs of parts they are manufacturing, and they are assembling with one another. So the problem is many parts are getting rejected because of the tighter tolerances, because of the coordinate tolerance system. So why the coordinate tolerance system have less tolerance zone, less than the geometric dimensioning and tolerancing? So all those discussions we will be doing further. So that's the problem. This is the very big problem, that part are not getting assembled with each other, and if they are not assembled, their functionality will affect. So the function which is intended, the part which is intended to function, it is not performing the required function. So that's why the part, either the part is going to be rework, so the rework has been done onto the same part, or it is going to be scrap. So to reduce the overall rejection, or to reduce the scrap rate, or to reduce the rework, the concept of geometric dimensioning and tolerancing comes into action. So this is the brief history, and now we are going to understand that what is GD&T is all about. So geometric dimensioning and tolerancing is a symbolic language. So first of all, we need to understand from the basic, it's just a symbolic language in which we are going to use one feature control frame. In that feature control frame, there are multiple compartments, or in those compartments we are going to write it down. I will be telling each and every compartment that how we fill those compartments. So first of all, geometric dimensioning and tolerancing is symbolic language which communicates the part, intent and function through design, manufacturing and inspection. So actually that engineering drawing which we are incorporating the GD&T into it, so the it communicates the part intent through design, through manufacturing and inspection. So all the stages will be in a same loop with the help of that engineering drawing, which consists of GD&T standards. It also gives more precise depiction of the part feature. Why it is going to give the more precise depiction? Because we are going to get more control over it. It controls form, orientation, location, profile and runout. So the 5 categories in the GD&T, there are 5 categories. Form, which is saying about the shape. Then there is orientation, we are talking about angles. Location, profile and runout. There are 5 categories. So one by one I will let you know that how these categories are being subdivided and how many characteristics are there. It also focuses on feature to feature relationship. So GD&T focuses on feature to feature relationship. Since GD&T is expressed using line drawings, symbols and Arabic numerals in feature control frame, people all over the world can read, write and understand regardless of their native language. So this GD&T is not dependent on one country or one region. These standards are applicable for all around the world. So these are very, very helpful, and this is what is GD&T. These are the definition for the what is GD&T. Now with one example I will let you know that how we are going to understand the concept of GD&T and why there is a need. So in this example you can see that I'm going to give an overview with this. Just to understand the GD&T concept, let us take a small example. Right now you can see an image over here. This is a rectangle or a rectangular block. So if somebody wants to manufacture the part, so we have to provide some dimensions to this part. So but with this manufacturing is not possible. Just by showing this rectangle, the manufacturing is not possible. So to produce this part we have to give some dimensions to this part. So in this you can see that I have given some sizes or the dimensions into this. So what we do is we have added the dimension and dimensional tolerances. So here you can see 100 plus minus 0.1 and 50 plus minus 0.1. So dimension and dimensional tolerances we have added. When only limit of size is given, So when only limit of size is given, then we may end up producing a part like this. You can see only limit of sizes are given. Limit of size. So when only limit of size is given, so with the help of that we can produce a part like this. This is one possibility, that the part can be produced like this. In this you can see, if we will see that the upper limit is here is 100.1 and the lower limit is 99.9. So upper limit minus lower limit 0.2 mm is the dimensional tolerance. So this is the possibility. This is the first possibility. The second possibility is where the dimension are limit, but the surface is not accurate. In this you can see the dimensions are within the limit. All the dimensions are within the limit, but the surface is not accurate. So here the problem is surface is not accurate. Surface is not accurate. So there will be, in this you can see there is a form error. So there is a form error. So this is one possibility. The other possibility is the part can be another possibility is we may end up creating a part like this also. So in this case you can see that all actual local size. So actual local size, if I'm measuring from here to here or I'm measuring from here to here, so actual local size is within the limit of size. So I'm writing now note over here. In this example, actual local size actual local size is within the limit of size. Within the limit of size. So wherever we measure, we are measuring from here to here or here to here. So actual local size is within the limit of size, but there is a band in the part. You can see there is a band into the part. So this is one of the major problem, that although this is under the actual local size is within the limit of size, but there is a band error. If this part is going to be assembled with the mating part, then what type of problem we are going to face? So when we produce a part like this and try to assemble with the mating part through the part within the limit of size, it will not enter properly. So the problem will occur, it will not enter properly. It will not enter properly in the mating part. So thus in all such cases, what we do have, we have to use the geometric dimensioning and tolerancing to control the shape also. Not only we are controlling with the help of GD&T, with the help of GD&T, we are controlling controlling the size and the shape of the part. So here you can see shape is also very important, because we have seen in this example, because all actual local size are accurate, but there is a bend into the part. So to control this bend we have to use the GD&T. Now it conveys both the nominal dimension. In this example, now we will understand that how many controls are there, how many categories are there. So all those categories we will understand this one by one. So first category you can see over here is for individual features. So first of all, we will the geometric characteristic symbols. So there are these are the geometric symbols which are in 2009 standard. You can see these are into the 2009 standard. You can see 2009 over here, and this is as per the 2018 standard. So first of all, we will see that there are three categories for individual feature, for individual feature, for related feature. So as we are moving towards the geometric characteristic symbols, so as per the ASME Y 14.5 2009 standard, there are almost 14 geometric characteristic symbols. So there are total 14 geometric characteristic symbol as per ASME Y 14.5 2009 standard. But in the latest update, as I have told you, in the 2018 standard, two of the geometric characteristic symbols are being removed, which are as per the 2018 standard, two standards are being removed, which are concentricity and symmetry. I will let you know that why they have removed in the further sessions, so do not confuse in this. Just for your knowledge, I'm telling you this thing, that the latest standard which has been released of ASME by 14.5 is in 2018. I have already told you in GD&T we have totally 14 symbols, and they are broadly classified in three categories. So the first category is individual feature. The first category which is divided is individual feature. Individual are features are the features which does not depends on the neighboring feature. So what are individual features? Which does not depend on the neighboring features. So those are called individual feature. Under this individual feature, you can see there is one type of tolerances is which is under we have the form control. So under the individual feature we have form control. In this form control we have straightness, flatness, circularity and cylindricity. So these four geometric characteristic we have under form control in the type of tolerances. The second classification in this we have is for the individual feature or the related feature. So this is for both individual as well as for related feature. Under individual and related feature, only one type of tolerance comes, which is profile. So in profile we have profile of a line and profile of a surface. So this feature are what is individual or related feature? So these features are the features which require relationship or dependencies with the neighboring part sometimes. So they are dependent or sometimes they are not dependent. So these features are in both the cases we use this type of tolerances, or we use this category. The third category what we have is here is, you can see the third category what we have is related feature. So what is this related feature? These are the features which are always dependent on the neighboring feature. Related feature is the feature which are always dependent on the neighboring feature. Under related feature we have three subcategories. First subcategory is orientation. Whenever the relationship between the feature or angle, whenever the relationship between the feature or angle, we called it a orientation. So whenever we are talking about angles, okay, relation between the feature or angle, so we are considering that we called it as orientation control. Now under which we have angularity, we have perpendicularity and we have parallelism. So under orientation we have three characteristics. First is angularity, perpendicularity and third is parallelism. The next subcategory is called the location control. So the next subcategory under the related feature is the location control, under which we have, you can see we have three over here: position, concentricity and symmetry. So under location control we have three geometric characteristics: position, concentricity and symmetry as per the ASME Y 14.5 2009 standard. Now the third subcategory which we have over here is of runout. So the next subcategory is runout. Under runout we have circular runout and total runout. So all put together we have 14 geometric characteristic symbol as per ASME Y14.5 2009 standard. Under orientation, you can see angularity is an alternate practice of perpendicularity and parallelism. So we use angularity for perpendicularity and parallelism. For both of these we use angularity only. And when it comes to ASME Y14.5 2018 standard, the concentricity and symmetry are being removed, so we have only position left, position control under the location. So we have left with only position under location control. I will let you know one by one when we will be discussing each and every geometric characteristics, that how we can use this geometric characteristics. At that time, I will let you know that why symmetry and concentricity are being removed, and while removing, why we are using position in terms why we are using the position under location control in terms of the symmetry and concentricity. To get the full advantage of these geometric characteristic symbol, we have something called modifiers also. So what are these modifiers? I will be letting you know one by one that how we use these modifiers. So when we use these modifiers along with the geometric characteristic symbols, we will get more advantage of the tolerances. So we get more and more advantage of tolerances. That's why we use these modifier with the geometric characteristics symbol. So here you can see over here to follow. You can see in this particular image that we have their maximum material condition, least material condition, and these are the symbols. So do not we are going to discuss each and every symbol in the coming session, so do not confuse in that. This is translational, projected tolerance zone, free state. So for why we use free state, so I will be telling you the concept of free state, that in which conditions we use for free state. Then there is a tangent plane, unequally disposed profile, independency, and all these modifiers which we use into our manufacturing drawings. So these are the very important one which we are discussing over here. Now in the next part, now we are going to discuss the course topics which we are going to discuss in this whole course. So these are some of the these are all the topics which I am writing down over here, that what we are going to discuss in the coming sessions. So we are starting with the introduction to GD&T. Then we are going to cover the 16 fundamental rules of engineering drawing, which is a very important concept for the design engineers. Not only the design engineers, because the 70% to 80% control is in the hand of design team. So that's why you as a design engineer, if you want to become a design engineer, or you want to make your career as a design engineer, then you have to remember that these fundamental rules are very important into your engineering drawings. While making your engineering drawings, you have to use these fundamental rules, and it will become very easy for you to use. So whenever I say ASME by 14.5 2018 standard or 2009 standard, if the drawing is applicable as per those standards, these fundamental rules, these 16 fundamental rules will automatically apply. Then there is a dimensional and tolerances, coordinate tolerance system. What are feature of size, actual mating envelope, unrelated actual mating envelope, related actual mating envelope, actual minimum material envelope, unrelated and related actual minimum material envelope. What are material modifiers? What is RFS, regardless of feature of size, versus maximum material condition versus least material condition? What is rule 1 and rule 2? Datum, planes, constraint, relationship. What are bonus tolerances? What is tolerance diagram? How we can calculate with the help of tolerance diagram a bonus tolerance? What is a virtual condition? What is a resultant condition? What is feature control frame? What is controlled radius? So these are the topics which we are going to discuss in this course. Then there are other topics also, like straightness. These are the geometric characteristic symbols. characteristics which we will be discussing one by one. We are also going to discuss what is datum, what are datum reference frame, what is 3 to 1 principle, and how we can apply 3 to 1 principle with the help of degree of freedom. So we will understand the whole concept of degree of freedom also in this. We are also going to understand about floating and fixed fastener and many more other topics. So these are some of the topics which we are going to discuss in the coming sessions of this course, and each and every session is connected with other session, so do not skip any session. And the assignments and the quizzes what I am going to give in this course, so although complete one by one, if you have seen this lecture, so you have to complete the assignment and the quiz, because if you will complete, you will have more and more confidence of learning, because GD&T's concepts are very very important. And the document or the PDF file what I am going to share with you, go through all the points, so learn all the points, because those are the points which are very very necessary to know about. So that's why, so this is all for this session. This is the introductory session, so I have tried to cover all the basic things of this. From the next session, I will be more covering the related topic to the geometric dimensioning and tolerancing. Thank you everyone.
Hello everyone, this is Manish from Skillable India. We are going to start the second session of this course, which is the geometric dimensioning and tolerancing. In today's session, we are going to discuss about the 16 fundamental rules of engineering drawings. So these rules are very important for any engineer who is completed the 3D model and going to make an engineering drawing, through which an machinist or a person who is manufacturing that part will be able to manufacture a part precisely. So that's why these 16 fundamental rules are very necessary. First of all, in geometric dimensioning and tolerancing, GD&T relies on these fundamental rules. So GD&T basically holds these rules, and I have already told you that ASME Y14.5 2018 standard, whenever these standards are applied, these rules are automatically invoked. So these rules are automatically applied on that engineering drawing if it is as per the ASME by 14.5 2018 standards. So it is written over here that these rules automatically applies where ASME by 14.5 2018 standards are applicable. And these fundamental 16 fundamental rules are connected with a lot of detailings into the engineering drawing. One by one, all the 16 fundamental rules we are going to discuss. So we are going to start with the first fundamental rule, which is denoted by A. What does this rule say? Each dimension. So each dimension shall have tolerance. So any dimension which is being given in the engineering drawing always shall have the tolerance, except some of the exceptions are there. So except dimensions identified as reference dimension, maximum size dimension, minimum size dimension, or stock. So stock is also known as the commercial stock size. So I will be letting you know that what is this commercial stock size means. Tolerance may be applied directly to the dimension. So we can apply directly tolerance to the dimension onto the engineering drawing, or through a general note. So in engineering drawing, you can write it down through a general note or through the title block. So here you can see in this example, you can see that this is a title block. So this is called the title block into engineering drawing. And these are the some tolerances which are applicable on all the dimensions of the drawing. So these you can see plus minus 0.5 this dimension and plus minus 5 degree. So these both tolerances are applied
on whole engineering drawing. So that's why this is very, very important. So what the first rule says, that each dimension shall have tolerance except the reference dimension, maximum size dimension and minimum size dimension. Now the question arises that what is standard stock size? So basically the stock size is item, those geometries are already controlled by established industrial or government standards. So you can see over here that items, what are the items in this? You can see that angles are there, tubes are there, or maybe rectangular tubes are there, or square tubes are there, or circular tubes are there, I sections, C section. So all these are the standard stock size. And in India, there is one organization which is called the BIS. So in India, there is a BIS which controls all the standards behind these shapes. So in case of bars, sheets, so there are many gauges available. Let's say if I am talking about 16 gauge sheet. So 16 gauge means 1.6 mm. If I convert this gauge into an mm, so 16 gauge means 1.6 mm. If I'm talking about 18 gauge sheet, it means about 1.2 mm sheet thickness. So this is basically the thickness of the sheet. So these are some standards which are governed by the BIS of a government, which is a government organization in India. So these are some standards which are applied all over India. So these are some strength. That's why we don't have to provide the tolerances in such shapes. With the help of example, I will let you know. So in this example, you can see this is a channel section. So all the dimensions, whether it's a D, this is dimension B, or it's a B dimension or any other dimension. Let's say this is a D thickness. So this is another D thickness, R2, radius 2, radius 1. So what's the distance between this? So all these, here you can see MC75. If I am talking about MC75 channel section, so this is medium weight channel. So this is medium weight channel, which is a MC75. So whenever we are talking about MC75, so these are the weight. So this is the mass of the MC75. This is the sectional area. This is the D, which is the size, 75 mm. So in this case, 75 mm is the size of this B. 40 mm is the B. So this size is called B is equal to 45 mm. So these are all the standard. So MC75 have all the standard, in the table. So these are applicable all around India. So you can see all the things inside this table. So this is called the standard stock size or the commercial stock size. So generally we use this word commercial stock size rather than stock size. So this is the example for that. So what does this second fundamental rule says? That dimensions and tolerancing shall be completed. So whenever on an engineering drawing, if you are making an engineering drawing, so first thing you must see that whatever dimensions you have provided, they are enough to manufacture that part. Dimensions and tolerances. So both the things you have provided onto the engineering drawing shall be completed. So there is full definition of each part feature. So there is not any ambiguity or any confusions or any assumptions for the machinist or a person who is reading that drawing. So the drawing should always be completed in terms of dimensions and tolerances. if there is any ambiguity or assumptions, so what is not allowed in as per the ASME by 14.5 2018 standard in the 60 fundamental rules, that a person cannot scale a drawing or make an assumptions on the basis of other dimensions. So sometimes on a soft floor, what happens that if our design engineer has missed some dimensions onto the engineering drawing, so the person who is there onto the machine who is manufacturing the part, he makes the use of engineering scale and scale the dimensions into the engineering drawing. So it is strictly prohibited that you should not use this method. So always, sometimes in the title block, in this case, you can see in this title block, it is written over here that do not scale the drawing. So these type of points are written onto the into the title block, that we do not we don't have permission to scale the drawing. So the assumptions are not required. So whenever these conditions are there, we do not have to scale the drawing or make an assumptions. So this is the second fundamental rule. So what does the next rule says? That each necessary dimension of an end product shall be shown. The end dimensions of any product should be shown onto the engineering drawing. So in this case, let's say this is the part drawing. So in this case, 60 mm and 30 mm are the end product dimensions. So the whole outer dimensions of the any drawing or any part should be available onto the engineering drawing. So this is the necessary. Secondly, this rule says that use of reference dimensions should be minimized. In this case, you can see that the dimension which is written in parenthesis, which is 20 mm here. So we have to try to minimize the use of reference dimension. In further sessions, I will tell you that why we use these reference dimension and why this rule is saying that we have to minimize the use of reference dimensions. So we have to try that the reference dimension cannot be used in the established part requirement. So we have to try to minimize or do not have to use the reference dimension in the engineering drawing. So what does this next rule, D rule, says? That dimensions shall be selected and arranged to suit the function and mating relationship. Mating relationship of a part shall not be subject to more than one interpretation. So what does this mean? That whenever we are putting dimensions onto the part drawing into the engineering drawing what we are making, so there should not be more than one interpretation for the same drawing. So in this case, in this example, you can see that we have selected and arranged dimension in such a way that the part feature, you can see that the part feature and the function and their relationship in this particular case with each other should have correct interpretation. So in this case, you can see that the line, which is I will say the extension line in this case, as used as the boundary line is used as an extension line, which is not correct. So we have to give dimension in such a way that that extension lines should be different from the boundary line. So whatever the part lines should be there in the engineering drawing, we don't have to use as an extension line, because it will make a confusion for the machinist. So that's why we don't have to make such practices which are not worthwhile and which makes a lot of confusion. So in this example, you can see that we are using a part boundary or a surface. These are the surfaces as an extension line. So there can be misinterpretation, which is not the right thing. So to eliminate this confusion, what we have to do is, actually this is a simple drawing. So that's why we are able to read and understand this drawing. But when there is a complicated drawing and we are using a boundary or a surface as an extension line, it may cause misinterpretations. So to reduce this difficulty, to reduce this problem, we have to make a separate extension line out of the boundary of the part. So always remember this, that that we have to give dimensions or on the engineering drawing outside the part boundary using the extension lines. So maybe like this, we have to give the dimensions. So these are the extension lines which should be written away from the part. So this practice is not allowed into this with the help of this rule. So correct way of showing the dimension is like this. So this is the rule number D. Now the next rule says, so what does this next rule says, that the drawing should be define the part without specifying the manufacturing method. So whenever we are creating an engineering drawing, let's say we are creating a part which has a hole. So we have to define the diameter of the hole, but we do not have to define the manufacturing process onto the engineering drawing. So in this example, you can see that only the diameter of the hole is given without indicating whether it is to be drilled. Let's say this is written over like this, drilling process or wire cut to be done. So this is not permitted. So these type of manufacturing processes don't have to be written onto the engineering drawings. So whether we have to drill a hole or whether we have to create it with the help of EDM or with the help of wire cut processes, or whether we have to punch a hole. So we don't have to write onto the engineering drawing. So this fundamental rule basically specifies that we don't have to write the manufacturing methods onto the engineering drawing. However, in some cases, it is written that, however, where manufacturing, processing, or the quality assurance or any environmental information, if it is essential, then to the definition of engineering requirement, it shall be specified on the drawing. So sometimes the condition comes that sometimes we have to write it down some points related to the environmental assurance or the quality assurance. Some environmental informations we have to write it down. Some processings are there. So those important notes, we can write it down onto the engineering document. So it is saying that it shall be specified on the drawing or in the documents. In this case only, a limited length of the area of a surface is to receive additional treatment. Let's say in this example, only this much area requires the induction hardening. So this additional treatment or consideration within the limit is specified on the drawing. So these type of specific processes, we have to show onto the specific processes. We have to show onto the engineering drawing. Okay. So these things we can specify. In this case, you can see that only this area requires the short pin. So we have to specify this onto the engineering drawing, or we have to require the masking on the plate. So we have to write it down onto the engineering drawing. Okay. So these are the specific special cases for the specific additional treatment of the part. So these we can specify onto the engineering drawing. So this is what this rule says. Other than this, these processes like drilling, rimming, wire cut, punching. So these type of processes we don't have to write onto the engineering drawing basically. Now what does this next rule says? So in this fundamental rule, which is F, says that non-mandatory processing information. So what is this non-mandatory processing information? Shall be identified such as non-mandatory manufacturing data or a reference information like finish allowance or a shrink allowance, etc. So what does this actual fundamental rule says? That if we specify the non-mandatory data, which is the non-mandatory manufacturing data onto the engineering drawing, so we have to specify on that. So why we have to specify? In some cases, let's say if we are manufacturing the part and we have given some dimension, let's say we have given some shrink allowance, or let's say a finish allowance. Let's say some coating, hardcore coating has to be done onto the surface of that part. So we have to manufacture the data by reducing the thickness of the finish, let's say 20 micron or 50 micron. So we have to reduce into that manufacturing part. So we need to specify this non-mandatory processing information shall be identified, such as non-mandatory as in the form of non-mandatory manufacturing data. So processing dimension that provide finish for finish allowance or shrink allowance. So provide the final dimensions are given on the drawing. So we need to give the final dimensions onto the drawing. So the manufacturing part plus the finish. So this becomes the final dimension. So whatever the final dimension, we need to specify onto the engineering drawings. So the next fundamental rule says that dimensions should be arranged for optimum readability. So whenever we are placing the dimensions onto the engineering drawing, let's say we are giving dimension to the part in the engineering drawing, so it should be arranged in an optimum manner that it is easy for the person to read it. So optimum readability should be there. We have to arrange in such a way that it should be easily readability. Dimensions should be shown in true profile views and refer to visible outlines. So in this particular fundamental rule says that whenever we are giving dimensions to the part, so we have to align in such a manner that in this example you can see that dimension lines should be aligned and grouped for uniform appearance. So in this you can see that all the dimensions are aligned in such a way that they are grouped and uniform appearance is looking. So these are uniformly arranged. So all the extension lines are properly arranged. If there is need, so we have used this extension line for this dimension and these dimensions also. So it is aligned properly. Now, if there is a requirement that we need to stagger our dimensions, or alignment should be in the form of staggering, so we can also stagger it in such a way. Let's say this is the part, this is the second example. So in this example, several parallel dimension lines, the numeral should be staggered for easier reading. So we have to stagger, if we are staggering also into our engineering drawing, so we don't have to stagger in such a way that the extension lines or the arrow we are denoting the dimension, it is going somewhere else. So it is not the person who is reading the dimensions. It is going to be misinterpreted. So this is very, very important that the dimensions which we are providing onto the engineering drawing should be aligned properly and it should have the optimum readability. So in this fundamental rule, it says that wire, cable, sheet, rods and other material manufactured to gauge or code numbers shall be specified by linear dimensions indicating the diameter or thickness. So we know that there are many things like tubes, like rods, like wire, sheets. So these are comes in with the gauge number. Let's say if I'm talking about I've already given you this example that if I'm talking about 18 gauge sheet, so means this gauge I'm in the reference of 1.2 mm thickness. I am denoting the thickness which is 1.2 mm. So this is how we provide the thickness, and these standards are throughout. We are using the wire or we are giving the sheet. So what does this fundamental rule says? That we can specify the gauge onto the engineering drawing, but first of all we have to give the linear dimension for it. So in this case you can see in this example we have to specify the thickness as a linear dimension. So as a linear dimension we have to provide the thickness, then only we can use the gauge. Let's say if I want to specify the gauge also, so I can specify the 20 gauge over here. So as this rule says that we have to specify the linear dimensions onto the engineering drawing, then only in bracket or we can show the gauge or the code number. So the gauge or code number may be shown in parenthesis. So whatever parenthesis we can use after the linear dimension following the dimension. So this rule basically says that after giving the linear dimension, we can write it down the gauge or the code number into the parenthesis. So what does this rule says? In this rule, a 90-degree angle applies where the central lines or the lines depicting feature are shown at the right angle. So in this particular example, if we take as an example, so what is actual rule saying? That whenever the part is showing the axis or the center line of that axis, or the axis is shown of the shaft. In this case, this is the axis. This is the axis shown in the shaft. So whenever the axis or the center line is given, so there is no need to mention the angle which is at 90 degree. So in this you can see that this is the surface. This is the surface. This is the surface of the shaft. So the surface of the shaft is perpendicular to the axis. So in this case, this 90 degree we don't have to show onto the engineering drawing. So it is already clear that whenever the axis is there which is perpendicular to the surface, so it means it is already at 90 degree, and we don't need to show the right angle or the 90 degree angle onto the engineering drawing. So here it is similarly saying that no angular dimensions is specified on a 2D drawing, orthographic drawing. So there is no need to specify this whenever this case is there. In this second example, you can see that in this part, this hole, this is a hole which is having a center line. So this hole's axis and the bottom surface is perpendicular to each other. So in this case, this 90 degree which is here, so in this case there is no need to show onto the orthographic view. So it is clearly shown that whenever there is an axis which is perpendicular to the surface, so we don't have to specify the 90 degree angle onto the engineering drawing. Now, what does this next rule says? A 90 degree angle applies where the center lines of the feature in a pattern or lines shown at right angle on a 2D orthographic drawing are located and defined with basic dimension is specified. So in this case, you can see this this hole is having a center line. So this is the center line over here, and this is the center line over here. So if I particularly make the center line, okay, so this is the center hole in this, this is the hole. So we don't have to show this 90 degree angle onto the engineering drawing. So there is no need to show this 90 degree angle as well. So it is clearly shown that these both axes are perpendicular in nature, are perpendicular to each other. So in this case also, we don't have to show the 90 degree angle onto the engineering drawing. Now, what does this next rule says? So in this rule, what this rule says, the zero basic dimension applies where axes, center planes and surfaces are shown coincident on a drawing, and geometric tolerances establishes the relationship among the feature and feature of size. So in this example, you can see in this example that the point where the two surfaces are meeting, so this surfaces have the 0, 0 baseline. So from here, if we are taking, let's say, if we are taking multiple positions of the geometric tolerances from here for this axis, so these are multiple center lines or axis from the surface. So this from this 0 point, it is creating multiple, establishing a relationship among the feature. In this case, feature is a surface. So the distance between the center of the hole. So in this case, these are multiple holes. So these are hole center points. So the distance between from the 0, 0 baseline. So in this, you can see that we are getting from one feature or feature of size, we are getting multiple dimensions we can take. So we can apply this 0 basic dimensions whenever we have the center plane, axis or surface, which are coincident in a drawing. So this is the K rule. So what does this next rule says? This is very important rule in the fundamental 16 fundamental rules. So the rule says unless otherwise specified, all dimensions and tolerances are applicable at 20 degrees Celsius. So whatever dimensions we are giving into the engineering drawing, those dimensions and tolerances are only applicable where the room temperature is at 20 degrees Celsius or 68 degree Fahrenheit. So why this is important? 20 degrees Celsius we need to maintain. If the temperature is different as per the manufacturing requirement, so whatever dimensions and tolerances we have given into the drawing and where the part is manufacturing, if the temperature is different other than the 20 degrees centigrade, then especially we have to provide some compensation to be made in the measurement made to other temperatures. If we are measuring the same component at other temperature other than the 20 degrees centigrade, then we have to give some compensation. So why all these things are are happening, and why there is a requirement for the standard rooms in the companies. So if a company want to take ISO guidelines, then they have to make a standard rooms into their manufacturing or the measurement areas. Every company is having the standard rooms, either whether they are using that standard room or not, but they are having because they have to fulfill the requirement of the ISO. So that's why this is the requirement. One of the, I will say in this, one of the basic principles of metrology is that the part dimension changes with temperature. Why this temperature is so important? First of all, I will give you a brief discussion about this. That temperature, according to the temperature, the basic principle of metrology is the part dimension changes with temperature because of thermal expansion or contraction. So whether the material can expand or the contracted. So this is the basic principle of metrology, that if the temperature changes, the expansion or the contraction occurs into the material as per there the coefficient of thermal expansion, CTE value changes. So all these material expansion and contraction are happening. Now the question comes, why temperature is so important? Let's say in this case, I will give you one example. Suppose there are two mating parts. Suppose there are two mating parts which are going to be assembled with one another. One is of steel and other is of brass. What will actually happen? Because as we know, both the values of either it's of a steel or it is of brass. If both the parts are being manufactured at 0 degrees Celsius, let's say the condition is both parts are manufactured at 0 degrees Celsius, steel part and the brass part. Now let's say we are manufacturing this part and we need to assemble one part with the other, and material is different, one is of steel and the other is brass. So when we go on to soft load, temperature is at 0 degrees Celsius, then time we have manufactured the part. We know that the CTE value of steel is this 12 into 10. This is the CTE value of steel, and brass is about this. So you know that brass and Dixie both have different CTE values. Brass is having the more CTE value. Brass is having more CTE value. CTE is basically a CTE is coefficient of thermal expansion. Do not get confused. Coefficient of thermal expansion. So when we assemble both the part at room temperature, so brass has a more CTE value. So what will happen with the brass is it will get expand because it is having more CTE value. It will expand and contract more with the change in temperature. So as it is having more CTE value, it will get expand or contracted more when the temperature changes. We can face problem at the time of assembly. At the time of assembly, it can be happen that the part did not get assembled with one another. So this is very important that we need to maintain this temperature that it do not get contracted or expand in such a way that it cannot get assembled with one another. Since parts are assembled at room temperature, it would seem practical to have the part length measurement refer to the assembly temperature closely as possible. So this is very important. It will expand more than the steel part, and assembly may not be possible. So this is why we need to see and we need to give such tolerances in such a way that the parts get assembled with each other, and we need to as a design engineer or as a production engineer or quality engineer, before if we are checking the part, so we have to keep in our mind all those things that these can if the part is manufactured correctly, then also the condition can come where it cannot get assembled. So all the scenarios as an engineer we need to keep in mind. So this is this L rule says this. Okay, now what does this next rule says? So what does this rule says? Unless otherwise specified, all dimensions and tolerances apply in a free state condition. So whatever dimensions we are applying into the engineering drawings, whatever tolerances we are applying to the in the engineering drawings, it is in a free state condition. Now the question occurs that what is this free state condition? Except there is some exception also, except for the non-rigid parts defined with the restraint notes. So in this two terminologies come out. First is free state condition. So first we are going to understand about the free state condition, that whatever dimensions and tolerances we are applying into the engineering drawing, it is in a free state condition except for the non-rigid part. So we are also understanding that how we are giving this to the non-rigid parts, and how we are demonstrate this non-rigid part if it get deformed. So first of all, what is free state condition? A state where only the force of gravity is applied. So as you know that when whatever part we are manufacturing, whatever if people are from the quality department, if they are measuring the part, they know that how to apply the pressure onto the whatever mechanism we are using. Either if we are using a micrometer or a CMM probe we are using to measure the part dimensions or the coordinate. So the minimum pressure we are applying onto the part to measure that part. So why we are applying the minimum pressure? Because if we will apply more pressure onto the part, it will get deformed. So because we know that whatever dimensions we have given or tolerances we have given, those in the those apply only in the free state condition, and the free state condition is where only the force of gravity is applied. So where only force of gravity is applied, this is in a free state condition. So the part which is going to measure onto the gravitational force, whatever part we are measuring, it is going to be onto the gravitational force is going to be applied on that. As you can see, all the measurements we use, like dial gauge we are using or CMM probe we are using, so we are applying the minimum pressure get applied onto that part to measure that part. The people who those who are involved in the measurement, they know that they know that they are applying the minimum plunger pressure during the measurements. So they know that they have to apply the minimum plunger pressure. Even in micrometers, we know that they have the ratchet mechanisms. If we will apply the more pressure, if we will apply the more required force, minimum required force other than that, it will get free. So that's why in micrometer we use the ratchet mechanism. That's the apply of the pressure will be not more than the requirement. So due to which the screw get free into the ratchet mechanism. So this is why whatever dimensions and tolerances we have given into the engineering drawing, it is according to the free state condition. Now for the exception of the non-rigid part, so first of all we will understand that what is called the non-rigid part. Non-rigid part basically are the parts like those made up of rubber or resins. So the parts which are made up of rubber or resin, like it can be O-rings gaskets. So these are some of the parts which are made up of rubber and resins. If we want to check the end measurement, because of the deformation, the force of gravity applied onto that. So if we are not applying the more pressure on that, still they can get deformed, because the rubber can get squeezed if we will not even apply their own weight. Sometimes with the you will see the tire with the own weight, they sometimes get contracted. So that's why whatever the parts are made up of rubber or resins, so we give some I will say note, through the note or through the F symbol. So we show that this part is in a non-rigid part. So if we are providing the F symbol onto the engineering drawing in the feature control frame into the geometric dimensioning and tolerancing, then it is a non-rigid part. So non-rigid part are those parts, those are made up of rubber or resin, where deformation is presumed to acquire due to a release of internal stress generated during the manufacturing process. If our part is a non-rigid part in which deformation can occur in a free state condition, so there we use the F symbol. So like this F symbol we use in the feature control frame. So with the help of example, we will be discussing this. So for parts that deform beyond the size tolerance or geometric tolerance in a free state, F symbol is written. So in this condition, you can see over here that this is a feature control frame. And in this feature control frame 2.0 F. So this F is showing that part is a non-rigid part. So F stands for the free state, which means to apply the tolerance under the free state. Whatever tolerance we are providing under the tolerances under free state. So this is very important. So in this example, you can see in any orientation, datum in this datum B must have the roundness. So this is roundness tolerance of 2 mm. So this is under the F. F is showing in this part made up of the soft material. So F, if we are applying F into any feature control frame, then the part is made up of soft material. So this is all about this rule. Now what this rule says. So this rule says, unless otherwise specified, all tolerances apply for the full length, width and depth. So this is very important, that whatever tolerance we are applying to the part onto the engineering drawing, it is going to be applied on full length, full width and full depth of the feature or the feature of size. So in this case, let's say D1 is a diameter and M5. So whatever tolerances we have applied onto the D1 diameter M5. So in this case, the tolerances which I have applied is applicable onto the full length. Not only this much length, whole length of the part is applied with this tolerance. So in this, the upper size, whatever tolerance we are applying to the D1 diameter, it is applicable to the full length. In this second example also, in this example, you can see whatever dimension, whatever tolerances we are applying onto the D1 S7, it is going to be applied onto the whole depth of this part. Whether it is here, it is here. So it is going to be applicable on each and every part throughout the depth of this part. So this rule basically applies that whatever tolerances we are applying, it is going to be applied on full length, width and depth. Now this rule says, so in this rule, what this rule says, that dimension and tolerances only apply at the drawing level where they are specified. A dimension specified on a detailed drawing is not required or applicable at the assembly level drawing. So what does basically this rule is saying, that whatever dimensions and tolerances we are applying on a part drawing, it is applicable for the part drawing, and what tolerances or we are applying on the assembly drawing, they are applicable only for the assembly drawing. We cannot use assembly drawing tolerances onto the part drawing tolerances for the part drawing, because in some cases we see that whatever tolerances we are giving in the assembly drawing, they are little higher than the part drawing. So whatever part drawing tolerances are there, it is for basically for the manufacturing purpose. So they are much tighter tolerances, very specific tolerances onto the part drawing. So this basic rule says that dimensions only applies for a drawing level. So whether it is for the part drawing, if it is a part drawing, it is only applicable for the part drawing, all the tolerances. And if it is in assembly drawing, it is applicable for the assembly drawing. We cannot mix it up. Let's say bolt, torque, welding, brazing, fresh fit and other assemblies. Therefore, detailed dimensions do not apply for the assembly level. Sometimes we see that we are using the, I have already told you, very tighter tolerances for the press fit parts. So whatever, they are not applicable onto the assembly level. At assembly drawing must repeat detailed drawing dimensions when they are to apply in the assembly. So we don't have to mix it up. This fundamental rules basically saying this. So what does this rule says? That wherever the coordinate system is shown on a drawing, it shall be right-handed. So whenever we are showing a coordinate system onto the engineering drawing, it should be always be a right-handed. What is right-handed? Right hand is basically a positive BL of the engineering drawing. So positive axis we are using into this right hand. Each axis shall be labeled and the positive direction shall be shown. So basically the positive direction is the right hand direction. So model coordinate system shall be compliance with the ASME by 14.41. So this is the standard of the ASME which is provided for the coordinate systems. So if we are moving towards the positive direction, let's say this is the positive direction or right-handed direction. This is a negative direction or the left-handed direction. So whatever time we have seen in the engineering drawings, if you have seen the it is shown in the engineering drawing that if we are using the, let's say, plus 5 BL, plus 6 BL, plus 8 BL, or the it is using the positive direction or the right hand side direction. If we are using the negative BL, like 4 minus 4 BL minus 2 BL, so it is into the left hand or the negative direction. So this rule says this. Let's take an example that if there is a car and the center point of the car is we are taking as a 0 BL. So if we see the right hand side door, so the right hand side door is the mirror image of the left hand side door. So basically the center point of the car is using as a 0 BL. If we are moving towards the right direction, it means we are moving towards the positive direction. Or if we are moving towards the left direction, then we are moving towards the negative direction. So so this is how we use this fundamental rule, and this is how we can use this into our engineering drawing. So this is all for this 16 fundamental rules. In the next session, we are going to start with another topic. Thank you everyone. So hello everyone, this side Manish from Skillable India. And in today's session, we are going to discuss a basic topic, which is dimensional tolerance, but it is very important for the design engineers to know about. You can see that we have two drawings over here. When I asked this question, I have asked this question to a lot of times to the students that tell me the difference between these two drawings. If I give them the dimensions, let's say I have given the dimension 50 and 50.0. So sometimes I ask this question that what's the difference between these two drawings? The answer comes from the students that moreover that they are the same drawings. But in practice, when we use into our engineering drawings, in practice we see both the drawings are different. Both drawings are different drawings. So if it becomes very essential and important for design engineers, it is very important and very essential for design engineers to identify and know the difference between dimensional units. So in today's session, we are going to learn about the differences between the metric based system and the inch based system. So whenever the dimension is a whole number, we remove the decimal point and the zero if it is a millimeter based system. So in this case, we haven't used any decimal, and the after decimal we haven't used any zero. So it means that this is a millimeter based system, mm based system. And if we provide decimal point like this and zero after the decimal point, means it is a inch based system. So this is a inch based system. So in today's session, we are going to understand this difference between both the system, millimeter based system and the inch based system. So in this first major difference identifying the metric system and inch based system is this, that if we are not using the decimal and zero, it is in mm. And if we are using the decimal and zero, it is inch based. So whenever the dimension is less than the whole number, many times the situation comes that the dimension is a less than the whole number. Let's say it is a dimension which is 0.5. So if I write over here 0.5. So whenever I write into the millimeter, I write like this, the dimension is less than, let's say that in case it is a 0.5. If I write into the inch based system, so I will not write 0 before the decimal. So I will write just decimal and 0.5. So 0.5 if I am writing means it is an inch based system, and if I am writing 0.5 means it is a millimeter based system. So then what we have is whenever it is greater than a whole number, let's say sometimes the condition comes that it is greater than a whole number, but by the fraction. Let's say we are having like this 50.5. So whenever I am writing 50.5 means it is in mm. Whereas in inch based system, if I am writing the same value, we write it as 50.50. So after 5 we are writing over here is 0. So so this is the basic difference between the millimeter based system and the inch based system. We are adding the decimal and the 0 after the decimal place, which tells that it is a inch based system. Now then what we have, if it is a unilateral tolerance, if we are using a unilateral tolerance, let's say unilateral tolerance. So if I have to write unilateral tolerance, I will write 50. In this case, unilateral means one side it will be 0 and other plus 0.1. Same if I want to write an inch based system, so I will write 50.0, then minus 0.0 and plus 0.1. So this is the unilateral tolerance in this inch based system. So in unilateral tolerance, we put 0 before the decimal and then tolerance value. Similarly, if it is a case of when it is inch based system, we have to add, if we are adding, let's say after 1 is 5. So in this also we have to put 0 over here, and 50.0 we cannot write 50.00. We have to give, because it has to be uniform in nature. So it has to be low uniformity. Next, whenever we have the dimensions in the form of plus minus tolerances, let's say the tolerances is having not unilateral and the plus minus tolerances are there. So how we are going to write it down in the form of plus minus tolerances? So in this case, if I write plus minus tolerances, 50 minus 0.1 10 and plus 0.25. So this is the plus minus tolerance we are writing down over here for the millimeter based system. For inch based system, how we will write? Minus 0.10 plus 0.15. So this is how we should be writing into the inch based system in the plus minus tolerances. Then we add, I've told you, then we add a 0 after it. If it is a 2 value, that 1 0 and 1 5. So we have to add 1 0 over here and 1 0 over here to look uniformity. Now we can write this dimension in the form of limit dimensions also. So how we can write it down, these dimensions in the form of limits, and what are the differences between the limit dimensions. So in this, if I'm writing down like this, 50.15 and 50.00. Similarly, if I'm writing down for the inch-based system, so 50.25 and 50.10. So basically we give the tolerance, and if we want to find out the tolerance value, so we actually minus the upper limit minus the lower limit. So in this case 50.1, then I should not write as the 50.50. Though it is a whole number, I have to add a decimal point and 0 to make it uniform. If it is a 2 decimal, then I have to add 2 zeros like this in this to make it uniform in the limit dimension, limit tolerance. So limit tolerance we are providing in this case. However, in this case you can see that both are same. How you will find out the difference? So these are different ways by which we can differentiate between the metric based system and the inch based system. But in this case you can see that both the ways. But if you take this particular example, in the limit tolerances, you can see that which are shown in the form of limit dimension, then it will become very, very difficult for us to find out that which is metric based system and which is inch based system if these limit dimensions are given. So in this particular case, we have to we will check with the help of geometric tolerances. Let's say, so like this, if it is given, so we will write it down like this. Sorry. So in this case, like this, we have to write it down. Let's say we will use the flatness like this, the geometric symbol. And if we have written 0.01, means it is millimeter based system. So in limit tolerances, we have to find out this with the help of geometric tolerances. So in this is a feature control frame. So if it is written 0.1 mm, so with the help of geometric tolerances, this is feature control frame. This is feature control frame. So with the help of this value, with the help of tolerance value, geometric tolerance value, we will find out whether it is a metric system, millimeter based system, or a inch based system. So with the help of this geometric value, we will be finding out this. So this is all for today's session between the metric based and the inch based system in the dimensional units. Thank you very much. Hello everyone, this is Manish from Skillable India. In today's session, we are going to discuss about the basic concepts of dimensioning and tolerancing. So how many types of dimensions are there? How many types of tolerances we use into our engineering drawings? So all the things we are going to discuss in this. Now that we have understood the concept of identifying the dimensional units, whether it's a metric millimeter based system or an inch based system in the previous session, we will try to understand different types of dimensions we have. We will try to understand all the types of dimensions we have and the tolerances. So whenever we have the dimension like this, in this, let's say I'm giving over here one dimension, which is 60 mm. So like this, the numerical is expressed in millimeters. Whenever I'm writing without a decimal and 0, it means it's a millimeter based system. So this drawing is millimeter based system. So this is 60 mm. So this is called the dimension. So this is called dimension. Like this, we have different types of dimensions on this drawing. So in this, you can see 20 plus minus 0.1 mm, 60, 30 mm. All these are dimensions. So now one of the fundamental rule of GD&T says tells that any dimension could carry a tolerance. Should carry a tolerance. Any dimension should carry a tolerance. Because manufacturing a part exacted to this dimension 60 mm is very, very difficult. So what we have to do is we have to add a tolerance in this. Let's say I am adding in this like plus minus 0.1 mm. So this tells that the part can manufacture anywhere between 60.1 or 59.9 mm. So in between this, so this portion of the dimension 60 plus minus 0.1 in this 60 mm is called the dimension, and 0.1 plus minus 0.1 is the tolerance. So when the word of question is what it is tolerance, when the question comes what is tolerance, so sometimes when we ask this question to the people, they say plus minus 0.1 in this is a tolerance, or 0.1 is a tolerance. But if we go through with the definition of the tolerance, so what is tolerance? So the definition here by the definition of tolerance is the difference between upper limit and the lower limit. So this is known as the tolerance. So you can when we convert this is into the upper limit, so this 60.1 is upper limit and 59.9 is a lower limit. So if we have the difference between these two, so the difference between these two is 0.2 mm. So 0.2 mm is the tolerance we have. So this is very, very important to understand that how to calculate a tolerance into the engineering drawing. So next, whenever we give plus minus tolerances in this way, whenever we give plus minus tolerances like 60 plus minus 0.1, so this is the plus minus tolerance. We say plus minus tolerance. So this is one of the terminology which we use regularly. The plus minus tolerance. So this particular dimension 60 plus minus 0.1 known as the nominal size. So in this case, this dimension is called the nominal size. So now the question arises, what is nominal size? Usually nominal size is the size that is specified in the drawing, which is derived by design. So this is called the nominal size. I will write down the nominal size. What is nominal size? Nominal size is the size usually that is specified in the drawing which is derived by design. So this is called the nominal size. The next terminology what we have is to understand is called the basic dimensions. Now we are going to understand about the basic dimension. So now what is basic dimension? So we will understand about the basic dimension. Basically, if we understand with the help of definition, then it is known as any dimension which put inside the box is called the basic dimension. Like in this case, you can see this 30 mm dimension which is put inside the box is called the basic dimension. It is the theoretical dimension. It is theoretical dimension. Theoretically exact dimension, I will say. Exact word is very important. Theoretically exact dimension used for specifying location, orientation, or a profile. So this is called the basic dimension. So in this case, the basic dimension you can see written is in like this 30 mm. So 30 mm in this is a basic dimension and is used to get the location of this hole. So location to this of this hole, we use this 30 mm as a basic dimension. For the exact dimension, we use this specifying the location of the hole. So the next terminology what we have here is limit dimension. So in this now we understand that what is limit dimension. So we will give you I will give you an example of that of the limit dimension is here. If we are using 60 plus minus 0.1 mm. So if we use similar terminology in the limit dimension, so we have to write limit dimension like 60.1 and 59.9. So this is the upper limit I have already told you, and this is the lower limit. So this is how we have to specify onto the drawing with the limit dimension. So then this type of dimension style. So this type of dimension style is called is known as limit dimension. Now we have something known as unilateral tolerances. So what are unilateral tolerances and how they are helpful for us? So we are going to find out unilateral tolerances. With this example, we are going to understand a lot of terminologies in today's session. So what is unilateral tolerance? In the previous session also I have told you this unilateral tolerance. So here if we use 60, lower limit is 0 and the upper limit is plus 0.1 mm. So whenever the tolerance value deviation is is only towards the positive direction. So the deviation of tolerance should always is only towards the positive direction. It is known as unilateral tolerance. So here the lower limit is 0 and the upper limit is plus 0.1 or 0.2 or whatever the tolerance we are taking, but it is only towards the positive. The deviation in the tolerance we can have in the manufacturing is only in the positive direction, not in the negative direction, because the other direction is 0 over here. Now the other terminology what we use regularly is in this. So this is called the unilateral tolerance. So now we go back onto the drawing, onto this previous example. So 60 plus minus 0.1, you can see over here the dimension over here. Here the deviation is on the positive direction as well as on the negative direction. At the same time, it is on positive and positive direction it is 0.1 mm plus 0.1 mm and negative direction 0.1 mm. So in this particular example, 60 plus minus 0.1. So this is the example of equal bilateral tolerance. So this is the example of equal, because it in positive direction it is 0.1 and in negative direction it is 0.1. So 60 plus minus 0.1 is the example of equal bilateral tolerance. So this is so finally there is one more type of tolerance which is called as reference. There is one more type of dimension which is called as reference dimension. But before starting the reference dimension, first of all, one more tolerance is there. Let's say if I have given 60 over here and in minus direction 0.1 mm and plus direction 0.2 mm. So in this particular case, this is the example of unequal bilateral tolerance. So this is the example of unequal bilateral tolerance. So these are the examples of the unilateral tolerance, equal bilateral tolerance, and unequal bilateral tolerance. Now there is one more terminology which is used frequently in the engineering drawings, where while studying 16 fundamental rules of GD&T, I have told you of this, the reference dimension. At that time I have told you that I will tell you about the reference dimension. So what is basically this reference dimension is, I will with the help of this example I will let you know. Finally, there is one more dimension. I will explain this dimension of the reference dimension. So in this case, this is the example. Okay. So when you take this drawing, very first dimension that we will meeting, if we are manufacturing this part, let's say, if we are manufacturing this part, so first of all, what we understand in this part is, first of all, first we will meeting for the manufacturing, we will see this 60 plus minus 0.1 mm. So let us say that the manufacturer maintained this dimension as 60.1. So while manufacturing, a manufacturer maintained this dimension at 60.1 mm. So let's say that the manufacturer maintained it, let's say, sorry, not 61.1. Let's say manufacturer maintained 59.9 mm in this case, because 60 plus minus 0.1 having tolerance. So whether it is produced 60.1 or 59.9. So the manufacturer maintained this dimension 59.9. So he is maintaining this dimension. For this, he has maintained this dimension, this particular dimension from here to here. Let's say he maintained 20.1, and then this dimension, this from is this point to this point, the manufacturer also maintained 20 plus 1 the dimension. So here here the dimension is, now if we add up both the dimension 20.1 plus 20.1, so it will come 40.2 mm. Now the overall dimension of the part from this point to this point is 59.9. So 40.2. So in this case, what we get over here is 19.7. But the lowest dimension, what can we maintain in this, from this point to this point, we are after manufacturing. So as per the drawing, that this dimension should not be less than 19.9. So maximum this can have 19.9 in with the help of 20 plus minus 0.1. But after manufacturing, in actual reality, we are getting 19.7 mm. Okay, so whenever we come with such problems in the manufacturing, what we do is, then we have to identify the dimension which is non-functional dimension. So when we come such problems, so we have to find out that which dimension is a non-functional dimension. So let's say we have found it out that this last dimension is a non-functional dimension. So here what we will do now is, so after identifying the non-functional dimension, in this case I have identified that this dimension is a non-functional dimension. Give that in parenthesis. So now this dimension I will give into parenthesis, 20 parenthesis. So this is called the non-functional dimension or reference dimension. Non-functional dimension or reference dimension. So this is how we have to find out this dimension, and the usage of reference dimension should be minimal, because in studying about the 16 fundamental rules of GD&T, it is saying that we have to minimize the use of reference dimension onto our engineering drawings. So the reference dimension is which is used for only reference and nothing to do with the functionality of the part. So this is all about the dimensions and tolerances. In the next session, we are discussing the next topic. Thank you everyone. Hello and welcome everyone. This is Manish Sharma from Skillable India, and in this particular session we are going to discuss the very important topic, which is the coordinate tolerances. When previously the coordinate tolerances we use into our engineering drawing when there is no existence of the GD&T. But the problem is coordinate tolerance system has lot of drawbacks. So in this particular session, I am going to discuss over what are the advantages of GD&T over the coordinate tolerances and why we have removed this tolerance system from our engineering drawings. In coordinate tolerance, first of all, we will know the definition. So coordinate tolerancing system is a dimensioning system which a part feature located or defined by means of rectangular dimension with plus minus dimensions, tolerances, plus minus tolerances. So whenever we are talking about the plus minus tolerances, like these tolerances we are talking about. So this type of tolerances when we provide, so these are called the coordinate tolerances. This is called the coordinate tolerance system or plus minus tolerance system. With coordinate tolerance tolerancing, dimensioning the part are given, but the drawing does not indicate how the part is to be set up for measurement. So this is the very important thing that is a drawback into the coordinate tolerancing, that it is not showing that how the part or it is not indicated. Actually, the datums are not finalized in that which datum we have to use, primary, secondary or tertiary datum. So these datums are not being defined in the engineering drawing. That's why in the drawing and the manufacturer, there is a lot of confusion between that, and in that confusion, lot of parts get rejected. So in this particularly coordinate tolerance system, there are a lot of drawbacks, and in this I'm going to discuss. So with the help of this example, you can see this method is simply this coordinate tolerance is simply incomplete method, and it does not precisely communicate the part requirement. It had a lot of drawbacks that there were. I will be telling you three major drawbacks of this coordinate tolerancing system. First one, we are in this particularly in coordinate tolerances, we cannot precisely communicate the part intent or the requirement onto the engineering drawing. I have already told you that we cannot mention that we in the coordinate tolerance system we do not mention datums. So datums are not there, and datums are not there. Geometric characteristic is not there. Geometric characteristics we do not define onto the engineering drawing. So these are some of the drawbacks which are very important, which have to be overcome, and that is fulfilled by the geometric dimensioning and tolerancing, which is GD&T. So in this particular coordinate tolerance system have three major drawbacks are listed below. So the first drawback is the drawing does not indicate how the part is to be set up or for measurement. So the first drawback is that it does not indicate the datums that which has to be used, primary datum for the inspection purpose or for the checking purpose for the multiple quality assurances. So it does not indicate that the part how to how to be set up the part for measurement. Second drawback is square or rectangular shape tolerance zone. So in this the second drawback is it is square and rectangular shape the tolerance zone. Third one is ambiguous instruction for inspection. So one by one we will be understanding all three drawbacks. So the first one is drawing does not have the proper indication for measurement. So the location of these holes could be measured in multiple ways because of it is not specified onto the drawing. So in this you can see that the dimensions are only provided in the form of plus and minus tolerances. So here the position of this hole, if I want to find the position of this hole, given is only in the form of plus minus, let's say here 0.2 tolerance in both x and y direction. So 0.2 tolerance is over here, 0.2 tolerance is over here. So from these two faces, if we are talking about these two faces, so we can find out the center of this hole. So in this direction it is 25, and in this direction it is in the vertical direction it is 37.5. So with this this is the first drawback. In the second one, it is square or rectangular tolerance zone. So using the coordinate dimension, the shape of the tolerance zone for the position of the center of each hole is a square shape. So let's say we are taking an example for this position. So if I am taking this hole and I am using this as a true center, so what we are going to get is over here is true center. So this is we are going to use as a true center, this whole center. Now we have tolerances of 0.2 plus minus 0.2. So this 0.2 plus minus. So total we have 0.4 over here and 0.4 over here. Now what the tolerance on both the side by which we end up the square shape tolerance, because we have plus minus tolerance means this is we are having 0.4 and this is 0.4, so that we are having only the square shape tolerance zone. The shape is called the shape. This shape, square shape, is known as the tolerance zone. Since the shape is square, so we call it up as a square tolerance zone. If you see from the true center, if the hole is 0.25 in horizontal direction in this direction and 0.25 in the vertical direction. So but when the tolerance goes towards the diagonal, when this moves towards the diagonal, it is more, and it is like in this case you can see this in this distance, diagonal distance is more than this 0.4. It is 0.57. So when we have more tolerance in diagonal direction, why not we have same amount of tolerance throughout and this was the problem. Why this diagonal tolerance we cannot use in the whole circle form? Why we are lacking? If I am creating one circle over here like this, so this tolerance zone, this extra part, we are missing into this coordinate tolerance system. So this is one of the biggest problem what we are facing into this coordinate tolerance system, this square and rectangular shape tolerance zone. Now the third one is ambiguous instruction for inspection example. So in this particular example, in this drawing, it is not clear that how I have to check the center. In this, there are no datums. So we cannot find out that what datums we have to use first, second, and tertiary. Primary, secondary, and tertiary datums are not mentioned. So how I am going to check this part is not mentioned. Here we have two probabilities. So the probability number 1 and probability number 2. A person who is checking the part face on the vertical direction, horizontal direction, this face he can put onto the horizontal direction. So the distance between this hole and this point will be different. And if we check this in the vertical direction, if we put, so this distance will be changed. So the vertical surface like this, and then just have a one contact point in this particular case. You can see this one contact point over here and the one contact point over here. We can also check this same part when this will be straight. This part will be shift. This surface will lie on this surface, and here is a gap. So the distance will change. So these type of datums, datum A, datum B, datum C, is not mentioned in this particular that which surface should be horizontal, which surface should be vertical, and to be aligned with the mating surface or to the surface plate. whether it's a granite or. So this is very, very important to check that with the help of example, we have understood that these are some of the problems which we face into the coordinate tolerance system. Face problem in measurement. Now we move forward. So these are some of the example. So this is the difference between the coordinate tolerance system and GD&T. So in this, you can see in this example, we have defined the plus minus tolerances 15 plus minus 0.05, and these dimensions we have provided in the plus minus tolerance. But in this case, you can see, so if there you have it in this drawing, the center of these two holes are given with the dimensions. We can also use, let's say if I am giving this dimension with the given to the positional tolerance. We need to find out the position tolerance of this hole. Let's say this hole. So this type of dimension are more accurate. So in this you can see this type of dimensions are more accurate, and we have defined the datums in this to check. So in this also we have defined the datums. So this is a precisely, in this example, it is precisely communicate their part requirement better than what we get into the coordinate tolerance system. So here first, so these are the shortcomings we have getting into this example. Now, similarly, if in that case, if we use the square tolerance zone, so in this square tolerance zone, we get less amount of tolerance, coordinate tolerance system, which overcome by the circular tolerance zone. So in this case, we are getting this black area. You can see this black area, we are getting 57% more tolerance zone, in GD&T. So this is the major drawback what we are having in the coordinate tolerance system. True center, you go in any direction, you will get the same radius, whether you are moving in any direction. In this direction you will get the same radius, in this direction you will get the same radius, in all the direction, whichever direction you move, you will get the same radius, because of which we have the advantage apart from the that converting a square into a circle. So we have converted this square tolerance zone into a circular tolerance zone. So we have more area, and we get 57% more tolerance than we get in the coordinate tolerance system. So in this ambiguous instruction for the inspection, when we get the coordinate tolerancing system, so we may end up get different results. So in this we get different results after checking the part. For the after the inspection, we get different results. But whereas if we use the GD&T, so this is the example of GD&T. If we use for the inspection, so it is very clearly shown that which datum, whether datum A, B or C, we have to use as primary datum, secondary datum and tertiary datum. So so the checking methodology is very clear for the inspector, and we get the accurate results with the help of GD&T. Now, as this is shown in this example, you can see this is also the example of coordinate tolerancing system, where you find all the dimensions with plus minus tolerances. When you have a drawing like this, whenever you have a drawing like this, you maybe end up part produced like this. So you can check any of the dimensions, which is the dimensions will be within the limit, within the tolerance, but within the limit of size, but the shape is not. So in this you can see that any dimension, all the dimensions are within the limit of size, and all the tolerances are within the tolerance, but the shape is not. So this is the very frequent problem with the coordinate tolerancing system. Now this is the another method by giving the instructions onto the drawing. So we have in the form of ambiguous instruction giving on drawings, which leads to misinterpretation. So this is not a functionally fit part. In the previous part, it is not functionally fit. In this alternate method, we can follow is to have the detailed literature. So the detailed literature like this it is given. But this alternate method have disadvantages also. What disadvantages is it? One, it is a language dependent. So this type of method is language dependent. Another type of it is misinterpretation is very frequent. It consumes more space. So this type of consumes more space onto the drawing. So more time to make such type of drawings. So we wanted some better system, and that system called we have used as a GD&T. Okay, so geometric dimensioning and tolerancing, where in this you can see where all the symbols are used to get the precise communication with the part requirement or intent. So all the precisely communicated requirement. So in this drawing you can see that each hole or each slot is defined particularly with the dimensional tolerances. So it not only controls the size but also controls the shape of the part. So this is very, very important that all the dimensions in this, all the datums are mentioned, whether we have to, if for the inspection purpose or the quality insurance, if we want to identify the each and every dimensions onto the part, if we want to inspect it. So we have to be defined each and every datum. So what's the primary datum, secondary datum and tertiary datum. In the coming sessions, I'm going to tell you about datums in very detailed manner, that how the 6 degrees of freedoms we use. So 3 are rotational, 3 are translational. So all those things about datums, feature of size, in the coming sessions we are going to discuss. So this is all about this session of coordinate tolerance system. So it has a lot of drawbacks. That's why we use the geometric dimensioning and tolerancing. Thank you everyone. Hello and welcome everyone. This is Manish from Skillable India. One of the very famous terminology which we use into our GD&T engineering drawings is a feature. Okay, so in today's session we are going to learn about feature and feature of size. In feature we will going to learn that how many types of features are there and how to recognize the feature of size. Okay, so most of the time we use this terminology without really knowing that what it really means. Okay, so we are going to discuss about feature, that what different types of features are there and what we can use into our GD&T drawings. Okay, so if I told you this definition, so feature is general term used for a physical portion of the part. Okay, so feature is a physical portion of the part, or its representation on drawing models and digital data files. Okay, so features can be any. Okay, it can be a surface can be a feature, a whole surface can be a feature, tap is a feature, fillet can be a feature, short can be a feature. So all these are the feature into the drawings. Okay, so these are considered to be the feature. The term feature is never used to describe imaginary items. Okay, so feature are not for the imaginary items. They are for the physical portion of the part. Like center line, axis, planes are not features. Okay, so these are some of the example. Now, in this image, what you can see is a rectangular block. Okay, so with this example, in this image you can see a rectangular block with 4 holes. Okay, let's say this is a block which is having a rectangular block and which is having 6 faces of. So in this 6 faces of this block are 6 feature. Okay, so these are 6 features and 4 holes. These 4 holes are also considered as a 4 features. So 4 holes also considered as a 4 feature. Okay, so in total, if we see, there are total 10 features in this part. 10 features in this part. Okay, so this is called feature, and this is how we can find out the differentiate between the features. Okay, now we will understand the complex feature. Okay, so what is complex feature? This is the next terminology which we used. Okay, so what we have is complex feature, which is nothing but a single surface. Okay, we have a single surface of compound curvatures or a collection of feature. Okay, so in this example you can see that this is a flat surface, then this is a fillet, then there is a tapered surface, then there is a fillet, and then there is a flat surface. Okay, so it is combination of different features. Okay, single surface is having a compound curvature of collection of features. So in this you can see, in this there are collection of features. Sorry. Yes, okay. So in this example, we have a fillet surface. Okay. So these are all which is connected with the all one another. Okay. So all the features are connected with one another. From point A to point B, collection of features can be called as single feature. Okay. So these collection of features are called as single feature. Called as single feature, and this is called as complex feature. So this is all about the complex feature. Now we are going to understand the next terminology, which is the interrupted feature. So then we have a interrupted feature, which is nothing but a feature with a one gap. Okay, so in this you can see, in this feature, this is a single feature with one gap. Okay, so this is considered to be a gap that divides into two or more feature. Okay, so this gap actually divides it into two features, this surface and this surface, as individual features. So this is called the interrupted feature. In this example, you can already said we have slot. In this is a slot which divides this feature and this feature into two features. Okay, so most often these two features are considered to be two separate features. Now people started calling as a single feature, called as interrupted feature. Okay, so this is also we use as interrupted features. Now in the now we are going to start with a feature of size. Okay, so it is very important topic to learn in this GD&T, because again and again we are going to use this feature of size. Okay, so now we are going to discuss about the feature of size. So what feature of size is? Feature of size is a general term used to refer to either a regular feature of size or a irregular feature of size. Okay, so there are mostly two types of regular feature of size we use. If we go through the definition, so feature of size refers to any surface or set of parallel surfaces associated with the size dimension. Okay, so let's say there are parallel surfaces which are any surfaces which are associated with the dimension. Okay, parallel surfaces here seen, and any surfaces or a set of parallel surfaces associated with the dimension, specifically example included in this example. Okay, so feature of size is of two regular feature of size and irregular feature of size. Okay, irregular feature of size. What is regular feature of size? RFOS it is called. It is if a cylindrical surface or a spherical surface or a circular element or a set of two opposed parallel lines. Okay, so what are things? cylindrical surface, spherical surface, or a circular element, or a set of two opposed lines, parallel lines, element or opposed parallel surfaces associated with directly tolerance dimension. Okay, associated by directly tolerance dimension is known as regular feature of size. Okay, in this example you can see that these are two parallel lines. This line and this line are two parallel lines. This is associated with the dimension. So this is the dimension. Okay, so if this is associated with the dimension, means this is regular feature of size. Okay, this dimension is also this line and this line parallel to each other, and they are associated with the dimension which is 120. So this is also the example of RFOS. Okay, in this also this dimension, actually this dimension it is showing. So in this part, this is a circular part, okay, cylindrical part, shaft which is having groove over here. So in this example, this is also we can check. Okay, so this is also an example of regular feature of size. So if this feature we have in this, you can see the cylindrical shaft. Okay, and it is associated with the diameter. So this is a regular feature of size. So the faces, the parallel faces are there. Okay, so groove, I have already told you that groove diameter is a circular element which is associated with the dimension. So this is groove is a circular element throughout the shaft which is associated with the dimension 20. Okay, so this is also the example of regular feature of size. Okay, so in simple layman language, if I tell you this thing, if you want to understand, so in simple layman language, if you want to understand that what a regular feature of size is, so if you take a vernier caliper, okay, if you take a vernier caliper and if you are measure any part, okay, and if you are able to measure that part with the help of vernier caliper, whatever dimension you will be measured with the help of caliper, then it is considered to be a regular feature of size. Okay, so simple layman language, if we can measure with the we can measure with the help of vernier caliper, we can measure with the with vernier caliper, then the dimension is regular feature of size. Then dimension is regular feature of size. Okay, now the second one is irregular feature of size. Okay, so in irregular feature of size also there are two types of irregular feature of size. First one is type A and second one is type B. When it comes to the irregular feature of size, I have already told you, which is nothing but a, in this, if we go with the definition, so this nothing but a directly tolerance feature. It is a directly tolerance feature or collection of feature. Okay, so basically the directly tolerance feature or a collection of feature which that may contain or to be contained by unrelated actual meeting envelope, that is a cylindrical or sphere or two parallel opposed parallel planes. Okay, so in this, what this definition is showing, that say if I want to check this dimension from this point to here, okay, so it is not possible to check with the help of vernier caliper. So this dimension we cannot measure with the help of vernier caliper. So for that, what we have to do is we have to create one unrelated actual meeting envelope. What is this actual unrelated meeting envelope? We will discuss in the further session. Okay, but it is an let's say this is a this envelope we have created. Okay, the above that part and the below this part. So now we are able to measure this part from this distance from here to over here with the help of vernier caliper. Okay. So now by creating this actual meeting envelope and related actual meeting envelope, we are able to check the part with the help of vernier caliper. So that's why this is the irregular feature of size. Okay. And this is very, very important, that how to create a actual meeting envelope. We will understand in the near sessions. So you can see this collection of features which are associated with the dimensions. Okay, so this feature is associated with the dimension and this feature is associated with the dimension. So after creating the actual meeting envelope, the height, we can measure the height of this part with the help of vernier caliper. So such objects are called the irregular feature of size, type A. So this is called the type A, irregular feature of size. Now the second type is type B. Okay, so irregular feature of size type B, what does this say? It is directly tolerance feature or collection of feature that may contain or to be contained unrelated actual meeting envelope, that is other than the cylindrical sphere or two opposed parallel lines. Okay, so other than the cylindrical sphere and two opposed parallel lines. In the type A, you can see in type A, these are two parallel opposed lines. So in type A, if I will, in type A, only the opposite parallel lines, in this case, these are the opposite parallel lines, or the surfaces should be cylindrical in nature. Okay, cylindrical or sphere or two opposed parallel lines. If these three conditions are to be satisfied, then it is into the type A, and it is and the dimensions cannot be measured with the help of vernier caliper. Then it is into the type A. If the part is other than the cylindrical or sphere or two opposed parallel lines or cannot measure with the help of vernier caliper, then it is considered to be the type B. Okay, so now it is considered to be the type B. So in this case, you can see the part is having a groove inside this a groove which is in triangle in nature. So it is not a cylindrical nor a sphere or not two opposed lines. Okay, so this is a triangular surface. Okay, so now we have to create a actual meeting envelope. In this case, this is we have created, which is exactly that shape. So in this example, we can have a triangle. I have already told you, to measure this triangle, we require an envelope. Okay, this envelope to counter shape of a triangle itself. Okay, so this is, we have created an counter shape envelope. Counter shape envelope. Okay, this counter shape envelope of a triangle itself. So this shape is not a cylindrical shape, nor this is not a cylindrical shape, nor a spherical shape, or nor a two opposed parallel planes. Okay, so hence this is called the type B irregular feature of size. Okay, so this is very, very important that if I will summarize all this in one go. Okay, so what is the regular feature of size? First of all, what is the feature of size? So feature of size, any dimension which we can measure for the features onto the part. Okay, then feature of size is particularly divided into two: regular feature of size and irregular feature of size. So what is the regular feature of size? A regular feature of size is a size which we can measure with the help of vernier caliper easily, whether it's two parallel opposed surfaces or let's say any hole is there, any other dimension which we can measure with the help of the vernier caliper. It is into the regular feature of size. Then the second part is irregular feature of size. In irregular feature of size, we have two types: type A irregular feature of size and type B irregular feature of size. In type A irregular feature of size, we have to create a unrelated actual meeting envelope. Okay, so in type A, we can only check cylindrical surfaces, spherical surfaces, and the two opposed parallel planes. That is considered to be into the type A. Okay, and irregular feature of size cannot be measured with the help of vernier caliper. That's why we have to create an envelope in such a way that after that we can measure the dimension with the help of vernier caliper. Okay, In the irregular feature of size type B, what we do, we create other than the spherical or cylindrical or two opposed planes, let's say there is a triangular or any hexagonal shape. Okay, so for that we create a counter shape envelope. Okay, so in this I have already told you, in this triangular shape we have created a counter shape envelope to measure the to check the or measure the part. Okay, so this is the type B irregular feature of size. So this is all about the topic. In the next topic, we are going to discuss about the actual meeting envelopes. Thank you. Thanks a lot. Hello everyone, this is Manish Sharma, and in today's session we are going to discuss the very important topic, which is actual meeting envelope. So what is actual meeting envelope and how we used with the help of in this feature of size? So it is very important to understand. So what is actual meeting envelope? Is basically an actual meeting envelope is an envelope that is inverse of a feature of size that just coincides with the extremities or high points of a feature. So what is this actual meeting envelope in layman language? If we understand, let's say if there is a part. So with the help of this example, we are going to understand about the actual meeting envelope. So this is a part. So in this part, if we want to check that what are the high points in this hole. So this part is having a hole. So this is a hole. If we want to check that what is the maximum size of the shaft can enter into this hole. So what we have to do is we have to create an envelope to check that what size of dimensions is possible to enter into this hole. So to understand this better, we take this example. So for hole, and first we will understand for hole, and then we will understand from the shaft point of view. So for hole, if you see, the actual meeting envelope is the largest cylinder. So this is, let's say, shaft, or you can say cylinder in this case. So the in this is a cylinder. So the actual mating envelope is the for hole, an actual mating envelope is the largest cylinder that may expand so that it coincides with the actual hole surface at the high points. If this cylinder enters into this hole and it expands inside in this direction, it expands in this direction. So what will happen? It will touch the high points of the hole. So let's say this is the high point, this is the high point. So it will touches the high points of the hole, so that we can find out that what is the maximum size, what is the largest cylinder can enter into this hole. If we see in this example, so now you can see in this in this drawing that the shaft or the cylinder has entered into this part in the hole. So it is touching the maximum points of the hole. So these are some of the so these are the maximum size of hole, the points which are extremities. So these are extremities points which is touching by this cylinder. So this is called an envelope. So this is called actual mating envelope in case of hole. So in case of hole, the cylinder will be the envelope to find out the maximum, to find out the largest cylinder size. So the maximum size shaft or cylinder can enter into this hole. So so here the shaft diameter, this is the maximum shaft. So this shaft is the maximum shaft. Maximum shaft diameter that can enter into this into the hole, because the shaft diameter is touching the high points. This largest cylinder diameter is the actual mating envelope. Okay, so I have already told you this largest cylinder diameter is known as the actual mating envelope. actual meeting envelope for this internal feature. So for now, we are talking about the internal feature. For internal feature, we are discussing this. For internal feature means for whole. Internal feature means whole. So this discussion is for the whole. Similarly, for the shaft. Now we will understand that what actual meeting envelope looks like for the shaft. So let's say this is a shaft. This is the example for actual meeting envelope for the shaft. So the actual meeting envelope is the envelope is an envelope that is inverse. The definition is same. So for shaft, an actual meeting envelope is the smallest hole that may contract so that it coincides with the shaft surfaces at the high point. Sorry. So this is the shaft. So this is the envelope. So this is the envelope in this case. This is the actual meeting envelope. So in this case, when the shaft will enter in this point, so the hole, this is hole points contracted. So this point, these points will be contracted and touches the high point of the shaft. So this is the high point of the shaft. So these are the high point of the shaft. So this is the smallest hole. So this is the smallest hole which can enter into the shaft by touching the high points of the shaft. So this whole diameter is actual meeting envelope. Okay. So in this scale, in this example, this hole is the actual meeting envelope for the shaft. Actual meeting envelope for the shaft. For shaft. In the previous case, it is for the internal feature of size. This is example for the external feature of size. So external feature of size, we are talking about shaft. Shaft. Now, actual meeting envelope basically is of two types. First one is the unrelated actual meeting envelope. And second one is related actual meeting envelope. So we are going to understand each of them one by one with the help of example. So first of all, we are going to discuss the unrelated actual meeting envelope. So now we will see that the unrelated actual meeting envelope will almost never be perfect perpendicular to the datums. So this point is very, very important because the unrelated actual meeting envelope will never be the perfectly perpendicular to the datum. So in this also we are going to understand with the help of example, with the help of shaft and with the help of hole. So both the cases we will understand that how it is important. So in the right side of the figure that shows the related actual meeting envelope is the largest perfect cylinder that is perpendicular to the datum and fits inside the physical cylinder. This is the definition. So it is an envelope that is similar perfect feature. It is saying that it is a similar perfect feature counterpart expanded within an internal feature of size or contracted about an external feature of size. So this is an external feature of size case. External feature of size. And this is internal feature of size. And size and not constrained to any datum. So it is also saying that it is not constrained to any datum. So in this particular example, if we see for shaft unrelated actual meeting envelope, so this is the datum. So A is showing the primary datum. So this is showing the datum. This is the actual design. And if we see, so these are the dimensions and it is given the 0.3 maximum material condition, which is perpendicular. Now the unrelated actual meeting envelope, I have in this, you can see in this part, you have a boss like structure shaft. And in this to measure the axis, if we see the axis of the shaft axis of the shaft you use as an envelope in this case. So in this case, this dotted lines, these lines are the actual unrelated actual meeting envelope, and this is saying that not constrained to any datum. That's why this is not perpendicular to this datum. So this this unrelated actual meeting envelope is not perpendicular with the datum. It is not constrained with the datum. Actual meeting envelope not taking the reference as a datum. So this unrelated actual meeting envelope is not taking reference as a datum. So this envelope which is not taking as a reference is called the unrelated actual meeting envelope. This will give the axis of the boss. If we see the axis in this case, so whatever the axis of this of the shaft will be, so same will be the axis in this case. So axis will be same for both the cases, for both shaft and the envelope in this case, but it is not perpendicular or not constrained with the datum. Similarly, we have the in this is the case of cylindrical pin or shaft, you can say. So that touches the high points. So this is touching the high points of this shaft. So this actual meeting envelope touching the high points of the shaft, and which is not using reference as a datum. So this is the unrelated actual meeting envelope. Similarly, for the hole also, for the internal feature of size for hole also, in this case, it is also not using reference as a datum, and the shaft hole axis and the axis of the envelope is same. So what the axis for both in both the cases are same, but it the envelope is not using reference as a datum, not using reference as datum as reference. Now we will learn about the related actual meeting envelope. So what about the related actual meeting envelope? So in this you can see related actual meeting envelope is an envelope that is similar perfect feature counterpart expanded within an internal feature of size and contracted about an external feature of size, while constrained in either orientation or location or both to any applicable datum. So in this case, you can see that the actual meeting envelope. So in this case, this is the actual meeting envelope, related actual meeting envelope, but it is also touching the high points, but in a but taking reference as a datum as a reference. So in this case, actual related actual meeting envelope, the envelope is using a datum as a reference. So it is perpendicular. You can see it is perpendicular to the, this envelope is perpendicular with the datum. So in this case of if you want to understand this concept, it is very similar to the unrelated actual meeting envelope only. But in this case, the only difference is this: the unrelated actual meeting envelope it does not take any reference as a datum, but whereas related actual meeting envelope takes the datum reference. It is using this reference as a datum as a reference. So here we have an example of a part like boss. So this is boss. So this is an envelope. The envelope contracts. The envelope contracts so that the actual meeting envelope, which is taking the reference of the datum surface, in this case orientation with the datum surface is called the related actual meeting envelope. So this is for both the condition, this is for the shaft or the pin, and this is for hole. Similarly, in this part also, if we have a hole. In this is an envelope which expands. So in this is also, it is touching the high points. So this envelope is basically touching the high points, touches the high points of the hole. At the same time, the surface is perpendicular. So this datum surface, it is using datum as a reference, is perpendicular to the top surface. So this envelope is perpendicular to the top surface. So it is taking as a reference datum. So this is also the example of related actual meeting envelope. So this is all about the actual meeting envelope. Hope you understand the concept of actual meeting envelope. For who, if I summarize this actual meeting envelope, so basically it is of two types: unrelated actual meeting envelope and related actual meeting envelope. In unrelated actual meeting envelope, we do not use, never use the datum as a reference for the envelope, but in difference between the related actual meeting envelope, we basically use the datum as a reference. Hello everyone, this is Manish Sharma from Skillable India, and in today's session we are going to discuss the topic which is the actual minimum material envelope. In the previous session we have discussed about the actual meeting envelope. It is similar to that, but it is almost opposite to the actual meeting envelope. Why it is, we will be discussing each and every point in this topic. So what is actual minimum material envelope? So I've already told you that it is an opposite of actual meeting envelope. Actual meeting envelope is an envelope which is outside the material. So basically, actual meeting, in the previous session we have discussed actual meeting envelope. So actual meeting envelope is an envelope which is outside the material. We are discussing the outside the shaft. We are creating an envelope which is outside the shaft. We are creating an envelope into the hole which is inside the hole. So the outside the material, we are discussing this concept of actual meeting envelope. But actual minimum material envelope, which is in today's session what we are going to discuss, for this actual minimum material envelope is the one which is inside the material. So this is also called the imaginary envelope. So in this particular actual minimum material envelope, we are going to discuss inside the material. So we cannot go inside the material. So that's why this actual minimum material envelope is actually an imaginary envelope. So this envelope is also called an imaginary envelope. So as per the standard, this is the definition. Actual minimum material envelope is an envelope that is similar perfect feature. So similar perfect feature or the smallest size that can be contracted about an internal feature of size, internal feature, so that it coincides with the surface of the lowest point. In the previous session, in actual meeting envelope, we are getting the high points. We are getting the high points of the shaft or high points of the hole. In this actual minimum material envelope, we are getting the low points. So the low points of the shaft, the low points of the hole, because this is the imaginary envelope which we are creating inside the material. So similarly, it is similar concept. So don't worry about it. So we are going to discuss with the help of one example. So in this example, you can see a shaft here. So in this example, you can see this is a shaft. So in this shaft, there is an envelope. So in this shaft, this is an envelope. This is an envelope. Now this envelope expands. So now this will expand in this side and this side. So when this envelope will expand, it will touches the low points of the shaft from inside the shaft. So this envelope is inside the shaft. This envelope is inside the shaft. That's why we called it imaginary envelope. Now this envelope will expand. This expand in such a way that it touches the low points of the shaft. So you can see now after expanding, it is touching this point and this point. So these are the low points of the shaft. So this is the envelope which is the maximum one. So this is the maximum envelope which can enter into the shaft. It touches the extremities of the shaft at lower ends. So this is the extremities points which is touching the lower points of the envelope. So this envelope is called the actual minimum material envelope. So this envelope is known as actual minimum material envelope. Minimum material envelope. Okay. This actual minimum material envelope is also of two types. First one is unrelated actual minimum material envelope, and the second one is related actual minimum material envelope. In the previous session, we have already discussed this point that what are the difference between the unrelated actual meeting envelope and related actual meeting envelope. So it is moreover same concept, but it is inside the material. Those concepts for the outside the material, which are creating actual envelopes for taking the size, feature of size, but in this concept, they are imaginary one. Now, in the unrelated actual meeting envelope, you can see this is unrelated example of a shaft. So it is also similar perfect feature counterpart contracted. So these are the this is envelope. So let's say this is envelope. This is closed from here. This is an envelope. Now this feature counterpart when contracted towards contracted about an internal feature or expanded to within an external feature. So now this will expand. This will expand in such a way that it will touches the low points and not constraint, and the external feature, in this external feature, this will not be constrained with the reference datum. So it is not going to be referenced with the datum for unrelated one. So for expanded, it will expand within an within the shaft and not constrained to any datum reference. And not constrained to any datum reference. Constrained to any datum reference. So now you can see after expanding this, it touches the low points of the shaft. So this is the maximum size envelope which can be imagined enter into the shaft. So this is the actual, sorry, not actual meeting envelope. It is unrelated actual minimum material envelope. So I will write down here actual minimum material envelope. Material envelope. Now we will understand. So now we are going to discuss, we have discussed for the shaft. Now we are going to discuss for the hole. So in this example, this is the external feature, and this is the internal feature. So in internal feature, you can see these are the envelope lines. So if we want to create an envelope and which touches the low points of the hole, so this will be contracted. These lines will be contracted towards the hole. So this line will be contracted towards the hole. This line will be contracted. After contracting these lines, so now you can see after contracting these lines will start touching the low points here, and these are the low points of the hole. So this is envelope not taking, this envelope is also not taking any reference of the datum. So this, in this also actual minimum, sorry, this is minimum material envelope. Minimum material envelope. So this envelope, hence this envelope is not taking the reference of the datum. So not taking reference of data. So this is, we are discussing the unrelated actual minimum material envelope for the internal feature, and this is touches the low points of the hole or the feature. So hence this is also called the unrelated minimum material envelope for the internal feature of size. Now we are going to discuss the related actual minimum material envelope. So actual minimum material envelope. What is related actual minimum material envelope? It is an envelope similar perfect feature counterpart about an internal feature or expanded with an external feature. So it will expand for the internal feature while constrained in orientation. So now you can see when it will constrain to an orientation. Orientation we are discussing for the this. So it is having the orientation location in location or both the applicable datums. So this envelope is using datum as a reference. So in this case, envelope is using reference datum as a reference. So now in this example, I have already told you we have an external feature of size, and the we are also going to discuss about the whole for internal feature. So for external feature, we have imaginary envelope. So this envelope is an imaginary envelope. Imaginary envelope which expands and touches the low points of the external feature from inside. At the same time, it is taking the orientation of datum reference. So this is the example of the related actual minimum material envelope for the external feature. Now we are going to discuss for the internal feature. So similarly, we have internal feature for which this is an imaginary surface. So these are imaginary envelope. These both are imaginary envelope because they are inside the material. Inside the material. Inside the material. For which they are imaginary envelope which contracts, they will contract. So they will move towards the hole and touches the low points of the hole. Again, this envelope, in this case, you can see now they are touching the low points of the hole. So you can see these low points. Again, this envelope is also taking as a datum as a reference of orientation, as also maintains and hence this is the example of the related actual minimum material envelope. So this is all for today's session. If you have any doubts, please discuss with us. Thank you. Thanks a lot. Hello everyone, this is Manish from Skillable India, and in today we are going to learn the very important topic in geometric dimensioning and tolerancing, which is the material condition modifiers. So geometric tolerances can be applied to a feature or a feature of size with the help of material condition modifiers. So I'm going to explain you that what a material condition modifier is and what are the different types of material conditions in today's session. So modifiers can be, you can see that modifier can be used in the geometric dimensioning and tolerancing in accordance with the ASME Y 14.5 2018 standard, which is the latest standard we are going to learn. So what material condition is? First of all, I will tell you with the help of definition. So material condition modifier is a symbol placed on a feature of size that states how much tolerance is available for that feature. A positional tolerance defines both the zone within which the center axis or center plane of a feature is of size is permitted to vary from a true position or a boundary located at the true position that may not be violated by the surface or surface of considered feature. Now, the regardless of feature of size means control placed on a feature of size stating that the geometric tolerance must be met regardless of the where the feature lies within the size tolerance. So it means that the regardless of feature of size does not dependent on the feature of size. It is directly related to the feature. Now, if in a simple terms we understand this, so what does this material condition is? Whenever we apply the tolerance to a feature of size. So here 70 plus minus 0.5 mm we are considering the feature of size over here. So whenever we apply tolerance to a feature of size dimension of a regular feature of size, it will establish high limit and low limit. So this high limit and low limits are these limits are called the material condition. So here these limits are called material conditions. Now, when the tolerance is applied to a size dimension of a regular feature of size, it establishes high and low limit. So here the high limit of this part is 70.5 and the low limit is 69.5. So these limits are basically called the material conditions. It is a very simple topic. First of all, I will let you know that what you can see that the regular feature of size dimension and the high limit and low limit. So now one by one we will understand. So these are the three types of material conditions we have. First one is maximum material condition, which is MMC. Second one is least material condition, which is LMC. And the third one is regardless of feature of size. Now one by one we will understand that what these material conditions are and how we have to apply. In the next part of this session, I will tell you that when you have to apply the MMC, LMC or the RFS. First, we will understand in detailed manner that what MMC means. So first of all, we will understand that what the material condition, maximum material condition means, or MMC. So MMC or maximum material condition is defined as the condition of a feature. Feature can be any, it can be surface, it can be a hole. So we are talking about that maximum material condition is defined as the condition of a feature which contains the maximum amount of material. This line is very important, that whenever the material is having a maximum amount of material within the dimensional tolerance, it means that it is having a maximum material condition. Means I will let you know when you have a feature that geometric dimensioning and tolerancing is called on. Now for two parts, for internal feature and for external feature. Internal feature is a hole because it is inside the material. So hole is considered to be the internal feature, and the shaft or the shaft is considered to be the external feature. So with the help of example, we will understand that what material condition is. So if it is a hole for internal feature, MMC maximum material condition will be the smallest hole size. If the hole will be small, if there is a block and inside that block there is one hole, if that hole is small, then it is having more material, then the part is having more material inside it. So this is called the maximum material condition. If the part is having more material, means hole is small. In the case of shaft or a pin, pin is the external part. If pin or a shaft will have the larger diameter, so if the part is having a larger diameter external feature, it is having more material. Its weight is more. If we will take a weight of that part, it will be more. So this is the maximum material condition. If the part is having maximum material inside it, so then it is considered to be the maximum material condition. Now with the help of its symbol of MMC is M within the circle. Is in simple words, if we say that maximum material condition is add material to a part. We are adding material to a part within the limit of size. Now in this two examples are there. So whatever I have told you, this is a hole, this is a part, this is a part, and this part is having two holes. These hole number 1 and hole number 2. When this part is having a smaller hole, means this part is having maximum material inside it. If the diameter of this hole is smaller, I will write it down over here. If the diameter of hole is smaller, means that this rectangular block, the part is having more material more material inside it. Material inside. And having maximum weight and having more weight. So whenever this condition is there, similarly for the external feature of size, this is for the shaft. In this case, a smaller size of the hole is giving more material to the part. But for external feature, it's more diameter. If the shaft diameter is more, more. Let's say here 50. Here you can say for the hole, if we see, so 49.5. Here the diameter is 50 plus minus 0.5. So the upper limit is 50.5 and lower limit is 49.5. So here the maximum material condition is to be considered the lower limit for the hole. But in case of shaft, it is also 50.5 and 49.5 in this case. In this case, for the external feature, let's say this is the external feature inside. This is the part. This is whole part is there. This part, if the size of the shaft is more, then it is having more material. So in this case, 50.5, the size of this diameter, if the 50.5 is this, so this is the MMC. In case of hole, 49.5 is considered to be the MMC, but because it is having more material when the size of the hole is smaller. In this case, in the case of shaft, in the case of external part, so the more size will be the MMC, 50.5 will be the MMC. Now, if I see that 120 plus minus 0.5, so what will be the maximum material condition for this? This is the external feature. This is the external feature. So these two size, these are the external feature. So 120 plus 5 will be the maximum material condition. Similarly, for 300 plus minus 5, what will be the maximum material condition? This is also the external feature. So 300 plus 0.5 is the maximum material condition for this part. Similarly, if we see for the hole, so it will be the lower limit, because in this case, if 300.5 will be there, because it is having more material, because the length of the part will be increased by 0.5 mm. In this case, width wise 120.5, so 120.5 will increase the limit, and in this case 119.5 will reduce the weight. 120.5 will increase the weight. So whenever more weight is there, it is the maximum material condition. Whenever there is a less weight, so now in the next part we will understand the least material condition, when the part is having less material inside it. Now this is the maximum material condition. So I hope that this topic is clear. What is maximum material condition? In simple words, maximum material condition when the part is having more material inside it. For hole, it's a lower limit, and for the shaft, it's the upper limit. It is as simple as that. Now we will understand the least material condition. What the least material condition means, or LMC. Least material condition, LMC, is the size of a feature of size for part which contains the minimum amount of material or the least amount of material. When the part is having least amount of material, it is considered to be the LMC, least material condition. When you have a feature that geometric dimensioning and tolerancing is called off. So now also, as we have understood the MMC with the help of two examples, a hole and shaft, least material condition also we will understand with the same two examples, hole and a shaft, for internal feature of size and the for external feature of size. Its symbol is L within the circle. Sorry, this is LMC. So for LMC, the symbol is L. For hole, internal feature of size, LMC. Here, sorry, we are talking about LMC. So LMC is the largest hole size. In this, you can see that LMC will be the largest hole size. If the hole size is bigger inside the part, means it is having less material. So this is the least material condition. If the shaft diameter is smaller, means that the shaft is having less weight, means it is having the least material condition. So with the help of example, we will understand. For external feature, for pin shaft, a small size of the pin is considered to be the LMC. This is called LMC. Largest hole size, smallest size of the pin or shaft is considered to be the LMC. Now in the example we will understand. So in this you can see what will be the least material condition for this hole. If this hole is bigger, means this part 1, when the hole size is bigger, the part weight will be less. So overall, when the part weight will be less, so this will be the LMC will be diameter 50.5. So 50.5 will be the LMC, least material condition. If similarly, if for external feature, this is a shaft, and if this shaft will be smaller, in this there are two conditions, 50.5 and 49.5. If this shaft will be 49.5, means a smaller shaft will be there, means it is a least material condition, it is having less weight. Whenever the part is having less weight, it is considered to be the least material condition. So in this case, LMC will be 49.5. So this diameter is less, so it means it is LMC. Now similarly, if we see for the width, this is the external feature. If this part width will be smaller, it means it is having less weight. So in this condition, 299.5 is considered to be the LMC. In this case, 120 plus minus 5, 119.5 is considered to be the LMC. So for external feature of size, it is now reverse from the MMC. So now I think the concept is clear for the maximum material condition and the minimum material condition. For maximum material condition, the part is having more weight inside it. For hole, if it will be smaller, then the weight will be more of the part, then it is maximum material condition. If the shaft will be bigger, means it is having more weight, means it is having maximum material condition. For least material condition, if the hole size is bigger, means it is having less weight. The part is having less weight. So it is the least material condition. For similarly shaft is having smaller size, means it is having less weight, it is least material condition. So now I think the concept is clear of the maximum material condition and the least material condition. Now we will understand the third part of this session, which is regardless of feature of size. Now what does this regardless of feature of size means? 1 second. Regardless of feature of size is the default condition. So first of all, regardless of feature of size is a default condition. Whenever we don't apply the maximum material condition or the least material condition, then the RFS is a default condition. RFS applies automatically of all the geometric tolerances by rule 2. So rule 2 says this, that the RFS applies RFS is a default condition. Whenever we don't apply the MMC or LMC, RFS applies automatically. Now, and this RFS requires no call out. Previously, we used the symbol S within the circle, but now in 2009-18 standards of ESME by 14.5, we don't have to use any symbol. This is a default condition, so no symbol is required for the RFS right now. So regardless of feature of size simply means that whatever GD&T call out you make is controlled independently of the size or dimension of the part. One thing is very, very important. Maximum material condition and minimum material condition can only be applied to a feature of size. Maximum material condition and minimum material condition cannot be applied on the feature. We have to apply onto the feature of size only. So in this case, you will see that the geometric tolerance of a feature needs to be independent of the feature of size. So in this case, it is independent of the feature of size, and previously it is a default condition. I have already told you which does not have any symbol. So we take an example over here of this rectangular block. So 70.2 and 69.8. We have two limits over here. So here you have a regular feature of size. So this is a regular feature of size. This is the example of a regular feature of size. I have already told you that whatever you can measure with the help of vernier caliper, it is considered to be the regular feature of size. So if you forget, so I am again repeating this sentence, that whatever you can measure with the help of a caliper or other tools, with the help of tools, that is considered to be the regular feature of size. So this is the example of a regular feature of size, and with the for which with the limits of which the geometric tolerance are applied. In this, you can see the geometric tolerance are applied. Flatness with the 0.2 mm remains constant for any size of the part within the limit of size. So for any 70.2 also the 0.2 is applied. For 69.8 also the 0.2 is applied. So in this case we don't get any bonus tolerances in the RFS. So this is called the regardless of feature of size. So this is all about the material condition modifiers. In the next video, I am going to tell you about the how to use RFS, MMC or LMC into our engineering drawings. So thank you. Thanks a lot. Hello everyone, this is Manish from Skillable India, and we are into the continuation of our course of geometric dimensioning and tolerancing. In today's session, we are going to learn the most important topic what we have already started this about the material condition modifiers. So in this, we are going to understand about the when to apply MMC, maximum material condition, when to apply LMC, least material condition, and when the RFS is a default condition. And when we are applying RFS, so what are the tolerances we get, tighter tolerances we get when we apply the RFS. So in this session, we are going to understand all the concepts of these material condition modifiers with the examples. So first of all, we are going to start with the regardless of feature of size. So first of all, regardless of feature of size with internal feature. So whenever I am talking about internal feature, I am talking about whole. So in this example, as you can see, when we apply regardless of feature of size, when a geometric tolerance is applied on an RFS basis, whenever we apply the geometric tolerance in the feature control frame in any engineering drawing on RFS basis, RFS is a default condition. So RFS basis, the specified tolerance is independent of the actual size of the considered feature. So in this, the specified tolerance is independent of the feature actual size, or we can say the considered feature of feature. So the tolerance is limited to the specified value regardless of the actual size of the feature. Likewise, referencing a datum feature or on an RFS basis means that a centering point about its axis or center plane is necessary. So regardless of the actual size of the feature. So in this, regardless of feature of size, in this particular example, you can see that we have the tolerance apply for 15 mm plus minus 1 mm. So in this, this is the tolerance we have provided, and 1 mm of the geometric tolerance is applied. So whatever, let's say here 3 conditions are there. What is the maximum material condition of this hole? Maximum material condition of this hole will be the smallest hole size, which is dia 14 mm. And the least material condition of this hole will be the dia 16 mm. You will see this. So whenever we have the part produced at MMC at dia 14 mm of this hole. So in this example, we have updated the positional tolerance at a regular feature of size. You have already seen. For the internal feature of size, we are considering. So we have different combinations over here. So you can see we have different combinations over here. One is when the part is produced, hole is produced at 14 mm, which is maximum material condition. So this is the maximum material condition when the part is produced at 14 mm. For this, we have the positional tolerance is of 1 mm. So when the part is produced at MMC, the tolerance is of 1 mm. When the hole is produced at 15 mm, the positional tolerance is still 1 mm. 1 mm only. When the hole is produced at the least material condition, which is LMC, still we have the positional tolerance of 1 mm only. So on RFS basis, whenever we are talking about RFS, whatever be the hole size, the tolerance value will be the same. So you can see that in this collective effect, so all the tolerances we are getting 14, 15, and 16 all diameter. Only we get the 1 positional tolerance, and the datum shift with what we are getting, the whole shift over here is of 0.1 mm. Here you can see 30 mm. So only 0.5 mm shift is seen over here on one side. So whatever be the size of the hole within the limit of size, the positional tolerance of 1 mm remains same, and we end up with the max. In this, you can see the maximum shift from the true position. You can see from the true position the maximum shift from on one side by 0.5 mm only. So whenever we calculate the inner boundary, this red portion is the inner boundary. So whenever we calculate the inner boundary, here you can see inner boundary is the maximum material condition minus geometric tolerance value. So you can see the maximum material condition over here is dia 14 mm minus 1 mm. So dia 13 is the inner boundary. So here we get the dia 13 mm as the inner boundary. You can see over here. So this is also the virtual condition. So this is the virtual condition. Actually, virtual condition is the worst case boundary that is possible for this part. So we will understand this concept in a later stage, but till now, what is virtual condition? Virtual condition is the worst case boundary what is possible for the part to for the mating part, for this part. So if you will see this part produced at I will say 14 mm or 15 mm over here diameter, we have a lot of clearance. So you can see that there is a lot of clearance over here at this position. But the thing is, but we cannot use this clearance. Why we cannot use this clearance? So whenever we get the regardless of feature of size, whenever we use the RFS, the tolerance are tighter. So whenever we use RFS, tolerance is tighter. Tolerance are tighter, and through there is a clearance, but it is not allowed to shift further from its true position. So it is not allowed to shift from its position because we have considered this regardless of feature of size. We haven't used any MMC or LMC over here. So always when we use RFS, when there is a tighter tolerance requirement, for example, in most of the cases when we use RFS to create a mold of, or we create a jigs and fixtures, machine tools when we create, so we use this RFS, and other machining applications to go with the regardless of feature of size only when there is a requirement of the tighter tolerances. So we considered RFS whenever we require the tighter tolerances. So inner boundary, I have already told you, maximum material condition minus geometric tolerance value. So this is the inner boundary, which is equal to the virtual condition also. Now the next one is maximum material condition. When we apply the maximum material condition, we have understood about the RFS, that when we apply the RFS, now we will understand about the maximum material condition. Maximum material condition, I have already told you, symbol is M within the circle. Maximum material condition defines the worst case condition of the part that will still guarantee because it is still within the prescribed tolerance. So whenever we use MMC, maximum material condition, we get still we get the extra tolerance or the bonus tolerance. How we get this bonus tolerance, we will be discussing with this. So the assembly between the pin and hole, whenever there are two mating parts, one is pin and other is hole. So to enter in a correct way in this, the pin should be entered in a hole. So when a hole is at the smallest MMC and pin is at its largest condition or also MMC. So whenever hole is at MMC means smallest hole size and pin is at MMC means the largest size of the pin. So you can see whenever we use the MMC for both the condition for hole and the shaft, so it is very difficult to mate both the parts. So we can be sure that we will still be able to assemble that part. So in this condition, we can be sure that we will be able to assemble these both the part. Pin is going to be assembled with the hole. So thus MMC is widely used in cases where clearance fits are common. So this is we use where the clearance fits are commonly used. Now we take an example for the maximum material condition where for the internal feature of size. So now let us have a look of applying maximum material condition for the internal feature of size. So here we added a symbol of MMC. So in this feature control frame, you can see in this feature control frame, I am making this feature control frame over here for the position, dia 1 mm tolerance, geometric tolerance, maximum material condition, primary datum, secondary datum, and tertiary datum. So the maximum material condition for the hole is over here. For the hole is 14 mm. 14 mm is the MMC, 15 mm and 16 mm is the least material condition LMC for this hole, because we have 15 plus minus 1. Now in the example, so you can see in this example that when we have the so in this you can see when the hole is produced at MMC, which is 14 mm, this is the MMC, the positional tolerance available is 1 mm, dia 1 mm. When the hole is produced at 15 mm, the positional tolerance available here is 2 mm. When the hole is produced at least material condition 16 mm, the positional tolerance is of 3 mm. And when 3 mm. So here when we give the maximum material condition as when we give the maximum material condition and we move from maximum material condition towards the least material condition, we get more tolerance. So when the hole is produced at dia 16 mm, which is LMC, we have positional tolerance available is of 3 mm, because we get the bonus tolerances adding up in this. So now you can see, and then the positional tolerance value always increases. So in this case, the positional tolerance value is increasing. So here we have the collective effect. You can see over here. So for each size of the hole, the positional shift from the true center. So this is the true center, and from this center you can see that 0.5 mm it is shifting from the true center in advance. So on one side, so for this, if we calculate the virtual condition, so what will be the virtual condition over here? Virtual condition is equal to the worst case boundary. Worst case boundary will be the inner boundary in this case for the maximum material condition. So inner boundary is equal to the maximum material condition minus the geometric tolerance value. So maximum material condition here is 14 mm and the geometric tolerance value is 1. So here we get the dia 13. So this is what we get over here, the virtual condition. So virtual condition over here is inner boundary, which is the dia 13 mm. So this red condition. Virtual condition is basically a condition which is the worst case condition when the pin is entered into the hole. I have already discussed this thing. So when we are learning about the virtual condition and the resultant condition, you will get more clear view of this concept. So virtual condition is nothing but the inner boundary over here in this case, which is equals to the maximum material condition minus the geometric tolerance value. We get the value over here is 13 mm, and any hole produced within the limit of size will enter into the virtual condition. And then we have the lot of flexibility in manufacturing. You can see that we have the lot of clearance over here, and in manufacturing we get ensure that it should be assembled with the other mating part. So if your application is that you have to ensure that your part is to be assembled only and have flexibility in manufacturing, when there are millions and millions of parts are produced and they need to be assembled with one another, at that time we use this maximum material condition a lot. So in this case, you will see most of the automotive components, automotive parts are there, what we produce are with the maximum material condition MMC. So finally, as I have said earlier only, virtual condition is equal to the inner boundary, which is maximum material condition minus geometric tolerance value. Now we will understand the next thing, which is the least material condition. Least material condition or LMC, when we apply, this is the symbol L within the circle. When the least material condition modifier is used, it indicates that the specified tolerance applies when the feature of size is at the LMC size. As the size of the feature of size departs from LMC size, the tolerance is increased by the amount that the size departs from the LMC size. We take the same example over here. We have the hole, which is the size having 15 plus minus 1 mm. In this case, dia 14 will be the MMC, maximum material condition, and dia 16 will be the least material condition. Now it is saying that when the part is produced at 16 mm, we have the tolerance of, in this feature control frame, first is position, dia 1, least material condition modifier, primary datum, secondary datum, and tertiary datum. So it is saying that when the part is produced at 16 dia, we have positional tolerance of 0.1 mm. Now, when the 0.1 mm. So if we move from least material condition towards the maximum material condition, so we get in this further. So in this example, you can see now the part we are talking about LMC, and we are moving from LMC towards MMC. So at 16 dia, we have the positional tolerance of 1 mm. At 15 dia, we have a positional tolerance of 2 mm. At maximum material condition, which is 14 mm, we have the maximum positional tolerance, which is 3 mm. So in the cumulative effect, you can see in this example, we get shift from 0.5 mm. So collective effect is shown over here, where we calculate the virtual condition. So here the virtual condition is the outer boundary. So why we are talking about the outer boundary in this case, not the inner boundary? So the outer boundary is equal to the least material condition plus the geometric tolerance value. So the bigger the hole, least material condition means size of the hole is bigger. So in this case, dia 16 mm plus geometric tolerance value, which is 1 mm. So 17 mm will be the outer boundary. So virtual condition is the 17 mm. So here circle is virtual condition. So if you see all the holes are within the black, in this black circle. Okay. So here, So here you can see this outer boundary. All the circles are in the outer boundary. So so all these three sizes are within the outer boundary, which is the 16 mm plus 1 mm. So we get the outer boundary, which is the virtual condition. So this is the worst case condition that what we get over here, which are produced are within the black circle, and it is touching over the edge. So the worst thing that can happen by this, we can always ensure a minimum wall thickness for the part. So whenever we use the LMC, we ensure that we get the minimum wall thickness. When we require the minimum wall thickness from the part. So basically this is the distance. This is called the minimum wall thickness of the part. So if you see, the wall thickness is not changing throughout the whole size. So this distance is not changing. You can see in this part that we are shifting, but still this distance where the minimum wall thickness is not changing. So whenever you have required of the minimum wall thickness application, when we require these application in all such cases, we can go with the least material condition. So most of the cases where the material thickness is important, where the weight of the material is important, like in aerospace, aeronautical applications, in aerospace applications. So at that time where the material thickness is the important case, at that time we use this minimum wall thickness, which is LMC, least material condition. So where the weight of the material is very, very important, and we use the least material condition in that case, where the virtual condition is equal to the outer boundary, which is the least material condition plus geometric tolerance value. Whenever we, now the most important part here is maximum material condition and least material condition. MMC or LMC condition is applied when the geometric tolerance is applied to a feature of size only. So MMC condition and LMC condition is only applied to a feature of size, FOS. And we cannot apply MMC or LMC to a feature. So only we can apply to this to the feature of the size. Now, geometric tolerance applied to a feature of size. So there are some of the examples: straightness, flatness, angularity, perpendicularity, parallelism, and position. So only these are the conditions where we can apply the maximum material condition and the least material condition. Now, MMC, maximum material condition, and the least material condition is applied when the geometric tolerance is applied to a feature of size only. To a feature. In this case, if I am talking about only feature, you can see geometric tolerance applied to a feature. So whenever we are applying these geometric tolerances to a feature, to only a feature, not a feature of size, so MMC and LMC we cannot apply. In this condition, we cannot apply maximum material condition and the least material condition. Whenever geometric tolerances GD&T is applied to a feature, in that case we cannot apply MMC or LMC. Only the case when the geometric tolerance is applied to a feature of size, then only we can apply maximum material condition and the least material condition. So in this, feature of size is the very important thing. So thank you all of you. In the next discussion, we will be further discussing about the next topic in GD&T. Thank you everyone.
Hello everyone, this is Manish from Skillable India. In today's session, we are going to learn the very important topic, which is the rule number 1. So we all know that games cannot be played without rules. So it is true also into GD&T. So that's why we are going to understand the 2 rules. First of all, in this particular session, we are going to understand the rule number 1. Actually, this rule number 1 is a very big topic. So I have converted this rule number 1 into 2 parts. So into the first part, so I'm going to tell you a very important rule, which is into the geometric dimensioning and tolerancing, which is called rule number 1. So in this rule 1, it is the also called at perfect form at MMC. So one by one, I will in the further this session, I will tell you that why it is called perfect form at MMC, why it is called envelope principle, and again why it is called individual feature of size rule. So this rule number 1 has 3 names. First of all, if we move forward, so I will write it down 3 names over here. So this rule is called perfect form at MMC. Perfect form. Form is also called the shape. Do not get confused. So perfect form at MMC. Secondly, this rule is called the envelope principle. Thirdly, this is called the individual feature of size rule. Individual feature of size rule. So one by one, we are going to discuss that why we are understanding this. So first of all, if we understand with the help of definition, so rule number 1 of the geometric dimensioning and tolerancing states that the form of a regular feature of size. So we are talking over here is about the regular feature of size. I have already told you about the regular feature of size, irregular feature of size. Irregular feature of size is of 2 type A, type B. So we have already discussed these things, but briefly I am going to tell you. Regular feature of size is the feature of size which we can measure with the help of vernier caliper. So it states that the form of a regular feature of size is controlled by its limit of size. So limit of size over here, you can see over here is dia 10 plus minus 12. So limit of size is the dimension. So limit of size, or otherwise known as the size tolerance. So this plus minus 2 or 10 plus minus 2 is called the size tolerance. Can be seen in many forms. A few of them are symmetric, unilateral and bilateral. It is sometimes also known as the Taylor's principle. So this size tolerance can be symmetric, this can be unilateral, this can be bilateral. It is sometimes also known as the Taylor's principle. Okay. So this is all about the rule number 1 definition. So the second one is the actual surface of a regular feature cannot extend beyond the envelope prescribed by the feature of size in the perfect form at MMC. So this particular I will tell you with the help of example that by the actual surface is this surface. This surface cannot extend beyond the envelope prescribed. Envelope, we are going to tell you, I'm going to tell you what is envelope over here. So why we are learning this rule 1, we need to ensure that the shaft should enter into the hole. So the part shaft or the pin is going to be entered into the hole. So what that's why we are understanding this rule 1 in detailed manner. So envelope is basically the maximum material condition of the shaft. In this case, you can see we are taking an example of shaft. So we are taking an example of a shaft. So the maximum material condition over size of this size. So MMC and LMC. So MMC of this shaft is 12 dia 12 mm and LMC is dia 8 mm. So with this example, I will tell you that how this cannot extend beyond the prescribed feature in the perfect format MMC. This means that if the feature measures at MMC, let's say if we are measuring this pipe part and manufacture this part at MMC, let's say this shaft is manufactured at dia 12 mm. So that it must be perfect in shape. So this shape should be perfect. If this is not perfect at MMC, at maximum material condition, then it will not enter into the envelope. So the perfect form of the feature must be perfect, which is into the real world. If we talk about with the manufacturing process, it is very, very difficult or it is almost impossible to manufacture the exact shape or at the perfect format MMC. Let's say in this case is 12 mm. So we want some deviation. That's why we provide the tolerances to the part, because if we are strict to the size of the part and the form, and we do not want any form error in the part, so the cost of the part will be very, very high. So to reduce the cost of the part also in the manufacturing of the part, we provide the tolerances. We give some tolerance to that part that it should get assembled with the mating part. So let's move further. So this is the drawing. Let's say with the help of examples, we will understand this. First of all, this is the drawing we give to the manufacturer. This drawing of the shaft we have provided to the manufacturer. So what are the conditions that manufacturer will manufacture the part? So condition number 1. So this is the condition number 1. This is the condition number 2. This is the condition number 3. And this is the condition number 4. Any of these conditions, this part can be manufactured, and there are multiple conditions also. We are taking only 4 conditions over here. The manufacturer can manufacture the part. A person who is a machinist will manufacture this part in many ways. So these 4 conditions I am taking here. So one by one we will understand that what are the different conditions in this. So to understand this rule better, we will understand with the envelope. So we have a regular feature of size with the limit of size. So you can see in this example only, we have a regular feature of size with the limit of size. So dia 10 plus minus 2 mm is the regular feature of size with the limit of size. Okay. So after manufacturing, let's say this is the condition number 1. This is the case 1. This is the case 1 of this part. So I have already told you about the limit of size. So the rule tells that when only limit of size is given onto the drawing. So this rule tells that when only the limit of size is given onto the drawing, the limit of size not only controls the size of the part. So this limit of size not only controls the size of the part, but also controls the geometric form or shape of this part at some extent. So this limit of size is controlling size of the part and geometric form of this part at some extent. So let's go in detail. So after manufacturing, I have already told you. So after manufacturing this part, we can manufacture this part in many ways. So this part should enter into the first. We have to fulfill some conditions. So there are some requirements that needs to be fulfilled to obey rule number 1. First condition, first requirement is that if we measure this part at this point, so wherever we measure this part, if we measure this part, the actual local size So actual local size. So we are talking about actual local size. So the actual local size should not be more than 12 mm and not less than not more than 12 mm and not less than 8 mm. So in this case, the actual local size you can see is 10 mm. So here it is 10 mm, here it is 10 mm, all the way it is 10 mm. So the actual local size within the size tolerance. So from 8 mm to 12 mm, this size should be there because this is the MMC and this is the LMC of this shaft. So the actual local size should not less than 8 mm and more than 12 mm. Second condition is, so this is the first condition. Second condition is this part should enter into the envelope. So this is the envelope. This part should enter into the envelope of maximum material condition. So the maximum material condition of the shaft is 12 mm. So the maximum material condition of the shaft is 12 mm. So we have created an envelope of 12 mm. So this rule is saying, this second condition, that the part should enter into the envelope of maximum material condition. So this part is entering into the envelope because this size is 10 mm and this variation we are having over here is 2 mm. Okay. So that's why this part is entering into the envelope. Okay. So this part should enter into the envelope of maximum material condition, which is dia 12 mm in this case. So this part is entering into the envelope, means this part is fulfilling the second condition also. So means this part is obeying rule number 1. This part is obeying rule 1. Now we will see the second example. So in this example also you can see that the actual local size, first condition is actual local size is within the size tolerance. So maximum we have 12 and the minimum we have 10 mm. So it is varying within the range. So from 8 to 10, from least material to maximum material condition, it is varying. So this condition fulfills the first condition, that the actual local size is within the limits. The second part is it should enter into the envelope. So this part is also entering into the envelope. So the second condition is also fulfilled. So you can see that this part is also, this is the second manufactured part. So this part is also obeying rule number 1. Now we will see the third example. In this first condition is actual local size is within the size tolerance. So let's say this is 8 mm, here it is 10 mm, here it is 12 mm, and again here it is 8 mm. So means the actual local size is within the limit of size. First of all, first condition is satisfied. The second condition is it should enter into the envelope. This part is entering into the envelope because the size is 12 mm over here and this part maximum size is 12 mm over here. Maximum we have 12 mm of dia. So this part is entering into the envelope. So this obeys rule number 1. Now this is the fourth example, fourth condition. So first of all, the actual local size of the part is within the size tolerance, which is 10 mm all over this part. So the rule number condition 1 is satisfied. Condition 2 is it is entering into the envelope. Yes, it is entering into the envelope. So the second condition is also satisfied. So this part is also obeys rule number 1. Now in this example, after manufacturing the part, the actual local size of this part is 12 mm. Let's say here dia 12, here it is dia 12, here it is dia 12. So the first condition is satisfied. The actual local size is within the limit of size, but it is not entering into the envelope because it is having the bow shape like this shape. So in this, it is not entering into the envelope. So it is not obeying rule number 1. So this part is not obeying rule 1 because it is not entering into the envelope. The maximum size we have over here is 12 mm, but it is having a bow shape and the actual local size is of 12 mm, means this size, the size over here from here is more than 12 mm. So this size is more than 12 mm, so it is not able to enter into the envelope. So in this case, it is not entering into the envelope. So this doesn't obey rule number 1. Now, why this rule number 1 is called the perfect form at MMC. Now we will understand this thing in a very detailed manner. Why it is called perfect form at MMC. So let's say this part is produced at a local size of 12 mm. So the actual local size at every point is dia 12 mm. If this part needs to get into the envelope, if this part needs to go into this envelope, it should have the perfect form. So in this case, first condition is satisfied. Over here, you can see that the actual local size is between the size tolerance, which is dia 12. So the first condition is satisfied. It is well within the limit of size and enters into the maximum material condition envelope. So now it is entering into the envelope and it is entered into the envelope. This part is entered into the envelope. Now, so this part obeys rule 1. So this is also condition satisfied. So this obeys rule 1. But the thing is, perfect form. If the part is manufactured at maximum material condition, the form of this part, the shape of this part should be perfect. The form error is not acceptable. Form error at MMC is not acceptable for obeying rule 1. So if the form at MMC is perfect, so it obeys rule 1. So that's why we say that whenever the part is manufactured at maximum material condition, so it should have the perfect form, which is impossible to manufacture, or say it will increase the cost at very high if we need to assemble this part. So that's why we call this part at perfect form at MMC. So this is why we say perfect form at MMC. Now, one by one, I will tell you what are the requirements. So in detail, we will understand to fulfill the requirements of rule number 1. One by one, we will understand. So rule number 1 is a dimensioning rule that ensures that the individual regular feature of size will assemble with one another. So why we are learning this rule number 1? Because we need to assemble the mating parts, the hole and the shaft with one another. So what needs to be taken as a mind, as a designer, as a design engineer, what are the things you have to keep in your mind that are important to obey the rule number 1? When rule number 1 applies to a regular feature of size, which is the very important thing, rule number 1 is only applied to a regular feature of size. It establishes an overall boundary or the envelope. So whenever it is manufactured at regular feature of size, so this forms the boundary or the envelope or for a regular feature of size that is equal to its MMC. So in this case, 10 plus minus 2. So the MMC, maximum material condition of the shaft, is dia 12 and the least material condition is dia 8. I have taken very wide tolerances just to understand you clear. So maximum material condition, let's say, so this envelope will be at the maximum material condition. So this envelope will be the maximum material condition. Now, rule number 1 applies to an external regular feature of size. External means we are talking about shaft. External regular feature of size. The maximum material condition boundary, maximum boundary or the envelope of a regular feature of size is equal to its largest size. Largest size for the shaft is 12 mm. So we are for shaft, for the example of shaft we are taking. So the maximum material condition of the shaft is 12 mm over here. Sorry. I will make it over here. So if we are talking about shaft, so dia 10 plus minus 2. This is the limit of size we are given here. So the maximum material condition will be dia 12 mm. So it is saying that to its largest size, limit size, MMC. So in this largest is to dia 12. LMC over here is dia 8 mm. So we are taking 12 mm, the maximum material condition for this envelope. When rule number applies to an internal regular feature of size, here we are talking about hole. So whenever we are talking about hole, so we will make one drawing of hole. Let's say this is having dia 10 plus minus 2 in this case also. So what will be the maximum material condition of hole is dia 8 mm and least material condition of the hole will be 12 mm. It is opposite to the shaft because in this case this part is having maximum material condition at MMC. When the hole is smaller, the part is having maximum material. When the shaft is bigger, it is having the maximum material. So maximum material condition is when the part is having maximum material, more amount of material. When the part is having less amount of material, it is called the least material condition. If the shaft is smaller in its dia, means it is having less material. So it is the least material condition. When the hole is bigger, means the part is having less material. So it is the least material condition. So basically it is saying that MMC, whenever rule number 1 applies to an internal feature of size, which is hole, the minimum boundary or the envelope of the regular feature of size is equal to its smallest size MMC. So that's why we are saying 8 mm dia, taking 8 mm dia. To design two regular feature of size that will assemble, the designer can use their MMCs. Now, this is the very important point. The design, to design, if we are as a design engineer designing some part, let's say we are designing, I am taking an example. So in the first example, it's saying for first requirement of the regular feature of size is it only applies to a regular feature of size. So regular feature of size, I have again and again I'm saying regular feature of the size. Regular feature of size is the size which can measure with the help of vernier caliper. Now here we take one example. As a design engineer, if I'm a design engineer and this is the shaft, this shaft is having a dia of 10 plus minus 2. So the maximum material condition is dia 12 and the least material condition is dia 8. So if I need to assemble, this is the second part with hole. This shaft is going to be assembled in this hole. So this previous point is saying to design two regular feature of size that will assemble, the designer can use their MMCs. So let's say if I have taken dia, first of all, I'm taking the same dimensions, dia 10 plus minus 2. So for hole, what will be the MMC? Dia 8 mm will be the MMC and LMC will be the dia 12 mm. So it is saying that we can take MMC. So dia 8 mm of hole will never, this shaft of dia 12 mm will never enter into this hole. Because why it is not entering into the hole? Because the hole diameter is 8 mm and the shaft diameter is 12 mm. So to assemble these both the part, the shaft and the hole, what I have to do is I have to change the dimension. From 10, I will take 14 over here. So I will change the dimension. So if I need to, in all the cases, if I want to assemble the part with one another, so what will be the maximum material condition now of the hole? Will be dia 12 mm and least material condition will be dia 16 mm. So when both the parts are manufactured at maximum material condition, shaft is also manufactured at maximum material condition and the hole is also manufactured at maximum material condition, still they are going to be assembled with one another. So the shaft which is manufactured at maximum material condition and the hole which is manufactured with the maximum material condition are going to be assembled with one another. So as a design engineer, we have to take such tolerances that both as a design into the design that both the part at maximum material condition will assemble with one another. It is the this is the concept why we are learning all these things. So the first requirement is rule number 1 only applies to a regular feature of size. Second requirement, the actual local size of a regular feature of size at each cross section shall be within the specified size tolerance. It is saying that whatever the size tolerance, let's say dia from LMC, dia 8 mm to MMC, dia 12 mm, these all the sizes, all the cross section sizes be within this size. So at each cross section, it does not exceed the 8 mm and 12 mm. So it is within this size tolerance. Always at each cross section, the size of the actual local size of a regular feature of size will be well within the specified size tolerance. This is the second requirement of the rule number 1. Third requirement is when the actual local size of a regular feature of size departs from maximum material condition towards least material condition. Whenever the maximum material condition is here is 12 mm and least material condition is over here is 8 mm. When the part is departing from 12 mm towards 8 mm, maximum material condition towards least material condition, so it is allowed to have an equal amount of departure. Let's say this part is having actual local size of 10 mm. So the maximum departure it can have is of 2 mm. Then only it should enter into the envelope. If it is having maximum departure, let's say it is having 3 mm and actual local size is having 10 mm, it will not enter into the envelope. So this does not obeys the rule 1. Let's say this 10 mm size is 9 mm. So the maximum departure what we can have over here is 3 mm. So if we have this departure of 3 mm and this actual local size is of 9 mm, then it can enter into the envelope. So it obeys the rule 1. Obeys rule 1. Now, fourth requirement is here. There is no requirement for a perfect boundary at LMC. So whenever we are manufacturing the part with least material condition, let's say at each cross section the actual local size is at of 8 mm, which is the least material condition, which is equal to LMC. So the maximum variation, maximum form variation up to the MMC. So the maximum variation we can have over here is 4 mm. So dia 8 can have maximum variation of dia 4 mm. So this is very important, that the maximum variation we can have is up to the maximum material condition, which is 12 mm. So this is the maximum variation we can have at least material condition. Fifth requirement is when the part is produced of a regular feature of size at maximum material condition, it should have the perfect form. That's why I have previously also told you that why it is called the perfect form at MMC. When the part is produced at 12 mm, each actual local size of this part everywhere it is 12 mm, then this part should have the perfect form. It shouldn't have any error in the form. If the part have perfect form, then only it will enter into the envelope. If the part is not having the perfect form, it should not have the enter into the envelope. So that's why if the part produced of regular feature of size at maximum material condition, which is dia 12, then it should have the perfect form or shape. Then only it will enter into the envelope. So this is the fifth requirement. Now, one thing I will also discuss with you, that why this rule is also called the individual feature of size rule. Individual feature of size rule is rule number 1 is also called the individual feature of size rule. Why it is called individual feature of size rule is because it does not controls the location and the orientation of the feature of size. So in this is called individual feature of size because it does not control the location and orientation feature of size. So whenever it is manufactured at maximum material condition with the bow-like structure, so the axis of the part is not perpendicular to the face. So this rule number 1 is applied only to the diameter. So only to the diameter it is applied. That's why we are applying only to the regular feature of size, not to the overall length of the part. So not to the overall length of the part. So the length of the part is independent of the diameter. So that's why with the rule 1 does not it is individual feature of size rule and does not controls the location and the orientation. With orientation I am talking about the angular. It can be perpendicular or parallelism. It does not control that. So this is all about the rule number 1. So thank you everyone. In the next discussion of the rule number 1, we are going to discuss some how to override rule number 1 and all other things. So thank you everyone. See you in the next session. Hello everyone, this is Manish from Skillable India, and in this particular session of GD&T, Geometric Dimensioning and Tolerancing, this is the continuation video or the session of the rule number 1. So in rule number 1, we have already understand that what are the requirements to fulfill if we want to obey the rule number 1. So in this session, I am going to tell you that how you can override rule 1 and what are the exemptions in the rule 1 and how you can verify with the rule 1. So rule number 1, and you can see over here. So first we will know about the exemptions. So first of all, we rule number 1 does not apply to the non-rigid part. We call them, this is the exemption 1. So rule number 1 does not apply to non-rigid part. The non-rigid parts like O-rings, belts, gaskets, and other non-rigid parts that are flexible and do not maintain their nominal shape in the free state. So in the free state, if the part do not follow the do not maintain their nominal shape, like rubber, so these type of material which are made up of rubber, so they do not maintain their nominal shape, so they do not come under the rule 1. So they are exempts from the rule 1. Now the second thing which are exempted from rule 1 is it does not apply to the stock sizes. In the starting of this course, I have already told you what are stock sizes. So in stock sizes, there are sizes which are the standards which are governed by the government entity like BIS in India. Bureau of Indian Standard controls these sizes, these standard shapes. So in this, bar stocks is there, tubing is there, sheet metal sheets are there, structural shape like I section, C sections are there. So these in this example you can see that these structures, these shapes, structural shapes does not obey the rule 1 because they are exempts from the rule 1. So these are the two exemptions in which we don't follow the rule 1. Now we will understand how to override rule 1. So rule 1 automatically applies to all the individual feature of size. First of all, this line is very important that rule 1 is a default condition. So on each and every engineering drawing, so this is a default condition. So on each and every engineering drawing, it automatically applies to all individual regular feature of size. So again and again, I have already told you what is a regular feature of size, irregular feature of size. So this does applies to the regular feature of size onto the engineering drawing. In some application, producing a part with perfect form at MMC may not be required, and if given will increase the cost of manufacturing. So as we already know that rule 1 is also named as perfect form at MMC. So sometimes we do not require the perfect form of the part at MMC because it will increase the cost of the part. It will increase the manufacturing cost of the part if we will need the perfect form. So we should provide some tolerances to it. So first of all, one by one, we will understand this. So then it becomes essential to override rule 1. So this can be done in 3 ways. So the rule 1 can be override in 3 ways. One by one, we will understand. First one is applying straightness to the size dimension of a cylindrical regular feature of size. If we apply the straightness tolerance to a size dimension on a cylindrical regular feature of size, so we can apply override rule 1. We will know in detail this. In detailed manner, we will know this. Applying a flatness tolerance to a size dimension on a planar regular feature of size. Specifying independency symbol. So there is one independency symbol which is like this. Specifying independency symbol to a regular feature of size dimension. So these are the 3 ways to override rule 1. One by one we will understand this. So in this case you can see that applying straightness to the size dimension of a regular feature of size. In this you can see that this is size dimension and we have provided the geometric tolerance straightness with 0.5 mm of tolerance over here. So here the straightness tolerance is applied to the size dimension of a regular feature of size. So in this case, the axis of the part, this is the axis. You can see this axis. This is the dia. So in this case, the axis of the part is permitted to have the straightness variation when the size dimension is at MMC. When the size dimension is manufactured at MMC, we still have the straightness variation of 0.5 mm. So when the part is manufactured at a maximum material condition, which is 10.5, so each and every position, so this is here in this case 10.5 is the MMC condition. Let's in this case, if we provide this, in this case when we provide the straightness tolerance to the cylindrical part, to this cylindrical shaft, so when the part is manufactured at its maximum material condition or at MMC, at each and every point, this is dia 10.5. So when the part is manufactured, still in this case, we have the tolerance of 0.5 mm. So this size, this overall size can have the maximum variation of 0.5 mm. So this distance can be 0.5 mm by applying the straightness tolerance. So this is how we can override rule 1. Because sometimes why we should increase the cost in manufacturing. So at this time we provide this straightness tolerance, that even if the part is manufactured at its maximum material condition and it is having some variation in its axis, let's say the maximum variation it can have is the tolerance which we have given in the straightness tolerance, which is in this case which is 0.5. So this is the geometric tolerance value which we have provided in this example. So maximum variation this part can have is of 0.5 mm, even if it is manufactured at maximum material condition. So this is how we can override rule number 1. So this is similar to the, this is the second way you can override rule number 1. This is similar to the first one only. Similarly, when we apply the flatness to tolerance to a regular feature of size, to a size dimension of a planar regular feature of size. So in this case, you can see that whenever we are applying this flatness, so this is the symbol of flatness. So in this case also, if the part is manufactured at, let's say, at maximum material condition, so if we will find out for this part, what will be the maximum material condition? Is 10.5. So 10.5 will be the maximum material condition for this part. So if we see the flatness, so it is having the 0.5 mm of variation. So maximum variation again in this case also. So this variation from here to here we can have 0.5 mm, even if the part is manufactured at its maximum material condition, because there are some conditions in the rule 1 which we have understood in the previous session, that there are some condition needs to be fulfilled for the rule 1. So so if we are overriding rule 1 to reduce the cost of the part. Finally, if we specifying the independency symbol to a regular feature of size, so in this case, this I symbol, this is the symbol, this is the symbol for independency. So this is the symbol for independency. We can override if we apply independency symbol 10 plus minus 0.5 to a regular feature of size. It means we are overriding rule number 1. So whenever this I symbol, whenever this modifier, this is the independency modifier. Whenever we use this modifier we used along with the size dimension, it tells that that this particular size dimension of a regular feature of size does not obeys rule 1. So whenever we use the I modifier, it means this dimension, this size dimension does not obey the rule 1. Hence we can override this rule number 1. So these are the 3 ways in which you can override rule 1 of geometric dimensioning and tolerancing. So we have some limitations in the rule number 1. Rule number 1 does not control the location, orientation or alignment between the feature of size. So in this case, in this example, you can see that this is the feature of size 42 plus minus 1, and these are the feature of sizes, and for 32 plus minus 0 plus minus 1. So this is the feature of size. So in this case, in this rule's limitation, in this way, it is going to tell you that these feature of size does not control the location, orientation or alignment between the feature of size. In this case, you can see that this surface and this surface is having a 90-degree angle into the drawing. And in this, from side view, this also having the C.
this is denoted as B. This axis of this hole, which is coaxial with the one another, this is one hole. So this and this hole, both are coaxial in nature in this drawing. So this is denoted by A. And other sizes are also denoted by D and E. So these are the diameter size. So in this example, you can see that unless otherwise specified, interpret as per ASME by 14.5 2009. So this is the GSME standard, all angles plus minus 5 degree. Now, after manufacturing this part, after manufacturing this part does not, this part manufactured like this. So this is not at right angle. This is also not at right angle. These holes are not coaxial with one another. So you can see over here that one hole is not coaxial with one another. Still, this part will obey rule 1. So for obeying rule number 1, we have only some of the criteria. What are these criteria we have? We will verify with the rule 1 this part. So this part just have to follow some of the verifications that so this part does not control the angle between these features, the coaxiality between these holes. It will only control the rule number. If we want to, it verifies the rule number 1. So it has to verify the two methods. So let's say what are the verification. So in this particular limitations, we have understood that this does not control the location, not control the orientation, not control the alignment. So if we want to verify, so this is the verification of the rule number 1. So first of all, if we have to verify the rule number 1, first of all, we have to check that the actual local size should be within the limit of size. So at each and every cross section, in this case, it is dia 10 plus minus 2. So the maximum material condition will be dia 12 and the LMC least material condition will be dia 8. So in this case, it is saying that the actual local size should be within the limit. So this is the limit. This is the limits. If all the sizes, let's say at all points, this size is within the limit. Let's say this is having 10, 11, 12, 8. So it can vary from 8 to 10, 12 anywhere, but it should be within the limits of size. So this is how the first condition satisfied. So first condition is satisfied. So we have verified the first condition. Now the second condition of the verification of rule 1 is that the MMC and the envelope rule. So the part should enter into the envelope. So envelope is of maximum material condition. So in this case, dia 12 is the maximum material condition. So the maximum size of this envelope the part should enter is 12 mm. So this is the MMC rule. So if the part is manufactured at maximum material condition, let's say part is manufactured at this part is manufactured at a maximum material condition from here to here. Let's say this is of 10 mm and 2 mm of variation. So maximum 12. So if the part is entered into the envelope, so the condition 2 is also satisfied. It means this obeys rule 1. So these are the two verifications which we have to do in verifying the rule 1. And rule 1 is a default condition. So it is applied on all the engineering drawings. So this is all about rule number 1. In the next discussion, in the next session, we are going to discuss about rule 2. Thank you all of you. Hello and welcome everyone.
in this new session of GD&T, Geometric Dimensioning and Tolerancing, we are going to learn about the Rule 2. In the previous discussion, I have already told you about the Rule 1, how you have to override Rule 1, what are the requirements of Rule 1, how we have to verify the Rule 1. So in the Rule 2, this is a default condition. Actually, Rule 2 is a default condition. And in this particular session, we will understand about Rule 2. So rule 2 basically says that regardless of feature of size, so regardless of feature of size or RFS is a default condition on of all geometric tolerances by rule 2 of geometric dimensioning and tolerancing and requires no call out. So in this is a feature control frame. This is a feature control frame. And in this, you can see this is the geometric tolerance value. So this is the geometric tolerance over here. And this has, in this, if there is no modifier is used, means this is regardless of feature of size. Previously, we used the symbol, but from the 2009 standard, there is no requirement of using the RFS symbol. So this is a default condition. So rule 2 basically says that RFS, regardless of feature of size, is a default condition of all geometric tolerances by rule 2, and geometric dimensioning and tolerancing requires no call out. So regardless of feature of size simply means that whatever GD&T call out you make is controlled independently of the size dimension of the part. It is controlled independently of the size dimension of the part. RFS basically, if in simple terms we understand, here is in the geometric dimensional geometric tolerance where there is no modifier symbol is used. So you can see that in this there is no modifier symbol we have used in a default condition, which is a default condition we have already discussed. And here we have three datum references: primary datum, secondary datum, and tertiary datum. So we don't have any modifier symbol in the references also. So here also we haven't used any symbol. So this is also a default condition. If we are not using the modifier symbol in the geometric tolerance column in this compartment, so in this in the datum compartment also we are not using the modifier symbol. So where there are no modifier symbol in either a tolerance segment or a feature control frame or of a datum segment, so these are the datums of feature control frame, then it is called the regardless of feature of size and regardless of feature of boundary. So this is called regardless of feature of size, and in this it is called regardless of material boundary, RFS and RMB, and this is a default condition. This is a default condition. Now here we have an example. So when a geometric tolerance is applied on an RFS basis, so here you can see this is a feature control frame, and in this feature control frame the geometric tolerance is applied on an RFS basis. So there is no modifier we have used. The geometric tolerance is limited to a specified value regardless of the size of the feature of size. So geometric tolerance value is limited to the specified value. What does this means? Let's say this diameter of this is 50 plus minus 1 over here. So 50 plus minus 1 means what will be the maximum material condition of this hole? Will be 49. And least material condition of the hole is dia 51. So for this hole, whatever the size dimension, whether it's a MMC or LMC, the tolerance will be 0.2 only. So 0.2 will be the geometric tolerance for either 0.2 for this, and even if the part is produced at dia 50 also, then also the geometric tolerance value 0.2 will be there. So whenever the feature of size and the positional tolerance for the positional tolerance, there is no modifier is used. For the datum, there is no modifier. So this is a default condition where the regardless of feature of sizes applies. So whenever we have RFS, then we have a tighter tolerance. Whenever there is a default condition, we have RFS, there is a tighter tolerances. In this case, hole can be produced, I have already told you that hole can be produced whether at 49 MMC or 51 at LMC, but the positional tolerance remains same for both the cases, which is 0.2 only. It remains constant. In most of the general applications like jig and fixtures, gauges, machine tools, so machinery, we require tighter tolerances. In that case, we use such cases, we go with the RFS regardless of feature of size. Where there is tighter tolerances is required to in the manufacturing, we go with the RFS. And RFS is a default condition by the rule 2. Now we will understand that whenever it is necessary, so whenever it is necessary, we can use MMC, maximum material condition, or LMC modifier may be applied. In that geometric tolerance value over here, you can see this. In this condition, we can use MMC modifier, maximum material condition, in the feature control frame after the geometric tolerance value, and we can apply to a feature of size, and which is maximum material boundary. So both symbol are this is after the datum, primary datum. So in this MMB or LMB modifier is also may be applied for the datum reference of the feature control frame. So this is we are coming out of the default condition. But if there is requirement of applying MMC or LMC, so we can apply into the feature control frame. So here we have the example of the maximum material condition applied to a tolerance, tolerance, and maximum material boundary applied to a datum reference. Here we have similarly, we have the least material condition applied to a tolerance and least material boundary applied to a datum reference. So this is very important. We take one of the example of maximum material condition. So when so here we have some flexibility whenever we are using maximum material condition modifier. This modifier, we got some flexibility in manufacturing. This flexibility, how we get, I will be telling you this, that we get the flexibility after applying the maximum material condition. Let's say so when the hole is produced at MMC, in this case, if the hole is produced at MMC, MMC is a 49. So MMC for this hole will be 49. Positional tolerance will be 0.2. So in this case, the positional tolerance will be 0.2. But whenever we will move from MMC towards LMC, in the for the feature of size, we will move towards MMC, the positional tolerance will increase. When we will reach at LMC 51, the positional tolerance will become how much? It will become 51.0.2 will be added. So 2.2 will be added. So in this case, you will see that 0.2 in each case, 1, 50, 50.1 and 51.2. So this will be the case for LMC. Sorry, we are discussing about positional tolerance. So positional tolerance will go 2.2. So this is how we get the flexibility in manufacturing. That when the part is produced at maximum material condition, because we have applied the maximum material condition modifier here in feature control frame. So after adding feature MMC, when we will move from MMC towards LMC, we got the bonus tolerance. So that's why we got the more flexibility in manufacturing. We have already discussed about the bonus tolerances. So when the hole departs from MMC towards LMC, then the positional tolerance value changes from 0.2 to 2.2, where you have to ensure assembly, and whenever you have to reduce the scrap rate. So with the help of this, the scrap rate is also reduced, because whenever there is tighter tolerances, the part rejection will be increased. But whenever we have flexibility in the manufacturing, the scrap rate will be reduced. In all such applications, we go with the MMC modifier. You will see in the most of the automobile applications, you will find MMC modifier used, because the production which is happening is on a very large scale, and many thousands of parts are going to be assembled with multiple thousands of parts. So that's why the flexibility in the manufacturing process is a necessity. So that's why we go with the maximum material condition modifier. In the next case, you will see we use the LMC modifier. So here we have used LMC modifier. So whenever the part is produced at LMC, which is 51, the positional tolerance will be 0.2. When we will move LMC towards MMC, means from 51 towards 49, the positional tolerance become 2.2, because the it will be got added. So in this case, whenever whenever there's a requirement of a increased, I will say, in this particular example, if there is a requirement of minimum wall thickness. So most of the application where we require the minimum wall thickness on a part, in such applications we use the least material condition modifier. So sometimes in aeronautical conditions and other critical precise applications, where there is material thickness is a very important aspect. In all such cases, we go with the least material condition modifier. So in this session, I have I have already told you three new terminologies, which is RMB, regardless of material boundary, MMB, maximum material boundary, and LMC, least material boundary. So one by one, we will be discussing about this. So first of all, regardless of regardless of material boundary, RMB is a condition where the stated tolerance limit must be met irrespective of as build datum, feature size, or location. So when a datum reference datum reference is a feature of size. So this is a condition. Whenever datum reference is a feature of size and no modifier is applied, then it is the regardless of material boundary. So in this, there is no requirement of the material boundary. Whenever this datum is a feature of size and no modifier is used, this is a default condition. So RMB is a default condition. In this case, no modifier is required. So it is no modifier is applied, and then this is condition is called the regardless of material boundary. Now, whenever maximum material boundary is a boundary that the datum feature of size will not violate, the MMB is calculated by combining the MMC size with any applicable geometric tolerance or on a datum feature of size. The MMB is always outside the material. We will know this. The MMB is always outside the material. Whenever we use the maximum material condition for the feature of size with the geometric tolerance, we can use for the datum reference, we use maximum material boundary. So MMB always used with the datum reference. So this is the very important thing. Now we will understand one more terminology, which is about the least material boundary. So least material boundary is a boundary that the datum feature of size will not violate. The LMB is calculated by combining the least material condition size with any applicable geometric tolerance on the datum feature of size. The LMB is always inside the material. So least material boundary is always inside the material, and MMB is always outside the material. So we will be discussing with the 3D aspect also. So this is very important. So whenever there is whenever a datum reference is a feature of size, and least material modifier is applied, and least material condition modifier is applied, then it is called the least material boundary. Now we will understand that how to override rule 2. We have already discussed that whenever there is no modifier used in the feature control frame, so it is a default condition, which is stated by the rule 2. But whenever we are using the MMC or LMC, maximum material condition or least material condition modifier in the feature control frame in the tolerance segment, so it means that we are overriding rule 2. So it is stated here, whenever MMC and LMC modifier is applied in the tolerance segment of the feature control frame and MMB or LMB modifier is applied in the datum reference frame segment of the feature control frame, then rule 2 is overridden. So what does this mean? That we are coming out from the default condition. What is the default condition? Whenever there is no modifier is used, whenever there is no modifier like maximum material condition and maximum material boundary is used in the feature control frame, so it is a default condition whenever no modifier is used. When we use the modifier, means we are coming out from the default condition and we are overriding rule 2. So whenever there is a requirement to use the maximum material condition or the least material condition with the maximum material boundary or the least material boundary, we are coming out from the overriding rule 2. So this is all about rule 2 and how we have to apply that, where we have to apply the default condition, where we have to apply the MMC modifier, and where we have to apply the least material condition modifier, LMC or LMB modifier. So now it is gotten clear that what is rule 2. Thank you everyone. We will see in the next session. Thank you. Hello everyone, this is Manish from Skillable India, and this is the continuation session of geometric dimensioning and tolerancing. In today's session, we are going to learn about the bonus tolerances. So bonus tolerance is a very important topic in geometric dimensioning and tolerancing. So with the help of bonus tolerance, although it is not a part of the ASME by 14.5 2018 or 9 terminology, but this is frequently used into the industry. So basically bonus tolerance is a very important part, and I will let you know that how we get maximum flexibility in manufacturing. And with this bonus tolerance, we can reduce the cost of the manufacturing and the cost of the inspection at very minimum level. So this is a very important thing in the geometric dimensioning and tolerancing, and it is a very important concepts also. So this can reduce the cost significantly in the by using the geometric dimensioning and tolerancing. To understand the flexibility of manufacturing, so let us take an example. With the help of we have a regular feature of size over here. So this is the example of a regular feature of size. So 10 plus minus 2, here we have taken the regular feature of size. For the ease of understanding, I have taken a very coarse tolerances, very bigger tolerances. So it will be make much easier to understand that how we make use of bonus tolerances in flexibility for the flexibility of manufacturing. So right now we have used over here the straightness tolerance. So straightness tolerance we have used of 1 mm. 10 plus minus 2 is the regular feature of size, and the straightness tolerance I have used over here is 1 mm. So after first of all, I will understand the concept of with the definition. In GD&T, bonus tolerance is a modification of a GD&T tolerance that under certain condition increases the tolerance. So what does this means? Under certain condition increases the tolerance. In the previous session, I have already told you about the maximum material condition and least material condition. So with the help of maximum material condition and least material condition, we will be getting more tolerance. That's why we are getting more flexibility in manufacturing, and while assembly, the rejection rate of the part will be less. So that's why in automobile sector, where thousands and thousands of parts need to be assembled with one another, so in that case, we need broader tolerances. We need more tolerances to get them assembled. So hence the term bonus, more specifically when the maximum material condition. So in this case, 10 plus minus 2, what is the maximum material condition? In this case, maximum material condition of this shaft is 10. If I am considering, so what is the maximum? It is 12. So 12 is the maximum material condition, and LMC, least material condition over here, is 8. So MMC and LMC of this part, MMC is 12 mm and LMC is 8 mm. So it is written more specifically when the maximum material condition MMC symbol is used to modify the GD&T tolerance. Here GD&T tolerance is 1 mm. So this is the GD&T tolerance, geometric tolerance. Bonus tolerance becomes available. The MMC modifier implies that the GD&T tolerance can be increased if the manufacturing process can control the related feature of size. So this is very important, that the manufacturing process can they get more room for with the help of tolerances. So let's say with the next example. So this is the part drawing. We have part drawing, and this is the condition of after manufacturing. So after manufacturing, what will be the condition? So here I have, if I have provided one symbol over here which is of maximum material condition. So here if I have provided the symbol maximum material condition with the straightness So whenever we are applying the maximum material condition or least material condition, it is only applicable to a regular feature of size. We can only provide material condition modifier to a feature of size. To a feature, we cannot provide the material conditions. Only to the feature of size, we can provide the material condition modifier. Either it's a maximum material condition or a least material condition. So in this case, if I have given the maximum material condition modifier, so what will be what we will getting over here is, so after manufacturing, we can end up with a part like this, which is manufactured at dia 12 and having, so I haven't used the diameter symbol, just you have to consider that. In this case also it is a diameter. So after manufacturing, we can end up with a part which is manufactured at dia 12 mm. It is having, this is the maximum material condition. I have already told you for this condition, MMC is 12 mm and LMC is 8 mm. So this is the maximum material condition. So the part is manufactured at 12 mm. So the maximum straightness error this part can have is of 1 mm. So this is the envelope. This is the virtual condition. What is the virtual condition? We will discuss this virtual condition in a very detailed manner in the coming sessions. But if I will tell you in one word, virtual condition is the worst case condition that the part can enter into the hole. So in this case, the worst case condition is, or the virtual condition is, the maximum material condition plus the geometric tolerance value, which is 12 plus 1, which is 13 mm. So in this case, the virtual condition or the envelope, this envelope, the virtual condition envelope is of 13 mm. So the maximum variation this part can have is of 1 mm. If the part is manufactured at maximum material condition, then the maximum straightness error can have is of 1 mm. Then only the part can enter straightness error, so that the part will be enter into the hole or into the envelope. In this condition, this is the virtual condition. So with the help of envelope, we are understanding that this part will enter into the mating part or not. So with the help of envelopes, we understand this, that this part will be enter into the with the mating part, or get assembled with the mating part. So for this, we will get the actual mating envelope. So in this case, this is the actual mating envelope. Actual mating envelope. In this particular case, it is produced at the MMC and with the maximum straightness error. So the actual mating envelope is created with the virtual condition, which is the maximum material condition plus the geometric tolerance value. So which is equal to the 13 mm. Now there are multiple possibilities. Let's say this part is not manufactured at 12 mm. This part is manufactured at 8 mm. Let's say this part is manufactured at 8 mm. This size, actual local size of this part is 8 mm throughout this part. So what will be this part is manufactured at least material condition, because LMC is a 8 over here. So now in case we are just understanding that part can manufacture at anywhere between 12 and 8. So let's say we are taking this example that the part is produced at the least material condition and cannot have the access band more than 1 mm. Oh, sorry. In this case, it cannot have more than 1 mm because the part is produced at MMC. This is the straightness error should not be more than 1 mm in this case. But this part enter into the virtual condition. So if this part with the 8 mm will enter into this, so the maximum variation, this is the variation. If this part is, let's say, 8 mm, so the maximum variation this part can have is 13 minus 8. So 13 minus 8, we have 5 mm. So the maximum variation we can have if the part is produced at least material condition is 5 mm. In the coming slide, I will let you know that how this calculations are being done. So this 5 mm is the bonus tolerance. So this is the bonus tolerance. How we are getting this? Now, practically speaking, if a part which is produced at its least material condition, and if the straightness error is more than 1 mm, it also reaches until the maximum least material condition, virtual condition, the part can enter into the mating part. So I have already told you that if the part is manufactured at 8 mm, the maximum variation that part can have is of 5 mm, because we are having the straightness tolerances of 1 mm and 4 mm is the variation. So this is the flexibility we want in manufacturing, so that the scrap rate can be reduced. How to get this flexibility by using the GD&T in is what we are going to discuss in this chart, that how we are getting this flexibility. Now, this is the same example. This is the same example. In this case, maximum material condition is 12 mm and the least material condition over here is 8 mm with this example. So after manufacturing, we are just understanding, I have already told you. In this case, one of the bonus tolerance is one of the terminology which is not into the standards. I have already told you, but very frequently used into the industry and is called the bonus tolerance. So bonus tolerance is a potential additional tolerance for geometric tolerance. Now, where the MMC and LMC modifier is specified, whenever we are using MMC or let's say LMC modifier, over here, let's say if we are using, I will make another feature control frame over here. So whenever we are using maximum material condition or least material condition modifier, it indicates that the stated geometric tolerance applies when the feature of size is at MMC or LMC size limit. When the actual mating envelope, this actual mating envelope of the feature of size departs from MMC towards LMC, when the size of the part, this is the part, when the part departs from MMC towards LMC, so towards MMC, an increase in the stated tolerance is permitted. So the tolerance will increase. If the part is manufactured at 12, then the tolerance we have is of 1 mm, because this is the actual mating envelope. Actual mating envelope. So this is created with the help of the virtual condition. So 12 plus 1, 13 mm. The part can enter into this envelope if the part is created, let's say, at 12 mm. I have already told you, if 12 mm part is the part is manufactured at 12 mm dia, so we have tolerances of 1 mm. 1 mm variation only we can have, because the maximum size, this is the maximum size. If this size is manufactured, then only the part will enter into the mating part. With the mating part, it get assembled. So this is the maximum size we have right now. So if the part is manufactured at maximum material condition 12 mm, we have straightness error, because if the part will be manufactured at 13 mm, let's say 13 mm part is manufactured, so we require the perfect form. In the rule number 1, we have learned this thing, that if the part is manufactured at maximum material condition, when the part with the tolerance, geometric tolerance, so this should be the perfect form, which is very costly or which is impossible to manufacture. So perfect form is required. So what we are using over here is that the part is not in this, sorry. So the part, we are taking it from the maximum material condition. So this is the maximum material condition. If the part is manufactured at maximum material condition, we have 1 mm of variation. Or tolerance we have, geometric tolerance we have is of 1 mm, which is this. Now, Similar case, if we are moving towards MMC towards LMC, let's say now the part is manufactured at 11 mm. So what will be the maximum variation over here we have is, if the part is manufactured at 11 mm, we have the variation is of 2 mm. So this variation is not now 1 mm, it will become 2 mm. So geometric tolerance value will be 2 mm. So we get more tolerance as we are moving towards from MMC towards LMC, from maximum material condition towards least material condition, because in this case, we have provided the maximum material condition modifier. So this is the MMC modifier we have used. So that's why we are moving MMC towards LMC. So this is the 2 mm variation we have. This is the bonus tolerance. Now, if the part is manufactured, let's say, if the part is manufactured at 10 mm, if the part is manufactured at 10 mm, dia 10 mm, so we have the we have the tolerance of 3 mm. So this variation will be now 3 mm. So this variation can become 3 mm and the tolerance value will be 3 over here. Now, if the part is manufactured at 9 mm, this 9 mm, so this tolerance, this variation can have 4 mm. So this will be manufactured like this. And we have more practical tolerance over here. Still the part will enter into the envelope. So the maximum variation is of 4 mm. Let's consider. If the part is manufactured at least material condition, which is 8. So this is the maximum material condition and this is the least material condition. So when the part is produced at 8 mm, so the maximum variation, although if I am considering this, so again the part is manufactured with 8 mm. So the maximum variation what the part can have is the maximum tolerance, which is 5 mm. So 5 mm of bonus tolerance. With the bonus tolerance we have. So as we are moving from MMC towards LMC, we are getting more and more tolerance. So that's why we use these material condition modifiers in the feature control frame. And this is very important to learn that why we are using these modifier and how did we get the more tolerance with this. So the MMC over here is, I have already told you that whenever we are moving from MMC towards LMC, we are getting more and more tolerance. More tolerance. Just for the, I have taken very big tolerances just to get understand, just to tell you that how we get the more tolerances. Now, if I consider some points if we remember. So in bonus tolerance occurs only when the geometric tolerance is applied at MMC or LMC to a feature of size. So it is very important point. These are points to remember. Points to remember. Bonus tolerance occurs only when the geometric tolerance is applied to at maximum material condition or least material condition to a feature of size. So bonus tolerance will only come into effect when we have given the material condition modifier to a feature of size. Bonus tolerance never get applied when we have provided the tolerance to a feature. So a feature of size and feature are two different things. So I have already discussed it before in the discussion that whenever we are applying the maximum material condition or the minimum material condition to in a feature control frame, we get the bonus tolerance. So this is only applied to a feature of size. Whenever we are applying the material condition modifiers to a feature of size, then we get the bonus tolerance. Second point is, bonus tolerance does not affect the size tolerance. So bonus tolerance does not affect the size tolerance. Whatever be the size tolerance, let's say it can be a plus minus 0.5, plus minus 0.1. So it does not affect the size tolerance. 10 plus minus 0.5 or 10 plus minus 0.2. Anything can be that size dimension, size tolerance. So it does not affect the size tolerance, bonus tolerance. What is the bonus tolerance? If we understand this, so it is the difference between the actual size and the MMC or LMC. So with the actual size, we with the and LMC and MMC. So the maximum amount of bonus tolerance is permissible. Maximum, if I write it down, so maximum amount of the bonus tolerance permissible is equal to the difference between MMC and LMC. So we are moving from MMC towards LMC of the actual meeting envelope. Actual meeting envelope of the tolerance feature of size. So this is very important, that it is basically the difference between of that. Whenever we are moving from MMC, maximum material condition, to a least material condition modifier. Now, I have already told you this thing, that bonus tolerance is applicable to the geometric tolerance applied to a feature of size. So bonus tolerance is applicable to a geometric tolerance applied to a feature of size, FOS, at maximum material condition and least material condition. Now, one thing is important. Every dimension is every time we have been provide the tolerance to a feature of size. So out of 14 geometric symbols, there are total 14 geometric characteristic symbols, out of which we have only these symbols which can be provided to a feature of size, which geometric tolerance applied to a feature of size. So these are the only tolerances which we apply to a geometric tolerance applied to a feature of size. Rest of them applied to a feature, and in this also there are some of them we are applying to the feature. I will let you know. Maximum material condition and the least material condition is applied when the geometric tolerance is applied to a feature of size only. So MMC and LMC modifiers are only applied when the geometric tolerance in the feature control frame is applied to a feature of size only. So these are the tolerances out of 14 that we provide to a feature of size, geometric tolerance to a feature of size, in which it is straightness, flatness, angularity, perpendicularity, parallelism, and position. So these are the only tolerances. So these are the geometric tolerances which can be applied to a feature of size. So these are the only geometric tolerance which can be applied to a feature of size with MMC and LMC modifier. In this, these are the only geometric tolerances which can be applied to a feature of size and get additional tolerance in the form of bonus tolerance, which we call as bonus tolerance. Now, there are other tolerances are also there. So bonus tolerances is not applicable to the geometric tolerances applied to a feature. Now you can see that bonus tolerances is not applicable or to geometric tolerances applied to a feature. So whenever we are providing the geometric tolerance to a feature, means either surface or hole, we are providing the geometric tolerance to a feature. So the MMC, material condition modifiers, either it's a maximum material condition or least material condition, both are not applicable. So these are 13 symbols. These 13 symbols, whenever geometric characteristic symbols, these are 13 symbols. When applied to a feature, is not applicable for the bonus tolerances, because we do not apply the material condition modifier. So in this there are 13 symbols: straightness, flatness, angularity, perpendicularity, parallelism, cylindricity, circularity, concentricity, symmetry, circular runout, total runout, profile of a line, profile of a surface. Whenever these 13 symbols, 13 geometric characteristic symbols are applied to a feature, I am not talking about feature of size, only feature. Whenever applied to a feature, the material condition modifier are not applicable. It means we do not get any additional tolerances. We do not get the bonus tolerances for when we apply the geometric characteristic symbol or geometric tolerances to a feature. So only these are the geometric tolerances applied to a when they are applied to a feature of size. Then only the material condition modifier we use. So this is the total value of the bonus tolerances we get. So this is all about the bonus tolerances. So now in the next discussion, we are going to learn, or I am going to tell you about the how to calculate with the chart. And there is one Excel sheet I will also let you know with the help of that how we calculate the bonus tolerances. So this is all about the today's discussion. Thank you everyone. Hello everyone, this is Manish from Skillable India, and in today's session of geometric dimensioning and tolerancing, we are going to discuss the very important topic, which is about the virtual condition. So what is a virtual condition? In simple words, if I will tell you what is virtual condition, so this is the worst case scenario of the mating parts. It can be a hole or it can be a pin. So in this particular session, actually, we are trying to ensure that the assembly between the mating parts and we are going to calculate the sizes of the functional gauges. And if in this video we are going to ensure that the part are going to be assembled with one another. The part with the hole and the part with the pin, they are going to assemble with one another. We are going to ensure in this session. So virtual condition is the worst case condition that the part can have. So how to calculate this? We will take first of all one example. So I have already told you that the virtual condition is a worst case condition of a feature in terms of mating of hole and a shaft. Shaft or a pin, both are same thing. So we are ensuring the assembly. So we are taking the worst case condition example over here. So this is the example. In this case, we have hole this side, part number 1, and this is the pin, part number 2. Now we have to ensure that this hole should be assembled with this pin. Sorry, this pin should be assembled with the hole. To understand the boundary concept, so first of all, we have to understand is boundary concepts. What is boundary? So we are going to understand the boundary concept in detail. So we have to understand this boundary concept. We are going to understand with the help of this example. So here we have two parts, one with the external feature of size. So pin is an external feature of size, and hole with the internal feature of size. So this is the internal feature of size. Whenever I am using the terminology external feature of size, means I am talking about pin. Whenever I am using the terminology internal feature of size, I am talking about hole. So don't be confused in this. We are just trying to ensure that the assembly between the hole and the pin. So to understand this concept better, so for both of them, we have a same limit of size. So you can see that the for hole 40.5 and 40.1 is the limit of size, and for shaft also we have same limit of size is over here. So in case of hole, 40.1 will be the MMC, maximum material condition, and 40.5 will be the least material condition. In case of shaft, 40.1 will be the least material condition and 40.5 will be the maximum material condition. So this is the case for, we have taken the same tolerance, same positional tolerance, which is 0.1 in both the cases. So both cases we have taken 0.1 positional tolerance. In these two parts, the worst case of the internal feature of size will be, what will be the worst case? In this case, the worst case will be the for the internal feature of size will be the smallest hole. So smallest hole means the 40.1 maximum material condition for hole. So smallest hole will be the smallest hole with the positional tolerance of 0.1. So here is the worst condition. So if we calculate the worst case boundary for this, so we will get 40.1 minus 0.1. We get 40 mm as the worst case boundary. So for hole, worst case boundary is the 40 mm dia. So dia 40 mm is the worst case boundary we have. Least material, maximum material condition minus the geometric tolerance value. So minus positional tolerance. So the least, the smallest hole we can manufactured with with this dimension we can have is of 40 mm dia. So this is the worst case condition for the hole, for the internal feature of size. If we take similar for the external feature of size or the pin, so what we can have is, in this case also we will take maximum material condition, which is 40.5. So this is the maximum material condition for the shaft. 40.5 is the maximum material condition for the shaft. So what can be the worst case condition? That the shaft can be biggest. So if we manufacture the shaft and if we see the virtual worst case boundary, so worst case boundary will be the MMC plus the positional tolerance, which is 40.6. So in this case, worst case boundary will be dia 40.6. So the part produced by 40.6 will never enter into the hole, which is having envelope of 40 mm. So this shaft is never going to enter into this hole because the size of the size is not matching. So that's why we calculate the boundary conditions. So that's why we are calculating the boundary, worst case boundary. That's we should ensure the assembly. So in this case, you can understand. So this is where we are calculating the boundary condition comes into picture. So that's why as a design engineer, all the time we have to see that the size, if we are taking the size of the hole, so what should be the size of the pin that is going to be assembled with the hole. So we need to ensure and we give exactly that dimension that ensures the assembly. So always we try that the maximum material condition for the hole and the maximum material condition for the shaft should be same. So how it will be same and how we will calculate that what should be the worst case, with the help of boundary conditions, how we can calculate the right dimension for the pin or the hole, for the internal feature of size or for the external feature of size. So we are going to understand with this. So we will again come to this example with the different dimensions. So first we will understand about the boundaries. Worst case boundary, inner boundary and outer boundaries. It is important to be able to calculate the boundary condition for a feature of size for several reasons. So it is important that to be able to calculate the boundary conditions for the feature of size for several reasons ensures that mating part will assemble. So we are here, the question is hole and pin should be assembled. So these both the things should be assembled. The main thing is the assembly. So we need to ensure that the pin and the hole should be assembled with one another. So in which we should we can calculate for the design gauges, make engineering calculations, etc. So the boundary concept in this section are explained using the example of the boundaries affect assembly. So what is the worst case boundary? The worst case boundary is a general term used to refer to an inner boundary or an outer boundary. So worst case boundaries is a general term and used to refer an inner boundary or an outer boundary or a virtual condition. The worst case boundary affects how part will assemble. So just why we are calculating this worst case boundary, because we know the exact dimensions that to be give onto the engineering drawing to manufacture. So that's why these boundary conditions are very, very important. So we will one by one we will understand that is what is inner boundary, what is outer boundary, and what is the virtual condition, and what are the different effects in the virtual condition, and how we will calculate them. Now, first thing is the inner boundary. So what is inner boundary? First of all, we will understand internal feature of size for hole. So inner boundary we are going to calculate for the hole as well as for the shaft. So for inner boundary we will calculate for the internal feature of size for the hole and the external feature of size for the shaft. So what is inner boundary? Inner boundary for an internal feature of size or hole is a worst case boundary generated by the smallest feature of size MMC. So for hole, MMC will be the smallest hole size. MMC will be the smallest hole size. Hole size. So here in this definition, the smallest feature of size MMC minus the effect of the applicable geometric tolerance and any additional tolerance or the bonus tolerance that may apply. So in this, just it is saying that the MMC minus the geometric tolerance value, GTV. So this is the condition for the hole. So this is the inner boundary. So if we calculate the inner boundary for hole for internal feature of size and the external feature of size. So in this case, inner boundary is MMC minus geometric tolerance value. For external feature of size, inner boundary of an external feature of size is the worst case boundary generated by the smallest feature of size, means the smallest shaft. Inner boundary will be the LMC minus the effect of the applicable geometric tolerance and additional tolerance, bonus tolerance that may apply. So minus the geometric tolerance value. So inner boundary for hole will be MMC minus geometric tolerance value, and inner boundary for this shaft will be the LMC minus geometric tolerance value. In this case, you can understand that the inner boundary will be the actual related actual mating envelope. Related actual mating envelope. And in this case, you can see that it is actual related actual minimum material envelope. Actual minimum material envelope. We have already understood this concept earlier of the envelope. What is actual minimum material envelope and what is actual related actual mating envelope. So this is the imaginary one and this is the real one. So this is all about the inner boundary for the internal feature of size hole and for the external feature of size shaft. With the help of example, we will understand this inner boundary concept in very detailed manner. So first of all, we are taking an example of RFS concept. So in this, RFS is the positional tolerance do not have any material condition. So first of all, this is for the hole. For internal feature of size hole, we are going to understand this concept. So the maximum material condition of the hole is 40.1 and the geometric tolerance value is 0.1. So the inner boundary is equal to the maximum material condition minus geometric tolerance value. So it is going to be 40. So inner boundary for the hole is the smallest hole size. So in this condition, let's say this is the true geometric counterpart and this is the center. With this center, the hole is being created with the maximum material condition with the center hole, which is not possible. So one by one we will understand that what can be the conditions. So this in this concept you can see I will show the extreme conditions that the part can be manufactured. So we are having MMC over here 40, sorry, MMC we are having 40.1 dia and the geometric tolerance value we are having 0.1. So you can see that here we have an internal feature of size with positional tolerance applied at regardless of feature of size. So to get the center of the hole, we here at have the tolerance zone. So this is the tolerance zone which is having 0.1 mm of tolerance zone, and the part is with manufactured with dia 40.1. So this is the tolerance zone we have 0.1 mm and the part is produced at the maximum material condition which is 40.1. So this is the ideal situation basically. So this is the ideal situation is to have the center exactly with the true position, which is very, very difficult. So the whole center anywhere within the circular tolerance zone. So it can be within this circular tolerance zone anywhere. It can be maximum here. It can be maximum here. It can be here. It can be here. So this whole center will vary within the tolerance zone. So in this case, the extreme top, extreme corner, extreme left, extreme right. So with this, you can understand that the tolerance zone we have here is at maximum. So these are the extreme conditions what we have here. If you put all the extreme condition together, so in this case all the extreme conditions are together, we end up with the combination like this. So in this case, if you want to assemble a true geometric counterpart or pin, in this case if you want to assemble the pin, so it will be the smallest size. So this green circle you can see inside this part. So however it is manufactured, the condition will be this, that it should be manufactured at inner boundary 40 mm. So this inner boundary will be 40 mm. So if the pin size is 40 mm, okay, it will enter into this hole. So the smallest size, the pin size should be 40 mm. Then only it will enter into this hole. If it will be more than 40, maybe the chance can come it will not get assembled. So the least size of the pin will assemble is 40 mm after all the worst conditions. So these are the worst case scenarios that the part is manufactured at extreme conditions. So these are the extreme conditions that the from 0.1 tolerance zone here, if the center is over 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 here. So these are the extreme conditions of the hole. So if the pin size is 40 mm, it will definitely going to assemble. So this is why we calculate the inner boundary. Similarly, we will understand the boundary, outer boundary. So for both the conditions, we will understand outer boundary for the internal feature of size hole and the for external feature of size shaft. So outer boundary is the largest feature of size LMC. So hole with the LMC, outer boundary is equal to the LMC plus the effect of applicable geometric tolerance, any additional tolerance that may apply. So in this case, you can see that the outer boundary for the hole is the actual minimum material envelope, because if this is a part and the boundary condition is inside the material, if it is inside the material, so this is an imaginary boundary. This is an imaginary boundary, and imaginary boundary we have already understood that this is the related actual minimum material envelope. Related actual minimum material envelope. So that's why these envelope is to understand in a very detailed manner is very important. That then only you will understand the inner boundary concept and the outer boundary concept of the hole and the shaft. Similarly, if we understand the outer boundary for the shaft, so what is the outer boundary for the shaft? Outer boundary of an external feature of size is a worst case boundary generated by the largest feature of size MMC plus the effect of the applicable geometric tolerance and additional tolerance or the bonus tolerance that may apply. So here we are saying that the geometric tolerance plus. So in this case, outer boundary, if this is the part, let's say, if this is the part and we are talking about the outer boundary. So it is MMC, the biggest hole, plus the geometric tolerance value. So we are talking about this size. So this is the actual mating envelope. So this is the related actual mating envelope. So you have to learn these things, outer boundary and inner boundary. So outer boundary for the internal feature of size will be the outer boundary for the internal feature of size will be the LMC plus geometric tolerance value, and outer boundary for the external feature of size will be MMC plus geometric tolerance value. Now we will understand about the virtual condition. So before starting the virtual condition, we will understand this concept with the help of example. So in this case, you will see with the RFS concept, we will understand for the external feature of size, outer boundary for external feature of size, which we have already understand. So outer boundary for external feature of size. So let's say the part is being created with the maximum material condition. So for external feature of size, this is MMC and this is LMC. So for external feature of size for shaft, if the center is at center. So this is the tolerance zone. So this is the 0.1 dia tolerance zone, TZ. So tolerance zone we have. Now, if the part is manufactured with the extreme conditions, let's say the center is over here, center is over here, here and here. With the extreme conditions, if the part is manufactured, so this is the extreme condition of the part. So if this shaft is going to be assembled with the hole, let's say this is another part and this is the hole. If this shaft needs to be get assembled with this hole, this shaft is going to be assembled with this hole. So what will be the size of this shaft? The maximum size of the hole should be 40.6. So here outer boundary of the shaft will be maximum material condition plus geometric tolerance value over here. So 40.5 is the size plus geometric tolerance value 0.1. So we get over here 40.6. So the minimum diameter of the hole should be at least dia 40.6. Then only this shaft will going to assembled with the hole. This is hole part 2, and this shaft is going to be only assembled with this hole if the size of the hole will be at least 40.6, because the extreme manufacturing of this shaft can be at dia 40.6. So this is the outer boundary. So outer boundary of the shaft will be 40.6. So this is the outer boundary, and this is the condition of actual mating envelope, related actual mating envelope. If you do not get understand, go back and see that video again, so you will get understanding in a detailed manner. So we are not understanding the concept of actual minimum material envelope. We are only understanding the concept of outer boundary for the actual mating envelope. So that's why it is important. Now we will understand about the virtual condition. So virtual condition is a very important. So in this case, you can understand that the virtual condition, what is virtual condition? I've already told you, it is the worst case condition. A fixed size boundary generated by the collective effect of the considered feature of size specified at MMC and LMC. So virtual condition we calculate for MMC condition and LMC condition, and the geometric tolerance for the material condition, for that material condition. So in this, you will understand that we have four concepts. Four concepts we have for virtual condition. MMC, maximum material concept for internal feature of size for hole. LMC concept for internal feature of size for hole. MMC for external feature of size for shaft or pin, and LMC concept for external feature of size for a pin. So MMC for hole, LMC for hole, MMC for pin, and LMC for pin. So these are the four concepts one by one we are going to understand in this virtual condition. Virtual condition can be established for a part for internal feature of size at MMC. So this is the first concept. So we can establish a virtual condition for four concepts. I have already told you, we can take the first concept over here. MMC concept applied to an internal feature of size for hole. So for hole, we are going to understand. So for hole, 40.1 is the maximum material condition and 40.5 is the least material condition. So these are the limit of sizes, and the positional tolerance is applied at maximum material condition. So here, if it is applied maximum material condition, so 40.1 is the MMC for hole and 0.1 is the geometric tolerance value. So virtual condition is the worst case condition. Here is equal to the inner boundary is equal to the MMC minus geometric tolerance value. So 40.1 minus 0.1, so 40 mm we are having here virtual condition. So dia 40 we are having the virtual condition. Now the part is manufactured at, so we are having this tolerance zone. So dia 0.1 is the tolerance zone we have, and the part is manufactured at maximum material condition. Now we have extreme conditions. So 40.1. So all the four conditions you can see that the hole is manufactured with the size this. So now you can see, now this is the inner boundary. So now you can see, so inner boundary here is the smallest shaft that can enter inside this hole. So inner boundary is equal to, why we are calculating the inner boundary? Because we have to calculate the size of the shaft, is the dia 40 mm. So 40 mm pin or the shaft will enter into this hole. So that's why we are calculating the inner boundary of this hole. So in this case, I have already told you that the virtual condition is equal to the inner boundary. Virtual condition is equal to the inner boundary. Inner boundary, the formula of inner boundary, I have already told you, MMC minus geometric tolerance value. MMC over here is 40.1 minus 0.1, which is geometric tolerance value, and 40 mm dia is the inner boundary or the virtual condition. So 40 mm dia of pin will can enter into this hole. So this is the size of the pin that can enter into this hole. So this is the MMC concept for the internal feature of size. Now we will understand the LMC concept for the internal feature of size. So LMC concept for internal feature, in this case also, this is MMC and this is LMC. Least material condition, maximum material condition. So, but here the modifier is of least material condition. So we will take the least material condition, which is 40.5. So in this case, the 40.5 will be the least material condition, is the largest hole. So this is the largest hole. And in this case, we will calculate the, for least material condition. First of all, this is the size. This is the least material condition. This is the size of the hole. And for this, the tolerance zone is of 0.1 only. This is the tolerance zone we have. For extreme conditions, when the part is manufactured at 40.5 at extreme condition. So this is the extreme condition we have, that the part is manufactured. So in this case, the virtual condition will be the outer boundary. So virtual condition will be the outer boundary over here, which is the least material condition plus geometric tolerance value. So outer boundary for the whole, you can see this green circle. This circle shows which is of outer boundary, which is of dia 40.6. So in this case, least material condition is dia 40.5 plus dia 0.1, which is geometric tolerance value. So this is the 40.6. So this is also the virtual condition is equal to the outer boundary. And this outer boundary, we have already known that this outer boundary is a related actual minimum material envelope. And this is the imaginary envelope because this is inside the material. So this is always this outer boundary of the whole. So this is the outer boundary of the whole, which is inside the material. So that's why it is called the imaginary boundary. It is also called the imaginary boundary, and that's this is the imaginary boundary. So because this is inside the hole, because in this case the hole will be much more bigger. So this is the worst case condition for the outer boundary in this case. Now we will understand the concept for the MMC condition for the external feature of size. So now we will understand the MMC concept for the external feature of size. So now you can see that for external feature for pin, so this is for pin. So this is the MMC 40.5 and this is the LMC. So if the part is manufactured at maximum material condition, because the modifier we have used here over is MMC. So if the part is manufactured at maximum material condition, so MMC maximum material condition is dia 40.5. We have tolerance zone. This is the circle denotes the tolerance zone, which is of dia 0.1 tolerance zone. Now we calculate the worst case condition. So the extreme conditions for this 40.5. So these are the worst case condition. So we are calculating the MMC concept for external feature of size. So in this case, what will be the worst case condition? What will be the virtual condition for this? So virtual condition is equal to the outer boundary of this shaft. For the maximum material condition, the worst case condition will be the outer boundary of the shaft will be 40.6. So this green circle is showing the outer boundary of the shaft, which is outer boundary. In this case, maximum material condition plus geometric tolerance value. So maximum material condition is 40.5 and the geometric tolerance value is of 0.1, which is dia
40.6. So virtual condition is equal to the outer boundary, which is 40.6 for the shaft. So this is the actual mating envelope. Actual mating envelope. Now, if this shaft is going to enter with the hole, let's say this is the part 2 with the hole. This is a hole. So the minimum diameter of the hole should be 40.6. Then only this shaft will enter into this hole. So that's why we are calculating the outer boundary for this shaft so that it can assemble with the mating part. In this case, it is hole. So this is the condition for the MMC concept for the external feature of size for the shaft. Now, we will understand the LMC concept for the external feature of size. LMC concept for the external feature of size for shaft. Now, again, in this example for shaft, this is MMC and this is LMC. But this here in the feature control frame, we have used the modifier which is LMC. So the dia 40.1 will be the LMC. Least material condition will be LMC is equal to dia 40.1. In this case also, if we see the tolerance zone, so dia 0.1 is the tolerance zone. If the part again manufactured at extreme boundaries, let's say this is the center, this is the center, this is the center, this is the center. So if the part is manufactured with worst case or the extreme conditions, what will happen? In this case, it will be the inner boundary. So inner boundary will be the size, but virtual condition. So in this case, you can see this is the virtual condition. So virtual condition is equal to the inner boundary for LMC. LMC concept, the external feature of size or shaft will be the inner boundary for LMC minus geometric tolerance value, which is 40.1 minus 0.1, which is 40 dia. So means this is the inside this shaft. So again, inside the material, when the concept is inside the material, this is inside the part, inside the material. So this is, you can see inside the material. So whenever it is inside the material, it is imaginary. Imaginary virtual condition. So it is imaginary and actual minimum material envelope. These concepts are very important. If you don't understand, do repeat these videos and try to understand these concepts, because this condition, in this condition, these are the virtual conditions which you have to remember and have to learn in a very detailed manner. Now, so this is the chart. So this is the chart which I have already discussed. We have discussed with the feature of size. So the part specification with the feature of size with no GD&T specified for the internal feature of size, for the external feature of size. So for inner, when this is the condition for internal feature of size and external feature of size. So inner boundary is the maximum material condition and outer boundary is the maximum material condition. Now feature of size with GD&T specified at RFS. So for internal feature of size, external feature of size at RFS, inner boundary is equal to the maximum material condition minus geometric tolerance value, and the outer boundary for external feature of size, outer boundary is the maximum material condition for plus geometric tolerance value. When feature of size with GD&T specified at MMC. So MMC for internal feature of size and MMC for external feature of size. So virtual condition is equal to inner boundary equals to MMC minus geometric tolerance value. For external feature of size, virtual condition will be the outer boundary is equal to MMC plus geometric tolerance value. Similarly for LMC, for internal feature of size and external feature of size, virtual condition is equal to for internal feature of size is equal to outer boundary LMC plus geometric tolerance value, and virtual condition will be for external feature of size will be inner boundary is equal to the LMC minus geometric tolerance value. So these are the some of the formulas for the worst case condition. So these are the worst case boundaries which is equal to. So these are the terminologies which you should be learning, and this is very, very important. So these are the some of the formulas which we understand, and with the help of these boundaries we design the functional gauges. So we only design the functional gauges with the help of these dimensions.
So for external feature of size, we have some virtual condition for both the internal feature of size and external feature of size is same. Now we understand. So again, if we take an example, similar example as we have taken at the starting of this session. So again, if we take the same example as we have taken in the starting of this session. So this is the example. So in this example, you can see that if we need to assemble the whole, this is the whole or the internal feature of size, and this is the pin, which is the external feature of size. So what will be the sizes? So in this case, the maximum material condition of the whole is MMC is 40.1 and the least material condition of the whole is 40.5. But in this case, now I have changed the sizes because we have to ensure the assembly. So in this condition, the least material condition of the whole is 39.5 and the maximum material condition of the whole is 39.5. So if we go with the worst case condition, so the worst case condition this whole can manufacture is the 40.1, which is the maximum material condition of the whole, and the geometric tolerance value of 0.1 at MMC, because MMC modifier we have used over here. So what will be the worst case condition? The worst case condition will be 40.1 minus 0.1. So the smallest whole. So the smallest whole will be the worst case condition. So MM's worst case scenario for this whole will be, worst case boundary will be dia 40 mm. Now, similarly, if we go with the shaft, so 39.9 is the maximum material condition because MMC modifier we have used over here. So 39.9 is the maximum material condition. 0.1 is the geometric tolerance value, and worst case boundary will be the biggest size of the shaft. The largest side of the shaft will be the outer boundary. So 39.9 plus 0.1. So dia 40 mm. So if the worst case boundary for hole is 40 mm and the shaft is 40 mm, so these both part can assemble with one another. So these both part can assemble. So this is how designers have to ensure and give such dimensions that the part at maximum material conditions with the worst case boundary can assemble with one another. So here the worst case boundary for hole is dia 40 mm and worst case boundary for shaft is dia 40 mm. So that's why we can assemble hole with pin. So this is how we have to take the dimensions. So this is all with the virtual conditions. We will, in the next discussion, we will be discussing the next topic, which is about the resultant condition. Thank you all of you. Hello everyone, this is Manish from Skillable India, and in today's session of geometric dimensioning and tolerancing, we are going to understand the resultant condition. So in the previous session, we have already understood about the boundary conditions. What is inner boundary, what is outer boundary, what is virtual condition, and in this session, we are going to understand in very detailed manner about the resultant condition. So when to use this resultant condition in geometric dimensioning and tolerancing, we will be discussing this in this session. So I am going to explain how to calculate the resultant condition. So by definition, resultant condition, if I will for internal feature and external feature, if I will be discussing this. So for a internal feature of size, the resultant condition is the variable value and the outermost boundary. In the case of internal feature, or whole, in this case, the resultant condition is the variable value and the outermost boundary. For external feature, in case of shaft or pin, the resultant condition is the variable value and the innermost boundary. So this is the case. In this case, so this is the example of hole, and this is the example of shaft. So in this case, we will understand first of all that we have for hole, we have the maximum material condition and the least material condition. In this case also, we have the least material. In case of shaft, we have least material condition 40.1 dia and the maximum material condition dia 40.5. Now, one thing we have to understand that when we are seeing that MMC, so when we have 40.5 in case of hole, first of all we are understanding for hole. So for hole, when at maximum material condition at 40.1 mm, the geometric tolerance what we have is 0.1 mm, 0.1 mm at maximum material condition. But as we move from maximum material condition towards least material condition, from maximum material condition to least material condition, we get the bonus tolerance. So in this case, as we move towards the least material condition, if this is 40.2, then we have the 0.2 mm. When we have 40.3, we have 0.3 mm. At 40.4, sorry, 40.4, we have dia for 0.4 mm. And at least material condition, which is 40.5, we have maximum tolerance, which is 0.5. So 0.5 is the maximum tolerance we have. So at tolerance zone at least material condition for this hole, we have 0.5 mm. So this is for the hole. In this case, when we move towards the maximum material condition to least material condition, at least material condition, when we have hole size is of 40.5 mm, so the tolerance zone we have is of 0.5 mm. So this is the case of hole. In case of shaft, now we will understand all the things with the shaft variation, with the example of shaft in this case. So for shaft, first of all, we will understand, or pin, at maximum material condition, because we have maximum material condition modifier in the feature control frame over here. In this case also we have maximum material condition modifier in the feature control frame. So at maximum material condition at MMC, which is dia 40.5, we have tolerance zone of dia 0.1 mm. As we go from maximum material condition towards least material condition, which is dia 40.1, so at 40.4 we have dia 0.2 mm tolerance. Dia 40.3 we have 0.3 mm of tolerance. Dia 40.2 we have 0.4 mm of tolerance. And at last, at least material condition, which is dia 40.1, we have maximum bonus tolerance. With the bonus tolerance, we have this at least material condition. So at dia 40.1, which is the least material condition for the shaft, the tolerance zone at LMC is 0.5 mm. So tolerance zone at LMC is 0.5 mm in both the cases. So how we will calculate the resultant condition with the definition we will understand. So this is the example. In further session, I will be discussing this in detailed manner. So what is resultant condition? Resultant condition is the single worst case boundary. In previously we have already understand virtual condition. It is the definition looks similar to the virtual condition, but in this case it is the single worst case boundary generated by the collective effect of the considered feature of size specified at LMC or MMC and the geometric tolerance value for that material condition. So as we have understood that there are four concepts for the resultant condition. So in this we have the maximum material concept for the internal feature of size. So MMC concept for the internal feature of size for hole, LMC concept for internal feature of size hole, MMC concept for the external feature of size pin or shaft, and the LMC concept for external feature of size pin. Okay, so for both the cases we will understand these concepts one by one. So the definition is very similar, but they are two different entities. Virtual condition is different entity and resultant condition is different entity. To understand resultant condition better, we will take different examples. So this is the similar example of hole. So this is for the MMC concept for internal feature of size hole. So we will understand first of all First of all, we will understand this is the for hole, the maximum material condition is dia 40.5 and least material condition is dia 40.5 and maximum material condition is 40.1. So when the tolerance zone is specified in the feature control frame is at maximum material condition. So if we see dia 40.1, which is MMC, the tolerance we have is 0.1. Now, as we move MMC towards LMC, LMC condition over here, dia 40.5 is the LMC, and we have the tolerance over here is 0.5 mm. So at LMC 40.5, we have the tolerance of 0.5 with the bonus tolerance. So in this case, at the least material condition, we will make the center, which is having a tolerance zone of 0.5 at LMC. So tolerance zone at MMC we will take, which is 0.5, and the LMC, this is the LMC. 40.5, the tolerance zone is for 0.5. So if we, in this case we take the extreme conditions, these are the extreme conditions. So these are the extreme conditions. We the holes, the tolerance. So in this case, you can see that the tolerance zone is the, if this is a hole. So in this hole, the maximum outer diameter, outer boundary will be the resultant condition. So in this case, you will see that resultant condition will be this green line, outer boundary. So resultant condition will be outer boundary, which is 41, because 40.5 plus 0.5 will be 41. So if we want to calculate the resultant condition, so this is the formula for outer boundary. LMC is 40.5, geometric tolerance value, which is 0.1 in this feature control frame, and plus bonus tolerance. So bonus tolerance over here is 0.4 mm. So which is dia 41. So this is the resultant condition for the MMC concept for the internal feature of size hole. So in this condition, if we are talking about hole outermost boundary, so again the concept come of the envelope principle. So this is the actual minimum material envelope in this case, because it is the outer boundary of the hole. This is the maximum resultant condition the hole can be manufactured. Now, one of the cases, so in this example we have a position when the part is produced at LMC. So initial situation is to have a hole of 40.5 dia exactly at the center, which is practically difficult to manufacture. Exactly at center, anything, it is very difficult to manufacture. So similarly we have the internal feature of size for hole. Okay, so this is the LMC concept for internal feature of size, which is hole. So when the hole is produced at maximum material condition, we get the bonus tolerance of 0.4 mm. In this case also, we have for hole, we have the least material condition and the maximum material condition. So this is MMC and this is LMC. So we are talking about LMC. So at LMC dia 40.5, we have the tolerance of 0.1 mm. So as we move to LMC towards MMC, which is dia 40.1, we have the tolerance of 0.5 mm. So in this case, 0.5 is with the bonus tolerance. 0.4 mm is the bonus tolerance plus 0.1. So it will become 0.5. So when the hole is produced at the maximum material condition, so this is the condition of MMC. So when the hole is produced at maximum material condition, we have tolerance zone at MMC is 0.5 mm. So this center exactly, which is manufactured, which is very difficult to manufacture at real center. So we are taking the extreme conditions if the hole is manufactured at the extreme condition of this dia 0.5. So at this point, this point, and this point. So we are taking 4 extreme conditions. So after manufacturing all the holes, you will see at maximum material condition the tolerance zone or at MMC will be, the tolerance zone at MMC is the tolerance zone at maximum material condition, which is dia 40.5, is geometric tolerance value plus bonus tolerance. So 0.1 plus 0.4 is 0.5 mm. So at dia 40.1 we have tolerance zone of 0.5 mm. Again, in this case you will see that the resultant condition is equal to the inner boundary. So this is the green circle you will see inside this green circle. So in this, resultant condition is the inner boundary. So inner boundary is equal to the maximum material condition minus geometric tolerance value minus bonus tolerance. So in this case 40.1 is the maximum material condition minus 0.1 geometric tolerance value, which is given in the feature control frame, and 0.4 mm is the bonus tolerance, which we have already calculated. So this is how if we reach at 39.6. So the inner boundary, so resultant condition is equal to the inner boundary of the hole. So this is the minimum size of the hole, maximum size of the shaft that can enter into this hole in this case. So this is the LMC concept for internal feature of size for hole. Now we will understand the MMC concept for external feature of size. So in this case, so here we have a maximum material condition. So MMC concept. So we are having in a feature control frame maximum material condition modifier. In this case, this is the in case of shaft. So this is the case of shaft or the external feature of size. So external feature of MMC maximum material condition will be the 40.5 and 40.1 will be the LMC. If the it is manufactured at least material condition, if the shaft is manufactured at least material condition, so least material condition of the shaft is dia 40.1. So at that time, what will be the tolerance zone? Tolerance zone at LMC will be the geometric tolerance value plus bonus tolerance. In this case, 0. Plus 0.4, 0.5 mm. So 0.5 mm dia of tolerance we are having at LMC dia 40.1 mm of shaft. So now if we calculate, so this is the least material condition and we have the tolerance zone at least material condition is of 0.5 mm. Now if we take the extreme conditions, so after creating the condition, you will see the inner boundary. So in this case, MMC concept for external feature of size for shaft, MMC concept for shaft will be the inner boundary. So inner boundary in this case will be the actual minimum material envelope. So how we calculate the resultant condition is equal to the inner boundary is equal to the LMC, which is 40.1 minus geometric tolerance value, which is 0.1 minus bonus tolerance, which is 0.4. So we get dia 39.6 mm. So this is the inner boundary or the resultant condition at MMC concept for external feature of size shaft. Similarly, we take the LMC concept, resultant condition, not the virtual condition, it is raw resultant condition we are calculating. So LMC concept for the external feature of size shaft. So now we will calculate LMC. So in this case also MMC will be this and LMC will be this. So at least material condition we are seeing what you want to after MMC for the shaft, which is dia 40.5. The tolerance zone at MMC will be 0.5 mm. Okay, so tolerance zone at MMC, which is dia 40.5, is equal to the geometric tolerance value 0.1 plus 0.4 bonus tolerance. We get the 0.5 mm. Now in this case also, so this is the maximum material condition for the shaft and we have the maximum material condition, we have tolerance zone of 0.5 mm.
So after extreme conditions, in this case you will see this is the outermost boundary. So this is outer boundary, which is resultant condition is equal to, in this case, resultant condition is equal to outer boundary, which is equal to maximum material condition, which is dia 40.5, geometric tolerance value 0.1, bonus tolerance 0.4 is equal to dia 41. So in this case, dia 41 is the resultant condition, and this is the actual mating envelope. So actual mating envelope. So this is the maximum size the part can, this is the maximum size that the hole can enter into this actual mating part, actual mating envelope. So these are the formulas which we have already discussed. These are the four conditions. So specified at MMC, internal feature of size, external feature of size. So these are the formulas which everyone should remember for the resultant condition. For internal feature of size at MMC is the outer boundary, which is LMC plus geometric tolerance value plus bonus tolerance. And similarly for the external feature of size, we have formula the LMC minus geometric tolerance value minus bonus tolerance, which is equal to the inner boundary. And similarly for the specified at LMC for internal feature of size and external feature of size. So this is the very important terminology which we regularly use in geometric dimensioning and tolerancing, and then how we calculate the resultant condition is very important. So this is all for today's session of resultant condition. In the next session, we will discuss the different topic of geometric dimensioning and tolerancing. Thank you everyone.
Hello everyone, this is Manish from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to learn about the feature control frame. This is the very important part because in each and every engineering drawing, wherever we are specifying the for the machinist or for the manufacturing department, we are going to use the GD&T symbols. So while using GD&T symbol, we cannot use like this. So for that, we have to use this feature control frame. So this feature control frame is very important topic in GD&T. Now we are going to start. So first of all, in this session, I am going to give you a detail of how to place geometric dimensioning and tolerancing symbols into the engineering drawing. So the feature in the feature control frame, the definition. So feature control frame or FCF is a rectangular graphics that represent specified dimensions information for one or more features. It usually appears on a blueprint or an engineering drawing or a CAD file to define the tolerance specification for a specific dimension type. So the feature control frame is a rectangular box that is particularly divided in multiple compartments within which geometric characteristic symbols, tolerance value, modifiers, and datum references are placed. So the datum references are placed. So in this example, so this is the example for the feature control frame. So whenever we see, so this is the feature control frame. So this is one of the example we are taking. So in this, there are multiple compartments you can see in this. And why it is important? Because whenever we provide the geometric tolerance value, we will provide into this geometric feature in this feature control frame. So first of all, before starting this geometric first compartment, so this is the first compartment. First compartment is always given for the geometric characteristic symbol. So out of 14 geometric characteristic symbol, any one symbol will be in the first compartment always. So you can use any of the 14 geometric characteristic symbols. So this is the first. So geometric tolerance characteristics. So first compartment is given for the out of 14 geometric characteristic symbol is placed in this feature control frame. It can be straightness, flatness, circularity, cylindricity, all these total 14 geometric characteristic. Out of 14, any of the geometric characteristics we can give into the first compartment. So this is the for the symbol of geometric characteristic. Now this is in the second compartment. In the second compartment, it is first of all, this is for the tolerance zone. So second number, this is for the tolerance zone. So whatever tolerances we have to write, we will write over here to shape tolerance zone shape modifier. If we have not given any symbol in this, so then it means that the tolerance zone can be, if we are not provided any of the symbol like diameter. In second compartment, you can see tolerance zone shape modifier. When we give the symbol diameter, let's say here we are using symbol diameter. This is the symbol of the diameter. Out of diameter, we can also use square. It means the tolerance zone is square shape. When if we are using out of this like this symbol, so it means we are the square the tolerance zone is in square shape. And if we are using s diameter, out of this, if we are using like this symbol, so it means the tolerance zone is in a spherical shape. So whatsoever we can use the symbol over here, so it just represent the tolerance shape. Now, if there is no shape modifier, it means if there is no modifier, direct the tolerance value is written. What does this mean? If there is no shape modifier, if this is not available, let's say, so what does this mean? It means that the tolerance zone is two parallel lines or two parallel planes. So diameter symbol is means the tolerance zone is in cylindrical form. If we are using diameter symbol, so it means the tolerance zone, which is the tolerance zone, so it is in cylindrical form. So that's why we are using the diameter symbol. Now, or we can give a you can see that in the second compartment only, in the second compartment only, the third position. So this is the third position. Previously we are talking about second position, and first we have talked about the first compartment first position. So in the second compartment, third position is given for the tolerance zone size. So this is the tolerance value, geometric tolerance value. So this is the geometric tolerance value. Whatever tolerance we are providing, we will write in the third position. So the numerical value given is the in the feature control frame is nothing but the tolerance zone size. Usually we call it as tolerance value or the geometric tolerance value. Now we come up to the fourth position in the second compartment. So this is the fourth position in second compartment. In the second compartment, fourth position, material condition modifier, size modifiers. So in the fourth one, we provide the modifiers is used to modify the tolerance zone size. So to modify this tolerance zone, we use the modifiers. I will write down here to modify the tolerance zone. We use modifiers. What does this modifier do? So we can apply the geometric tolerance to a regular feature of size only. So whenever we can apply geometric tolerance, we can only apply to a regular feature of size. So regular feature of size only we can provide the geometric tolerance value. Regular feature of size. And we can modify the tolerance zone size also. So this size we can modify. How we can modify? By using modifiers. So by using modifier, we get bonus tolerance. So this is how with the while using the modifiers, we can use the bonus tolerance. So that's how it is called the modifiers, which can modify the size tolerances. What type of modifier we can use? We can use maximum material condition. So this is the symbol M we have used over here. You can see. So we can use the modifier maximum material condition. We can also use the modifier least material condition if L shape. So here we can write down L and the round. So this is called the least material condition. Then we can use the projected tolerance zone. If we are using P means projected tolerance zone. We will in further sessions we will understand what is projected tolerance zone and how we can use into the engineering drawing and why we are using the projected tolerance zone and some more topics like fixed fastener formula and another some more topics are there. So that is very important. So we are also using the projected tolerance zone. Then we are using the tangent plane. T in a circle, we use this symbol for the tangent plane. Statistical tolerance zone. So ST and circle with the inside the circle. So we use this for the statistical tolerance zone. Then we use F symbol round the circle, which is for the free state. So in the starting, I have already told you about the free state, that why we use free state. So non-rigid parts, we use the free state condition like rubber O-rings or gaskets. So for those parts, we use the free state condition. So modifier frequently used when the tolerance geometric control is applied on a regular feature of size only. So whenever we use the geometric control which is applied to a regular feature of size. Apart from these, there are also there are multiple modifier. So these all type of modifier we use into the fourth compartment. Now we move towards the third compartment and fifth position. So this is compartment is called the third compartment and this position is called the fifth position. So whenever we use the feature control frame onto a form control. So whenever we use feature control frame onto a form control then there only be I will say are two compartments. So only two compartments will be there whenever we will provide the feature geometric tolerance to a form control. In form control there are four characteristic symbol: straightness, flatness, circularity, and cylindricity. Whenever we use the form control, only two compartments will be there. First compartment and second compartment. These three compartments will be not be there. But whenever we use the geometric tolerance to a related feature, then we can have a minimum of three compartments. Like we can have three compartment, this compartment, this compartment, this compartment, and maximum of four compartments in the five compartments in the feature control frame. So in the third compartment, always the primary datum. So this third compartment will be for the primary datum. So this third compartment is for the primary datum. And in the fifth position, this is the symbol for the primary datum. Right now we are using. So onto the drawing in the datum identification. So whenever there is a datum identification, let's say this is a part. So in this part, it is specified like this, that this surface is the datum A. So always this datum modifier is all datums are always provided onto the engineering drawing. So primary datum should be selected on a plane that contains feature that are critical to the function or inspection of the feature. Think mating surface. It must have at least 3 points or 3 degrees of freedom of contact with the part which are not in a straight line, a plane to hold the part. So to fix the part onto the fixture, So first of all, we already know the concept of the 6 degrees of freedom. If we don't know, in the coming sections, I will tell you that how 6 degrees of freedom works. And with the help of 6 degrees of freedom, we came to a part from free state to a we hold in such a way that with the help of 6 degrees of freedom, we lock all the 6 degrees of freedom, 3 rotational and 3 translational movements. So with the help of these, we lock all the 6 degrees of freedom to hold the part, to stop the part movement. Now, in the whenever a datum is considered, that would be the first reference for measurement. So datums are the, I will say, datums are to be considered, that would be the first reference. So in the primary datum, these are the first reference for measurement. The order of the datum is important. Whatever the order. So these 3 compartments are for the primary datum, secondary datum, and tertiary datum. So order of precedence is very important. Order of precedence. We will understand this order of precedence in a detailed manner. So order, that primary datum, it will be the first, secondary datum will be second, and tertiary datum will be third. So the primary datum usually have 3 places to fix 3 degrees of freedom. So primary datum holds to fix 3 degrees of freedom, or 3 movements. It locks 3 movements, primary datum, to hold the part. Now we will move on to the concept of the boundary condition. So the sixth position in the third compartment, whenever the datum we consider is a regular feature of size. So this datum is a regular feature of size, then we can use the modifier over here. So in this case, we can use maximum material boundary or the least material boundary modifier. So this M symbol you will see over here is maximum material boundary, MMB, or least material boundary. So the concept of maximum material boundary condition is very useful, since it can allow much easier assembly conditions. As the datum feature departs from the MMB, it can allow a shift so that the positional tolerance pass. When the regular feature of size is considered to be a datum, MMB or LMB modifier can be applied. So we can apply MMB, maximum material boundary, or least material boundary modifier when the regular feature of size is considered to be a datum. Whenever regular feature of size is considered to be a datum, we can use MMB or LMB modifier can be applied. If now we come into the 7th position. So this is the 7th position in the 4th compartment. If required, we can use the secondary datum. So this will on to the right of the primary datum in the 4th compartment. So again, this letter correspond to the feature somewhere on the part on the engineering drawing, which will be marked with the same letter, which is B. In this case, we are using B. So whenever symbol like this is given, so it is denoted somewhere on the engineering drawing. So this letter denotes for the secondary datum, and this holds or fix 2 degrees of freedom. Now finally, we secondary datum should be perpendicular to the primary datum and have a minimum of 2 points or of contact, or 2 degrees of freedom line. The datums often establish the orientation of the second axis. So in the second compartment, it is for the secondary datum, which is always perpendicular to the primary datum, and it holds minimum of 2 degrees of freedom. Now we have in the 5th compartment, we have the tertiary datum. So finally, in the 5th compartment, we have tertiary datum. If required, this would be at the 5th end of the 5th compartment. This letter again correspond to the feature somewhere onto the part, which will be marked by the letter C. So this is also denoted by letter C like this. So it is denoted somewhere onto the engineering drawing with the help of this mark. And this locks 1 degree, 1 point of contact or 1 degree of freedom. So tertiary datum should be perpendicular to both primary and secondary datum, and must have the only form 1 point of contact. So a third datum feature contact the third plane of the datum reference framework. So this is very, very important. So this is all for the feature control frame. In the next discussion, in this all the feature control frame we have already discussed. So these are the entities, or I will say items, that can be used in the feature control frame. In the second session, we will use one example. So in the feature control frame, whenever we want to use the geometric tolerance onto the feature, let's say whenever you want to use the geometric tolerance onto a feature, so this surface is considered to be a feature. This surface is considered to be a feature. Then the feature control frame leader. So then the feature control frame leader. So this is the leader we are using over here. Leader arrow directly pointing onto the surface of the object. So in this case, this is a form tolerance. Straightness we are using over here. So in this compartment, whenever we use form tolerance, we have only two compartments with the tolerance, geometric tolerance characteristic symbol and the geometric tolerance. So only two compartments we are here. So, or we can show it onto the extension line over here. Whenever we want to use the geometric tolerance to a feature of size, whenever we want to use it as a feature of size, so what we do is then the feature control frame. So feature control frame, this is a feature control frame. Feature control frame leader line. Leader arrow should be in line with the dimensional arrow like this. So this is a feature of size. This is a feature of size. Whenever this arrow is pointing towards the feature of size, just below dimension like this. So this is how we place the feature control frame onto a feature of size. Both things are different. Whenever we are using like this, it is a feature, surface is a feature, and these dimensions are called the feature of size. Regular feature of size, irregular feature of size, we have already understand. If we talk about the regular feature of size, so anything we can measure with the help of vernier caliper, it comes under the feature of size, the regular feature of size. So just below dimension like this. Now in this example, you can see this is all about how to place geometric symbols in the engineering drawing. So this is the leader line, if you will say. So it is just placed between, so this is a regular feature of size. In the regular feature of size, we are using this dimensions like this. So this is the positional tolerance symbol, characteristic symbol we are using over here, positional tolerance. This is the tolerance, 0.1 is the tolerance. M under circle is the modifier, maximum material condition. This is a primary datum, secondary datum, and tertiary datum. So in this, you can see that these are the symbols we are using over here. This is for the primary datum, this is for the secondary datum, and this is for the tertiary datum. So in this, you can see that the planar datum, center plane, axis datum. So these are how we provide the tolerances to the into the drawing. So always we provide the primary datum, secondary datum, and tertiary datum. This is for the hole and this is for the shaft. So this is how we use the feature control frame. So this is all about the feature control frame. In the next discussion of GD&T, we will discuss some other topic. Thank you everyone. Hello everyone, this is Manish from Skillable India, and in today's session of geometric dimensioning and tolerancing, we are going to discuss very important key terminology, which is about the controlled radius, where we use controlled radius and why it is important to learn about controlled radius. With the help of definition, we will understand this. The controlled radius is a variation of radius. So basically we are talking about the control radius, which is a variation of radius. Its dimension, the size of a circular feature using the radius length. So here we are talking about the fillets or the round which we provide into the design. But it also gives an additional requirement that the surface of the contour must be a fair curve. So uh, whatever round or fillet we are providing, it must be have proper curve. What we have sometimes that we do not get the proper radius when we provide the radius to avoid the cis concentration. So this means that the surface must be continuous without reversals. So just showing with the help of one example we will discuss. So whenever we have a part like this, if I draw one part, let's say first of all in the first example we are discussing with the first part, and we have provided a fillet radius at this center at this part. So let's say if we have given over here r10 plus minus 0.1. So if I have provided the dimension, which is the radius 10 plus minus 0.1, which is the 0.1 is the tolerance over here. So what can happen that this to avoid what we usually avoid with the while giving the fillet radius to the part, whenever we have a sharp edges, so there will be a cis concentration. So at the sharp edges, whenever there is a edges like this, so always there is a cis concentration. To avoid this cis concentration, we usually provide the fillet to eliminate this concentration. But while applying this fillet radius, so for this, after let's say after manufacturing, it should lie within the boundary. It can be like this, and like if I will make, so here you can see that it can be 10.1 or 10.1, or it can be 9.9. So in between this, it can be anywhere in between this radius. But sometimes what we actually face this problem, that after manufacturing the part, after manufacturing this radius, what we get, what we get is the this type of part, in which you can see there are multiple reversals are there. There is a zigzag shape into the part. It is within the tolerance zone, but it is having zigzag shape. So to avoid this, you can see this zigzag shape is also having the sharp points. So these sharp points also contains the cis concentration. So we are giving the fillet radius to avoid the cis concentration. So what we do over here is, now the main intention of giving fillet radius is to remove the cis concentration, but which is not taken care in this case. So in this case, you can easily understand this thing is not taken care. So here again, we have some sharp edges, because of which we are not fully able to eliminate the cis concentration. So whenever the application called for very smooth surface, so whenever there is a smooth surface requirement, what we do is, we can add C in front of the R. So we provide the C in front of the R. So this shows the controlled radius. So this, whenever we are writing over C in the engineering drawing before R, so it means we are saying to the manufacturer that you have to control this radius. Surface must also lie within the tolerance zone, within the boundary of the 10.1 and 9.9. But the flats and reversals are not allowed. So these flats and reversals are not allowed with the smooth surface within the boundary by which we are able to remove the cis concentration. In the second example, when we apply the controlled radius, whenever we apply the controlled radius to a part, so to avoid the cis concentration, the symbol CR, so in front of R, 50 plus minus 0.5, we write it down this C over here, which is showing the controlled radius and is placed before the size dimension. So this C is placed before the size dimension. Now, the difference between the radius and the controlled radius is in the contours of the machine feature. So this is the, you can see in this example, that there are a lot of contours are there, like this contours are there. You can see this contours, although they are within the tolerance zone, within the plus minus 0.5, but still while the point along the radius dimension surface must only fall within the tolerance zone. Points along a controlled radius, when we provide not R, we provide C over here. So the surface must fall within the tolerance zone and a continuous arc. So it will lie between this part. So it will lie within the boundary of the tolerance zone, within the boundary, and it will have a smooth, continuous arc. Continuous arc. So this is very, very important. So whenever we require a smooth continuous arc, we provide C for the controlled radius before the size dimension. Controlled radius. So this is all about the controlled radius in the geometric dimensioning and tolerancing. For engineering drawings, this is very important to control the radius and have a smooth continuous arc and remove the cis concentration. Thank you all of you. In the next discussion, we will have some different topic. Thank you very much. Hello everyone, this is Manish from Skillable India, and in today's session of geometric dimensioning and tolerancing, we are going to understand the very important GD&T geometric symbol or the geometric tolerance, which is about the straightness. Okay, so straightness tolerance basically comes under the form type. Okay, so it basically controls the form of the part. Okay. So in straightness tolerance, first we will understand the help of a definition. So the symbol of the straightness tolerance will be like this. So whenever there is a straight line, okay, we are using in the first compartment of the feature control frame, then it is a symbol of straightness. Okay. So straightness is a two-dimensional GD&T callout. So first of all, whenever we are using straightness tolerance, so it is a two-dimensional GD&T callout that controls the straightness of the part feature. Okay. In this case, you can see this is a part, and this part, this surface is having arrow line. Sorry, this is having arrow line. Okay. So it's a feature control frame. So in this feature control frame, it is this feature control frame is arrowing towards the surface. Okay, so surface is considered to be a part feature. Okay, so this is how we provide the geometric tolerance straightness to a part feature. Okay, whenever we are putting arrow towards the surface or towards whole surface or any other surface, so we are providing the straightness tolerance to a part feature. No axis can be perfectly straight. Okay, so here no axis can be perfectly straight. Let's say if there is a round part. Okay, if the part is having in a round profile. Okay, like this, we will understand further with the example. Okay, so the axis at the center of this cylindrical part is not cannot be perfectly straight. Okay, so to control this axis straightness, we give the straightness tolerance to a feature of size. So basically, we will discuss this thing. So the goal is to ensure it is straight enough for the application. Okay, we already know that anything which is manufactured by the machine cannot be perfectly in the shape. Okay. So control this that its application do not hurdle or the axis of the shaft or the pin should be enough straight that its assembly or the application we can ensure. Okay, so this call out set a standard on how straight a feature must be along its length. Okay, so along its length, we are talking about if we are talking about axis, so we are talking about the whole length of the part till the axis is there. Okay, so if we are talking about this part, so we are talking about the whole length of this part. Okay, so this is very important. Straightness can control two very different types of functions. Okay, straightness can control two different type of function. It is the only call out that can control either the line or a surface or a feature of size. Okay, so what does this mean? First of all, straightness can be provided to a feature. In this case, this is the first case. Okay, so this is the case first when the straightness is a straightness symbol is applied to a feature. To a feature. Whenever you can see over here also straightness tolerance applied to a feature. Okay, so whenever the leader line is pointing towards the surface, so it means that we are providing tolerance to a feature. Okay, in this case, this is the second example. So the straightness applied to a feature of size or axis. Okay, so whenever let's say here we are using the word dia. Okay, so whenever we are applying the tolerance, straightness tolerance to a axis. Okay, so in this case, this red line over here is the axis. If we are providing this and the leader line, in this case, leader line will be perpendicular or the parallel with the dimension. Okay, so whenever we provide the straightness tolerance to a feature of size, we will show the tolerance feature control frame with the dimensions. Okay, and whenever we apply the straightness tolerance to a feature, we will pointing towards the surface, towards that feature for which we are providing the straightness tolerance. Okay, now in the first in the feature of size, whenever we provide the straightness to a feature of size, we can use the maximum material condition and the least material condition, because we cannot apply maximum material condition and least material condition to the feature, but we cannot apply onto the feature, but whenever there is a feature of size, to the material condition modifier we can provide. So in this case, we can provide the maximum material condition or least material condition to the part. Okay, so in the next example we will understand with the same example that how we can do this. Let's say, so first of all, first we will understand straightness applied to a feature surface. Okay, so when we apply the straightness tolerance to a feature, when we apply this call out to specify the surface straightness, the tolerance zone forms a total white zone above and below the ideal surface position and controls any deviation. Surface straightness controls the form of a line anywhere on the surface and the has two type of applications. The first type, it is a flat surface such as a face of a cube. Okay, and in this case, this is a cube. Okay, so this surface is straightness. If we are seeing from the right side, this the flat surface. Okay, so the straightness can be at single line. Okay, straightness can be a single line at any point. Okay, so it can be a straight line. So if we first type, if we understand, so in a detailed manner. Okay, so let's say I am taking an example over here. This is a part. Okay, and this part we have provided the size dimension which is of 50 plus minus 0.1. Okay, so when this part is manufactured, after manufacturing this part, we can have the axis, let's say, like this. Okay, So and we take the height between the peak and valley. Okay. So if we take the peak and valley, so this is the peak, which is the maximum we can allowable deviation can have, and this is the valley, which is the minimum. Okay. So in this case, this distance we can have plus minus 0.1. So here we can have the deviation of 0.2 mm over here. Okay. So the difference cannot be more than 0.2 in this case, which is the size tolerance. Okay. So this is what rule 1 tells. The rule 1 tells that we should be within the tolerance zone. Okay. So now if you want straightness control, then what we achieved from rule 1, then I have to use the straightness tolerance over here. Okay, so if I use the straightness tolerance, so after applying straightness tolerance to a feature, okay, so because we are talking about the feature, so can be applied in two ways: applied to onto a surface and applied onto a axis. Okay, so first we will discuss how to apply straightness onto a surface, and we will go to then we will understand about the axis control. So first of all, if you want to control the straightness of a surface, then what we have to do? Then the leader length should point towards the like this. Leader length will follow straightness and 0.1. Okay, so this is how we can apply the feature control frame onto the space. So what we want to control and probe leader line with the feature control frame. Okay. Now what we are having over here, in what the cases we are making. 1 second, I will let you know. After applying the feature control frame, okay. So the geometric tolerance value should not be less than the tolerance. Whenever we are applying any geometric tolerance value, it should be not less than the tolerance value, size dimension. Okay, so here the size tolerance is 0.2. So here we are using 0.1 as the geometric tolerance. Okay, so now what we have, okay, so from here to here we have size dimension of 50.1. Okay, and from here to here we have the size dimension, what we have is 49.9. Okay, now this is 0.2 mm of tolerance. Now anywhere between this, okay, so it can have like this, anywhere in between. But the thing is that the peak and valley of this profile of after manufacturing. So this is the case of after manufacturing. This is never be more than geometric tolerance. It should be within the 0.2 mm of tolerance, and it should be always, I will say, 0.1 mm. Okay, it can be like this in a straight line, or the situation can become that it cannot be straight line. Let's say it can be like this also in a taper line. Okay, but if we are providing the straightness to a uh, feature, okay, in this case also it will be mentioning that the peak and valley should be within the tolerance zone. So this peak and valley should not be more than 0.1, although it will be within the 0.2 mm of tolerance zone. Okay, 0.2 mm tolerance. If it is in a taper shape, it will be acceptable. Okay, so where the maximum limit of is this 0.2, and the geometric tolerance is 0.1. If the part is manufactured in a taper shape profile, so it will be always in the within the tolerance zone as per the rule 1. Okay, so here you may have the end up with the taper with the minimum size of the 49.9 and maximum size of the 50.1, which is allowed. But the surface peaks and valley, the high points and the low point should not be more than 0.1. So this is the straightness control onto the surface. Okay, straightness control onto the surface is a two-dimensional entity. I have already told you, and tolerance zone is two parallel lines. Okay, so whenever we are talking about the tolerance zone, whatever tolerance zone like this, if we are it is So it is always a two parallel lines. Okay. So this is how they are controlling the 0.1 over here if we are not understanding. So it is in a taper shape. But it will always be in a rule 1. Always act. Okay. So rule 1 always says that the part should enter into the actual mating envelope. Okay. So envelope is the maximum limit MMC condition, which is the maximum material condition of the part. Okay. Since we are applying straightness onto a surface, it is a feature control, and we will not be able to apply the MMC condition. So whenever we are applying feature straightness tolerance to a feature, so we are not able to apply the MMC or and LMC condition. Okay. Now we will see. Now I will remove this. Okay. Now what we will see in the next example, we will apply the straightness tolerance to a we will apply now we'll to the straightness of the axis of the shaft. Okay, so now we will apply the straightness of the axis of the shaft. In this case, this is the leader line. It is showing to the part axis. Okay, to control the straightness, to have the in the second part. Okay, so straightness applied to a feature of size. In this case, we are applying the to the axis. Okay, straightness tolerance to the axis. Since you can see this that in this case where we have provided the tolerance, we have provided in this example to the feature of size. Okay, so this is in 2D shape. We have provided the to all the length, okay, of the part. We have provided the straightness tolerance to the feature of size. On the axis of the shaft must be within the cylindrical of the dia 0.1. Okay, so here we have used the diameter 0.01. So this diameter, okay, so here we have 0.1. Okay, so if we remove this 0 from here, okay, so this 0 is removed. Only 0.1 at maximum material condition is there. So we have the 50 plus minus 0.1. So the maximum we have is maximum shift we have 0.2 mm. Okay, and the minimum shift we can have is of 0.1 mm within the cylinder. Okay, so in this case also, if the after the manufacturing this part, so we have 0.2 mm of tolerance zone, but after manufacturing the part can be end up like this. Okay, its axis is tilted. Okay, so it should be within the tolerance zone. So what we will do over here is that it should be within the tolerance zone. So we will make two straight lines to form this axis in the tolerance zone. Okay, I will rub this because it is not proper. If we will see this in a two parallel planes, okay, parallel lines we will provide. So now we have give the straightness to the axis. Okay, so in this case we have provided the tolerance zone. In when we apply the straightness tolerance to a feature of size, we can apply the maximum material condition and minimum material condition. Okay, so we will give the call out over here as the feature of the size controlled, and then get the three-dimensional entity. Okay, so in this case you will see that this cylinder of tolerance zone. So this is a cylindrical tolerance zone. Okay, so this is a cylindrical tolerance zone over here, and this is a three-dimensional entity. Whenever we apply the straightness to a feature of size, then we can apply the MMC and the LMC conditions. So here in the example, I have given the maximum material condition modifier, which tells that whenever the shaft is at the maximum material condition, okay. So if the shaft is manufactured at 50.1, okay, So this shaft is manufactured. What will be the MMC condition? MMC condition for this shaft will be 50.1 and LMC condition will be 49.9. Okay, so when the shaft is manufactured at 50.1, the tolerance zone will be 0.1. Okay, so whenever shaft is manufactured at 50.1, which is MMC, so the tolerance zone will be 0.1. When we move from MMC towards LMC, okay, let's say when it will be 50, we have 0.2, and when we have 40.9, we have 0.3 mm of tolerance. Okay, so as we move from MMC towards LMC, we get more tolerance zone. Okay, so the worst case possibility to manufacture the shaft is at LMC, which is 49.9. When it produced at 49.9, then the geometric tolerance will be 0.3 mm. Okay, we get increase in the tolerance zone. This is about the straightness tolerance. Okay, so whenever we apply the straightness tolerance to a feature of size, we can apply the maximum material condition and the minimum material condition modifier, and this is how we can get the more tolerance with the help of this condition modifier. Okay, so after manufacturing, we can have like this. Okay, so whenever this axis always be within the tolerance zone. Okay, within the this cylindrical tolerance zone, this axis should be always be within this. So this is all about the straightness tolerance. Okay, so if I summarize the whole session, so straightness can be applied two ways. Straightness can be applied to a feature which is considered to be a surface, and straightness can be applied to a feature of size which is the axis. Okay, so whenever we apply to a feature, we cannot use the material condition modifier or the MMC condition or the LMC condition. But when we apply to a straightness tolerance to a feature of size, which is the x, we can use the maximum material condition and least material condition modifier. So this is all about the straightness tolerance. Thank you. Thank you all. Hello everyone. So this side Manish from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to discuss the second geometric tolerance under form control, which is flatness. So why flatness tolerance is important? Step by step, how we can calculate the how we can give the flatness tolerance to a feature or a feature of size. One by one, we will see. So first of all, we will understand the definition. The flatness tolerance. Many application needs parts with a flat surface. In case of designing molds or we are designing a press tools. So for that, many a times we require flat surfaces. So what we use in for the flat surfaces, we use the grinding wheel to flatten out the surface. So flatness is the most important thing which we required in a designing also, in manufacturing also. So no surface is perfectly flat. Whatever we can do, we are doing it with the machining, but it is very I will say it is very tough to get the perfectly flat surface. But using GD&T, we can develop parts with a surface that is flat enough for the application. So here it is important that the parts should be enough flat that what we are ensuring for the application, it is perfectly workable. So that's why we need to ensure that the flatness should be within the tolerance zone. The flatness callout controls the uniformity of a surface or a median plane. So here we are talking about median plane. This word is very important in flatness. With the help of 3D overview, I will tell you how these median planes are important. Median planes are as needed. It defines two parallel planes. On either side of the flat surface. As the tolerance zone or for the surface, all the points of the specified surface must lie between these two planes for part approval. So in case, let's say, in this is the example. So first of all, flatness can be applied to a feature, and flatness also can be applied to a feature of size. So in this case, you can see that flatness applied to a feature, which is a surface. Whenever it is same as straightness, as I have already told you, that whenever arrow line, this leader line is pointing towards the surface, that means we are providing tolerance to a feature. And whenever the leader line is parallel, or the I will say in line with the dimension line like this, means we are providing tolerance to a feature of size, FOS. In this case, we are providing to a feature. So two ways we can provide the tolerance zone. So here we have an example. In this example, you can see this is the example. So this is the example of a feature with part is having dimension of 10 plus minus 0.5. So here the dimension is provided 10 plus minus 0.5 mm. Since I haven't applied the geometric tolerances till now, rule 1 is applied. First of all, the rule 1 will be applied automatically. So after manufacturing the part, let's say after manufacturing this part, what we can end up like, let's say, this type of surface we can have. So end up the part like this, the peak and the valley. So this is the peak. At the top of the part will be the peak, and the bottom, this is the valley. So the difference in the difference is the flatness error. So whatever this distance will be the in our case we have provided 0.2 flatness, or say 0.5 mm. 0 plus minus 0.5 mm is the provided. So 1 mm, very coarse tolerance I have taken over here. So 1 mm will be the maximum this can happen. Maximum this can happen whenever we are manufacturing, because we are taking plus minus 0.5. So 9.5 and 10.5. So upper limit will be the 10.5 and lower limit will be the 9.5. So total tolerance zone we have over here is 1 mm. So if you refine the flat surface, let's say if we are manufacturing this part, so what will happen? So what will happen if I will remove this? So after manufacturing, we should be getting out from the rule 1. Then we have to apply the flatness tolerance. Similar, it is similar to the straightness only, but what is different is this is a 3-dimensional surface. So when we apply it to this surface or a center plane, so if I will give you an example of this, if I will give you an example with this, so you can see this is a part and we required flatness for this surface of this part. So what we will do over here is, first of all, we will select the tolerance zone. So tolerance zone, here we have the median planes. So if I will just to showcase you, these are the median planes. So these median planes are the whole onto the whole surface. So this is the difference. This can be the difference between which is 10.5 and 9.5, which is 9.5 is this plane and 10.5 this plane. So we want flatness to be within this tolerance zone. So whenever we provide the tolerance, in this case, whenever we provide tolerance to the whole planar surface, what we look like, what is this looking like? The part can be, so first of all, so part can be like this. Part surface can be like this. So the peaks and valley in this part should not be more than 0.2 mm, because the geometric tolerance we have applied is 0.2 mm. So although we have the dimensional of 1 mm, but still when we provided the geometric tolerance value, it is the 0.2 mm. So it is within 1 mm, within 10.5 will be the upper limit and 9.5. But the point is that the tolerance zone, the peaks and valley of this surface will not be more than 0.2 mm. It is within this, but anywhere between this, but it is not, the peaks and value not be more than 0.2 mm. It can be like this also. And one more case can be occurred in the next profile. So here we are applying the flatness applied to a feature. This is what we are understanding in the previous slide. So in this case also, this is the case which we have understand over here. The peaks and valley is should be not more than 0.2 mm. So this profile like this should be within the 0.2 mm. It can have in range of 10.5 and 9.5. So this is very, very important. While straightness has two parallel lines, in the straightness tolerance, it is two parallel lines because it is a two-dimensional entity, tolerance zone. In this case, the flatness tolerance zone is formed as a two parallel planes because this is 3D equivalent surface. The flatness tolerance zone is the volume between the two parallel planes, which I have already told you in the 3D view. So the distance between the parallel planes is the stated flatness. So whatever the two parallel planes, so between that we are getting the flatness control tolerance value. The surface being controlled must lie within the volume defined by the tolerance zone. So one condition is this. The other condition can be this. So in this case, you can see that 10.5 mm is this and 9.5 mm part this. It can be taper. The flatness can be in taper, but still these peaks and valleys are not be more than 0.2 mm. So the distance between the peak and valley will always be 0.2 mm. Although this, if I will take this point and this point, this range is 1 mm. This range is 1 mm because 10.5 minus 9.5 upper limit minus lower limit is 1 mm. But still the peaks and valley should not be crossing the tolerance value of 0.2 mm. Okay. So peaks and valley are defined. Although this is into the taper, it is acceptable, but the peaks and valley should not be more than 0.2 mm in this flatness tolerance. So this is the condition 2. So this is the second condition. Now we will understand that when flatness applied to a feature of size. Whenever flatness applied to a feature of size, flatness on a derived median plane, DMP. So derived median plane, this word is very important, which I have already shown you in the 3D view. Flatness on a DMP is another way of using flatness in GD&T. In this case, the flatness symbol is applied to a feature of size. So in this case, you can see that we are applying this flatness symbol to a feature of size rather than a surface. The control feature is the virtual DMP of the reference feature of size. This has many practical applications. Most notably is the stacked components. So we are talking about the stacked components in which two components are stacked with one another. Another point to bear in mind when using the flatness symbol of a derived median plane DMP is that the maximum material condition MMC and the least material condition LMC modifiers are also applicable to it. So the flatness callout in the figure below condition contains the MMC modifier symbol. So in this case, you will see that whenever we are providing tolerance to a feature of size, so we can have the maximum material condition modifier or the least material condition modifier. So in this case, we are providing flatness to the feature of size. So you can see that the flatness symbol is applied to a modifier is given to the tolerance zone. So this is very, very important. Now in this, now we will see where are the center planes. So why these center planes are important in this case. So let's say if we are taking a profile and the so here what we have is, this means that after manufacturing we can end up with a part like this also. Let's say this can be the condition where the part we manufactured like this. So the center plane, if I make one center plane, so the center plane will be also tilted. So center plane of the part will also be in a round shape. Now, if you take total tolerance between the two parallel planes, so here I am making two parallel planes. So in between this is the median plane between this. So these are the two parallel planes and the center plane of the actual part. So this dashed line is the actual center plane of the part, which is within this two planes, which should not be more than 0.2 mm. So this is the case. This is the how we can control. This is the controlling of the flatness of for the center plane. If the part is manufactured with the round profile. So this was added. This manufacturing or the maximum material and the minimum material condition. This was added in the 2009 standards onwards. Since we are applying flatness to a feature of size only, here we can have maximum material condition. So whenever we are applying maximum material condition, we are getting more tolerance. So when the part is manufactured at 10.5, so we have the tolerance of 0.2 mm. As we move from MMC towards LMC at 9.5, so we have the more tolerance zone, which is 1.2 mm. So as we move towards MMC from LMC, we will have more tolerance zone than we have at MMC. So the part is produced at 10.5 mm is having the tolerance zone of 0.2 mm. Then the flatness error will be in this case will become 1.2 mm at LMC condition for the planar surface. This is the feature of size when we apply the condition to a feature of size. We get more and more tolerance. So this is, although that's only the thing which we have already discussed, that flatness on a derived median plane DMP for a width type feature of size. So in this we are talking about two surfaces, this surface and this surface. So we are controlling two surfaces. So the derived median plane into the engineering drawing is planar. But after manufacturing this part can be tilted, which I have already told you. So as per the rule 1, automatically limits the flatness deviation of the each surface. Thus, to have any meaning, a separate flatness tolerance applied to either single surface must be less than the total size tolerance. The flatness surface tolerance feature control frame associated with the width dimension replaces the rule 1 dimensions or requirement for perfectly formed at MMC, with the separate tolerance controlling the overall flatness of the width type feature. So in this case, we are controlling the width type feature. So with this, the median planes, this is called the median plane. Now, how to measure the flatness? If you want to measure the flatness, what we have to do is place the target. So whatever the target is, let's say this is the part. Place the target in the precision table. This is the precision table over here, plane table, and secure it in place. Set the dial gauge. So in this case, this is the dial gauge indicator, so that its measuring part comes into contact with the measurement surface. So this part over here is coming into the contact with the measurement surface. Move the target. So this target will be moved here and there. This part will be moved here and there. So the target, so that the measurement surface is evenly measured and read the dial gauge value. So this dial gauge indicator will tell that how smooth the surface is. If the variation is large, it will rotate like this in the 360 degree. So the largest deviation value is the flatness. So the largest deviation, whatever the deviation will be in the dial indicator, it will measure the flatness. What will be the disadvantage? So the measured value may change depending on any change in the measurement point. Since the measurement point change depending on how you move the target, therefore it is difficult to obtain a stable measured value. So dial indicator moves and records the flatness error. So this is very important because in this dial indicator, if I will say, so in this dial indicator, it will record the flatness error. Whatever the flatness error will be recorded in this dial indicator. Now, one more method is there to how to calculate the flatness. So if we will discuss, so how to measure the flatness, we have the using the coordinate measuring machine or the CMM machine. So CMM machine is very important machine which we regularly use for measuring the flatness, profile measurement, any surface component to check it is right or wrong, to inspect the part. We use this machine a lot. So CMM, what is CMM? If I will briefly tell you, so CMM is a coordinate measuring machine. It has one probe. With the help of that probe, we collect the point cloud data. So with the help of these are probes. So you can see these probes over here. This is a single machine probe. This is the probe. With the help of this probe, we collect point cloud data. And with comparison of multiple points, let's say uh, this is the part. So here we will check, here we will check. So at multiple points, we will check the part and whatever the variation will be. So let's say whatever the variation in the part, whatever we collect into the point cloud data, whatever the variation into the part, it will collect into the computer. So with the help of CMM, we are collecting the point cloud data and it will be recorded. So whatever will be the deviation, let's say this deviation will be checked, whatever tolerance we will give. Let's say if I have given 0.5 mm, so that will be recorded and that will be given. If it is inside the tolerance zone, let's say this part is inside the tolerance zone, so it will be given that this part is approved. So this part is approved if it is within the tolerance zone. If it is outside the tolerance zone, this part gets rejected. So this is how we calculate or to measure the flatness with the help of coordinate measuring machine. So this is all about flatness. In the next discussion of geometric dimensioning and tolerancing, we will discuss the next geometric tolerance zone, which is circularity. Thank you. Thanks a lot. Hello everyone. So this side Manish from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to discuss the second geometric tolerance under form control, which is flatness. So why flatness tolerance is important? Step by step, how we can calculate how we can give the flatness tolerance to a feature or a feature of size. One by one, we will see. So first of all, we will understand the definition. The flatness tolerance. Many application needs parts with a flat surface. In case of designing molds or we are designing a press tools. So for that, many a times we require flat surfaces. So what we use for the flat surfaces, we use the grinding wheel to flatten out the surface. So flatness is the most important thing which we require in a designing also, in manufacturing also. So no surface is perfectly flat. Whatever we can do, we are doing it with the machining, but it is very, I will say it is very tough to get the perfectly flat surface. But using GD&T, we can develop parts with a surface that is flat enough for the application. So here, it is important that the parts should be enough flat that what we are ensuring for the application, it is perfectly workable. So that's why we need to ensure that the flatness should be within the tolerance zone. The flatness callout controls the uniformity of a surface or a median plane. So here we are talking about median plane. This word is very important in flatness. With the help of 3D overview, I will tell you how these median planes are important. Median planes are as needed. It defines two parallel planes it defines two parallel planes on either side of the flat surface. As the tolerance zone or for the surface, all the points of the specified surface must lie between these two planes for part approval. So in case, let's say, in this is the example. So first of all, flatness can be applied to a feature, and flatness also can be applied to a feature of size. So in this case, you can see that flatness applied to a feature, which is a surface. Whenever it is same as straightness, as I have already told you, that whenever arrow line, this leader line is pointing towards the surface, that means we are providing tolerance to a feature. And whenever the leader line is parallel, or the I will say in line with the dimension line like this, means we are providing tolerance to a feature of size, FOS. In this case, we are providing to a feature. So two ways we can provide the tolerance zone. So here we have an example. In this example, you can see this is the example. So this is the example of a feature with part is having dimension of 10 plus minus 0.5. So here the dimension is provided 10 plus minus 0.5 mm. Since I haven't applied the geometric tolerances till now, rule 1 is applied. First of all, the rule 1 will be applied automatically. So after manufacturing the part, let's say after manufacturing this part, what we can end up like, let's say, this type of surface we can have. So end up the part like this, the peak and the valley. So this is the peak. At the top of the part will be the peak, and the bottom, this is the valley. So the difference in the difference is the flatness error. So whatever this distance will be the in our case we have provided 0.2 flatness or say 0.5 mm. 0 plus minus 0.5 mm is the provided. So 1 mm, very coarse tolerance I have taken over here. So 1 mm will be the maximum this can happen. Maximum this can happen whenever we are manufacturing, because we are taking plus minus 0.5. So 9.5 and 10.5. So upper limit will be the 10.5 and lower limit will be the 9.5. So total tolerance zone we have over here is 1 mm. So if you refine the flat surface, let's say if we are manufacturing this part, so what will happen? So what will happen if I will remove this? So after manufacturing, we should be getting out from the rule 1. Then we have to apply the flatness tolerance. Similar, it is similar to the straightness only, but what is different is this is a 3-dimensional surface. So when we apply it to this surface or a center plane, so if I will give you an example of this, if I will give you an example with this, so you can see this is a part and we required flatness for this surface of this part. So what we will do over here is, first of all, we will select the tolerance zone. So tolerance zone, here we have the median planes. So if I will just to showcase you, these are the median planes. So these median planes are the whole onto the whole surface. So this is the difference. This can be the difference between which is 10.5 and 9.5, which is 9.5 is this plane and 10.5 this plane. So we want flatness to be within this tolerance zone. So whenever we provide the tolerance, in this case, whenever we provide tolerance to the whole planar surface, what we look like, what is this looking like? The part can be, so first of all, so part can be like this. Part surface can be like this. So the peaks and valley in this part should not be more than 0.2 mm, because the geometric tolerance we have applied is 0.2 mm. So although we have the dimensional of 1 mm, but still when we provided the geometric tolerance value, it is the 0.2 mm. So it is within the within 1 mm, within 10.5 will be the upper limit and 9.5. But the point is that the tolerance zone, the peaks and valley of this surface will not be more than 0.2 mm. It is within this, but anywhere between this, but it is not, the peaks and value not be more than 0.2 mm. It can be like this also. And one more case can be occurred in the next profile. So here we are applying the flatness applied to a feature. This is what we are understanding in the previous slide. So in this case also, this is the case which we have understand over here. The peaks and valley is should be not more than 0.2 mm. So this profile like this should be within the 0.2 mm. It can have in range of 10.5 and 9.5. So this is very, very important. While straightness has two parallel lines, in the straightness tolerance, it is two parallel lines because it is a two-dimensional entity, tolerance zone. In this case, the flatness tolerance zone is formed as a two parallel planes because this is 3D equivalent surface. The flatness tolerance zone is the volume between the two parallel planes, which I have already told you in the 3D view. So the distance between the parallel planes is the stated flatness. So whatever the two parallel planes, so between that we are getting the flatness control tolerance value. The surface being controlled must lie within the volume defined by the tolerance zone. So one condition is this. The other condition can be this. So in this case, you can see that 10.5 mm is this and 9.5 mm part this. It can be taper. The flatness can be in taper, but still these peaks and valleys are not be more than 0.2 mm. So the distance between the peak and valley will always be 0.2 mm. Although this, if I will take this point and this point, this range is 1 mm. This range is 1 mm because 10.5 minus 9.5 upper limit minus lower limit is 1 mm. But still the peaks and valley should not be crossing the tolerance value of 0.2 mm. Okay. So peaks and valley are defined. Although this is into the taper, it is acceptable, but the peaks and valley should not be more than 0.2 mm in this flatness tolerance. So this is the condition 2. So this is the second condition. Now we will understand that when flatness applied to a feature of size. Whenever flatness applied to a feature of size, flatness on a derived median plane, DMP. So derived median plane, this word is very important, which I have already shown you in the 3D view. Flatness on a DMP is another way of using flatness in GD&T. In this case, the flatness symbol is applied to a feature of size. So in this case, you can see that we are applying this flatness symbol to a feature of size rather than a surface. The control feature is the virtual DMP of the reference feature of size. This has many practical applications. Most notably is the stacked components. So we are talking about the stacked components in which two components are stacked with one another. Another point to bear in mind when using the flatness symbol of a derived median plane DMP is that the maximum material condition MMC and the least material condition LMC modifiers are also applicable to it. So the flatness callout in the figure below condition contains the MMC modifier symbol. So in this case, you will see that whenever we are providing tolerance to a feature of size, so we can have the maximum material condition modifier or the least material condition modifier. So in this case, we are providing flatness to the feature of size. So you can see that the flatness symbol is applied to a modifier is given to the tolerance zone. So this is very, very important. Now in this, now we will see where are the center planes. So why these center planes are important in this case. So let's say if we are taking a profile, and so here what we have is, this means that after manufacturing we can end up with a part like this also. Let's say this can be the condition where the part we manufactured like this. So the center plane, if I make one center plane, so the center plane will be also tilted. So center plane of the part will also be in a round shape. Now, if you take the total tolerance between the two parallel planes, so here I am making two parallel planes. So in between this is the median plane. Between this, so these are the two parallel planes, and the center plane of the actual part. So this dashed line is the actual center plane of the part, which is within this two planes, which should not be more than 0.2 mm. So this is the case. This is the how we can control. This is the controlling of the flatness of for the center plane if the part is manufactured with the round profile. So this was added. This manufacturing or the maximum material and the minimum material condition. This was added in the 2009 standards onwards. Since we are applying flatness to a feature of size only, here we can have maximum material condition. So whenever we are applying maximum material condition, we are getting more tolerance. So when the part is manufactured at 10.5, so we have the tolerance of 0.2 mm. As we move from MMC towards LMC at 9.5, so we have the more tolerance zone, which is 1.2 mm. So as we move towards MMC from LMC, we will have more tolerance zone than we have at MMC. So the part is produced at 10.5 mm is having the tolerance zone of 0.2 mm. Then the flatness error will be in this case will become 1.2 mm at LMC condition for the planar surface. This is the feature of size when we apply the condition to a feature of size. We get more and more tolerance. So this is, although that's only the thing which we have already discussed, that flatness on a derived median plane DMP for a width type feature of size. So in this we are talking about two surfaces, this surface and this surface. So we are controlling two surfaces. So the derived median plane into the engineering drawing is planar. But after manufacturing this part can be tilted, which I have already told you. So as per the rule 1, automatically limits the flatness deviation of the each surface. Thus, to have any meaning, a separate flatness tolerance applied to either single surface must be less than the total size tolerance. The flatness surface tolerance feature control frame associated with the width dimension replaces the rule 1 dimensions or requirement for perfectly formed at MMC, with the separate tolerance controlling the overall flatness of the width type feature. So in this case, we are controlling the width type feature. So with this, the median planes, this is called the median plane. Now, how to measure the flatness? If you want to measure the flatness, what we have to do is place the target. So whatever the target is, let's say this is the part. Place the target in the precision table. This is the precision table over here, plane table, and secure it in place. Set the dial gauge. So in this case, this is the dial gauge indicator, so that its measuring part comes into contact with the measurement surface. So this part over here is coming into the contact with the measurement surface. Move the target. So this target will be moved here and there. This part will be moved here and there. So the target, so that the measurement surface is evenly measured, and read the dial gauge value. So this dial gauge indicator will tell that how smooth the surface is. If the variation is large, it will rotate like this in the 360 degree. So the largest deviation value is the flatness. So the largest deviation, whatever the deviation will be in the dial indicator, it will measure the flatness. What will be the disadvantage? So the measured value may change depending on any change in the measurement point. Since the measurement point change depending on how you move the target, therefore it is difficult to obtain a stable measured value. So dial indicator moves and records the flatness error. So this is very important because in this dial indicator, if I will say, so in this dial indicator, it will record the flatness error. Whatever the flatness error will be recorded in this dial indicator. Now, one more method is there to how to calculate the flatness. So, if we will discuss so how to measure the flatness, we have the using the coordinate measuring machine or the CMM machine. So CMM machine is very important machine which we regularly use for measuring the flatness, profile measurement, any surface component to check it is right or wrong, to inspect the part. We use this machine a lot. So CMM, what is CMM? If I will briefly tell you, so CMM is a coordinate measuring machine. It has one probe. With the help of that probe, we collect the point cloud data. So with the help of these are probes. So you can see these probes over here. This is a single machine probe. This is the probe. With the help of this probe, we collect point cloud data. And with comparison of multiple points, let's say uh, this is the part. So here we will check, here we will check. So at multiple points, we will check the part and whatever the variation will be. So let's say whatever the variation in the part, whatever we collect into the point cloud data, whatever the variation into the part, it will collect into the computer. So with the help of CMM, we are collecting the point cloud data and it will be recorded. So whatever will be the deviation, let's say this deviation will be checked, whatever tolerance we will give. Let's say if I have given 0.5 mm, so that will be recorded and that will be given. If it is inside the tolerance zone, let's say this part is inside the tolerance zone, so it will be given that this part is approved. So this part is approved if it is within the tolerance zone. If it is outside the tolerance zone, this part gets rejected. So this is how we calculate or to measure the flatness with the help of coordinate measuring machine. So this is all about flatness. In the next discussion of geometric dimensioning and tolerancing, we will discuss the next geometric tolerance zone, which is circularity. Thank you. Thanks a lot. Hello everyone, this is Manish from Skillable India, and in today's session of geometric dimensioning and tolerancing, we are going to start the fourth geometric control in the form control geometric tolerance, which is about the cylindricity. So this is the last and the fourth geometric tolerance under the form control. So first we will understand the definition. So the cylindricity symbol. So this is the cylindricity symbol. Whenever we are using like this, so this some symbol under the box is called the cylindricity symbol. So this symbol we use for the cylindricity. Cylindricity symbol is used to describe how close an object conforms to a true cylinder. So whenever there is a circular round profile of a length, let's say we are talking about a shaft. So in this example, if we are talking about a shaft, so how we will check that it is in a proper form, it is into a proper shape. So we use the cylindricity, and this cylindricity rather than circularity or the roundness in the previous discussion we have made at a one cross section, but in the cylindricity this is not on the one cross section, this is all over the length. So cylindricity follows the roundness and the circularity and the straightness. So this is also called the composite. Sometimes people also call the composite tolerance because it is the in this tolerance we use the straightness and the circularity, both the tolerance in one tolerance, which is cylindricity. So as usual we have a in this example you can see if we go with the limit of size, so if we provide the size to this, so 30 plus minus 0.1, so here we have the size. So as usual, whenever we have the limit of size, dimension, in this case 30 plus minus 0.1 if we are using. So whenever we use 30 plus minus 0.1, whenever there is a limit of size, the rule 1 applies. So rule 1 applies whenever there is a limit of size. Rule 1 applies. So we have two coaxial cylinders. So we have two coaxial cylinders. In this case, you can see like this. So this is the first cylinder and this is the second cylinder. So we have two coaxial cylinder over a length. So over full length, we have two coaxial cylinder for the tolerance zone. So plus minus 0.1 means 0.2 mm of tolerance zone. 0.2 mm of tolerance zone we have over this cylinder. Now, for whole length, so if there is a length 60 mm length is this, so whole 60 mm there are two cylinders which can define the tolerance zone. So here we have tolerance zone of 0.2 mm. So the actual surface lies within these two coaxial cylinders. So the actual surface, whatever the surface will be manufactured, will lie within this tolerance zone. If I want to control the cylindricity better, then what I get, then I have to get out from the rule 1. So what should we have to do in this case? Then I have to apply cylindricity tolerance to this. So when we apply cylindricity tolerance in the feature control frame, so like this, 0.1 mm. So if we apply the cylindricity to a surface, so the geometric tolerance value will be is always less than the dimensional tolerance value. So whatever be the tolerance value to the dimension, the geometric tolerance value will always be smaller than this value. So 0.2, the geometric tolerance value 0.1 will always be smaller than the dimensional tolerance value. So this is the most important part. Now we have two coaxial cylinders which we have which is 0.1 mm apart. So although we have 0.2 mm of tolerance zone, but whatever tolerance we have provided into the geometric tolerance value 0.1 mm, it is within this tolerance zone. Whether 30.1 is the upper limit and 29.9 will be the lower limit. So within this 0.1 mm tolerance zone. So whatever the peaks and valley will be there. So this is not more than the 0.1 mm. Although we have 0.2 mm of tolerance zone, but the peaks and the valley in all over the cylinder will not be more than 0.1 mm because we have mentioned into the geometric tolerance value. So the actual size should lie within the two coaxial cylinder, and this is a three-dimensional entity. So cylindricity is a three-dimensional and three-dimensional tolerance, and tolerance zone are the in this two coaxial cylinders. So most of the people call this as composite tolerance also, as I have already told you, because the cylindricity controls the circularity as well as the straightness. So circularity plus straightness is in this case, if we use circularity plus straightness, so straightness is called cylindricity. So that's why it is called the composite tolerance. Cylindricity is a surface control. So cylindricity is a surface control which we have already discussed. So that's why we cannot apply the feature that we cannot apply the maximum material condition and the minimum material condition, because the material condition modifier can only be applied to a feature of size. So in this condition, cylindricity can be only be applied to a feature. So we will be not able to apply the MMC and the LMC modifier. So form control is and the one of the most important part. If I will tell you, so The cylindricity controls, these are the important points. Cylindricity controls is a GD&T tolerance from the form control group. So in the form control group, we have four geometric tolerances: straightness, flatness, circularity, and cylindricity, and guarantees the part cylindric shape by determining the two key aspects of roundness and axis straightness. The cylindricity tolerance zone is represented by the two concentric cylinders, or we can say two coaxial cylinders. So we can also say two coaxial cylinders. These cylinders run along the entire length of the curved surface. So one on the inside and other on the outside, creating a perfect cylinder boundary around the part entire surface. So the cylindricity controls tolerance zone is a volume enclosed by a radial separation between these two concentric cylinders. The difference in their shape is the applied cylindrical tolerance limit. So whatever limit we have applied, let's say these are two coaxial cylinders over the length like this. So this is the distance between, this is the tolerance zone. In this case, 0.2 mm is the tolerance zone. So between this tolerance zone, we are providing the surface. So the actual surface lies within this tolerance zone. So this is very important part. So thus the zone is such that the entire surface of the part is constrained. So the common axis of the concentric cylinders in the tolerance zone coincides with the axis of the cylindrical part. All points of the surface under control must lie within the zone between these two concentric cylinders for approval. So whenever this surface will be into the between the two coaxial cylinders, whatever tolerance zone we have provided. In this case, if we have provided 0.1 mm of tolerance zone, so this cylinder will control the whole into the tolerance zone. Now, how can we check the cylindricity? First of all, I will let you know one of the very important thing in this discussion. So form control or the form controls are independent of the orientation, location and size. So form controls, this either it's a straightness, either it's a flatness or a circularity or a cylindricity. So they are independent. They are independent of the orientation. So they are not checking the whether it is on some angle, whether it is 90° or at some angle. The part is tilted from the location. So the location is not, they are independent of the location also. So they are not being controlled by the location also. And the third thing, they are not controlling the size. Just they are controlling the shape of the part. So these four form tolerances controls the shape of the part. So form control are never enough to fully define a sketch. So they are used to refine other controls. If we go through about the gauging and measurement, so how we check the cylindricity of the part using a roundness measuring instrument. So roundness measuring instrument like this, you can see into this image. So it is somewhat like a CMM machine only. So with this, what we do is, it is the instrument are used to measure the cylindricity and circularity. So this instrument used to measure the cylindricity and circularity. To verify the accuracy of the cylindrical feature, we check for radial as well as the longitudinal distortion in the cylinder. So this probe over here checks multiple points over the round profile of the part and checks that the part is within the tolerance zone or not. Using a coordinate measuring machine, in this case, you can see this is a coordinate measuring machine. This is a CMM machine, and it is checking. Many a times, accurate cylindricity measurement will not be possible without a CMM. So accuracy can only be achieved with the help of CMM machine. A CMM is far more capable of GD&T measurements compared to manual alternatives. So obviously, I have already in the previous discussion also I have told you about the CMM, the possibilities of CMM. So with the help of inspection, CMM plays a huge role to check the part whether the part is manufactured correct or not. So this is a huge advantage. An advantage of CMM is that besides cylindricity, it can measure a variety of other geometric tolerances also. So variety of tolerances like cylindricity, circularity, flatness, straightness, you can check multiple type of tolerances or the position and other profile also. So we can check other with the help of CMM, we can inspect the other types of parts also. So this is all about cylindricity in the geometric dimensioning and tolerancing. So we have already covered all the four form tolerances in the geometric dimensioning and tolerancing. So this is all about today. Thank you. Thanks a lot. Hello everyone, this is Manish from Skillable India, and in today's session we are going to learn about the most important topic in geometric dimensioning and tolerancing, which is nothing but datums. So in this particular session we will understand about datums and datum features, and I will also let you know that what is the difference between datums and the datum features. So in this starting of the session, first of all we will understand that with the help of definition. So datums are nothing but the references. So as per the ASME Y14.5 1994 standard, define datum as a theoretical exact point, plane and axis. So whenever we are talking about datums, so we are talking about the references. Datums are act as a references and they can be considered as a point, axis and plane. So that's why point, axis and plane. So that's why we are calling that theoretical. So these are the derived from the true geometric counterpart. So of a specified datum feature. So whenever we have a part and in that there are different features, let's say in a part there is a hole. So datum, that hole or the surface of the outer surface of that part is considered to be the datum feature. And that a datum is an origin from which the location or the geometric characteristic of a feature of a part are established. So I have already told you that datums are acting as a references. That's why we are taking an origin from which the location we are locating the part that are established the geometric characteristic of the feature. In easy words, a datum serves as a reference entity for measuring and locating the different geometric feature of the part. So I will tell you with the help of example. So the datum symbol is compatible with all GD&T symbols. So the datum symbols, either it's a primary datum, secondary datum or tertiary datum, all datums are compatible with the GD&T symbols except for those related to the form tolerance. So we have already completed the form tolerance, which is straightness, flatness, circularity and cylindricity. So in these four cases of form control, we do not provide datums, because in form control we have already understand that they are independent of location, orientation and the location and the orientation. So they are independent of it. So that's why we do not use the datums in the form control tolerances. Either it's a straightness or flatness or circularity or cylindricity. So let's say we will understand this thing with the help of example. So this is the example. So in this example, you can see this is a part. So we want to manufacture the part. So we have to take a raw material. So this block we are using as a raw material. In this example, I am taking this block as a raw material. So first of all, we have to place it on the machine table. So first of all, if this is a raw material, so it's all the surfaces are uneven. So first of all, what we will do is that at least one surface we will make as a flat surface, to make that surface as a reference point, reference surface, or we can call it as a individual feature surface, or the first surface which is perfectly flat, which we can use as it as a datum. So we can choose any surface as the first surface. So in this case, I am choosing this surface for machining, and we are keeping this onto the machine table and start machining onto the first surface. So then we are start machining. So the very first surface that we are going to machine does not have any relationship between any other surface. It is not dependent. So this first surface is not dependent on any surface, because this is the first surface, and first surface is always used as a primary datum surface. So that's why we call this first surface as an individual feature, because it do not have any relationship. So that's why the first surface we use, it uses as a, it called it as an individual feature. So after manufacturing that individual surface, the first surface or the feature, we take it as a reference. So the first surface, we take it as a reference, and then we put it onto the machine table. So after machining the first surface, this surface will act as a reference surface, and this, taking reference of this surface, we are now machining onto the other surfaces of the part. So the rest it onto the machine table, and then create a relationship with the second feature. Let's say if I am working on this part, let's say if I want to create a slot like this, and I want to cut a slot, so I will use this surface as a reference surface, the bottom surface as a reference surface for machining onto the second surface. So this surface is having a relationship with the bottom surface. So to the first existing feature, we do not have any relationship. So then start machining on the second feature. So how to create relationship to, that with the second feature and the individual feature, already accurate existing accurate feature which we have already machined at the below surface, is called datum. So the bottom surface which we are using as a reference, so that surface is act as a datum. So in this case you can see that the bottom surface is acting as a datum. So this is a datum feature. Whenever we are this surface is there, whenever we can touch the surface, or we can touch the reference, it is considered to be the datum feature. So this is a tangible one. So datum features are the tangible or the physical features, whereas datums are the theoretical one, and they are intangible. Although I will give you a brief introduction, brief discussion about this. So datum is the theoretical one. It could be a line, it could be a edge, it could be a plane, or datum feature can be a surface. So in drawing we represent datum features like this. So you can see that this surface we are using as a primary datum in this case. So this is the symbol of primary datum, and this is how we provide the relationship. So we will move on to the presentation. So in drawing we represent the symbol like this. So A under the box, and this has having line like this. So this is the datum feature symbol. This is how we provide the datum feature symbol. We can accept any symbol from A to Z except IOU. This triangle can be a filled triangle, and it can, or it can be an empty triangle also, or the open triangle. So it can be a filled one and the open one also. So the datums are nothing but the creating a relationship between intersect feature and the already existing accurate feature. So basically it is a relationship between the second feature and the already accurate feature, which is the bottom surface of the part, or the feature or the feature of size. So datums are the basically the references and the relationship between the second feature and the individual feature. So how we are going to represent it onto the datum feature control frame. So feature control frame. So this is the example of a feature control frame. So this is feature control frame. In this feature control frame, third compartment, fourth compartment, and fifth compartment is given for the datums. So this is given for the datums. Now, in the first compartment, in the third compartment, this is the third compartment, this is the fourth compartment, and this is the fifth compartment. So in third compartment, there is always be a primary datum. In the second compartment, we always have a secondary datum. And in third compartment, we always have a tertiary datum. So how we give in to the feature control frame? Let's say the order, let's say A, B and C, how we give is called the order of precedence. In what will be in the third compartment, fourth compartment and fifth compartment, it will be called as order of precedence. So order of precedence is very important topic. We will cover it this in a very detailed manner. Whatever we take into the third and fourth and fifth compartment, in this case, whatever we are taking it into the third compartment, let's say in the third compartment we are taking B, fourth we are taking A, and fifth compartment we are taking C. So this will be the primary datum, this will be the secondary datum, and this will be the tertiary datum. So this order is very important. Whatever we are using, let's say we are using C over here and B over here. So this order of precedence is very important. This is why it is important. Why? Because it is whenever we are giving onto the engineering drawing, so when the time of inspection, these datums plays an important role. So it controls the 6 degrees of freedom, although we will cover that 6 degrees of freedom in a different session. So this with the help of 6 degrees of freedom, we make the part stable in a stable condition. So the primary datum, secondary datum and tertiary datum basically locks the part onto the table and do not and all the movements of the part with the help of locking all 6 degrees of freedom in this. So this order of precedence is very important in the feature control frame. So we can give any ACB, ABC, BCA. So we will know today how to choose. We will also know that how to choose the order of precedence sequence and why we take it as a why it is important in taking as a datum. So whenever we are going to discuss about the datum reference frame, in that we will be discussing this topic. Now the concept of datum. So I have already told you this thing that first we take the raw material, which I have already told you. Whenever we will take a raw material to manufacture the part, first surface. So let's say this is the first surface, the top surface we are considering of the raw material is the first surface. So this surface, the first surface is also called the individual surface, individual feature. So this surface is also called the individual feature. And we start machining does not require any relation with the other surfaces of the raw material. So the first surface do not require any relationship with the other surfaces and of the raw material. So we can start machining with the first surface. Then if we are machining onto the next surface, let's say second surface. So the first individual feature, the top feature will act it as a datum feature. So this surface will be act as a datum feature. This individual feature will be act as a datum feature and it will create a relationship between this. This will act as a reference. So this will act as a reference surface. Now we will understand in very detailed manner that how it is important that datums and what is the difference between the datums and the datum features. So as I have already told you about the datums and the datum features, it is very confusing between the datums and datum features. Just remember that when we are talking about datum features, we are talking about a physical form or we can touch that feature or it is a tangible form. So first of all, it is a common mistake. One must be clear about both to make a professional engineering drawing. So you must, as a design engineer, you must be very clear about this. So a datum feature is a physical tangible feature of a part. So let's say this is a part and this is a surface and this surface is acting as a reference. So this is a datum feature. This is acting as a datum feature. So that establishes the datum because this surface is acting as a I will say as a reference feature. Since it is a real entity, so this surface is a real entity. We can touch this. It is not exact and can have an irregular form. So this surface obviously can have an irregular form. So whenever we are taking it as a reference, so there is a chance that we may end up creating wrong decisions, wrong inspection. So for this, we create a plane which is a theoretical one, which is touching the high points of this surface. So let's say if this is a part, so we will create one imaginary plane which is touching the high point. So at the bottom, this plane at the bottom will act as a datum. And this plane is a theoretical one. Theoretical. So planes, the datums is a relatively more abstract concept. It is a geometrical exact representation of the datum features. So whatever datum features are there, let's say its surface is a datum feature, but we want exact dimension. So we will create one plane which is touching the high points of this part. That's how we can calculate the right inspection, whether it's a 5 mm. In this case, let's say we are taking. So whatever measuring with the high points with the imaginary plane, it is touching the high points of the part. So this is a theoretical one. This is intangible. So we cannot touch this plane. And so that the example, if a rough surface of is the datum feature. So in this case, I have shown you that this is a rough surface of the datum feature. The datum will be perfectly smooth plane. So I have created the plane bottom of this part that best simulates the surface. So this is the how we can create the differentiate between the datum features and datums. So datums can be a point, it can be an axis, it can be a plane. So these all considered to be a datums. So this is all about the datums and the datum features. In the next session, we are going to cover about the datum reference frame and the order of precedence. So thank you. Thanks a lot. Hello, welcome everyone. This is Manish Sharma from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to understand about the datum reference frame. And the other topic which we are going to discuss today is implied datum and the order of precedence. So the most important thing in today's session, first of all, we will understand about the datum reference frame. So whenever we take a part, we have to bring this part to a stable condition. So in this case, you can see in this image, this is a part. And if this is a part into a space and we want to bring this part into a stable condition, what we have to do, we have to constrain all the movements. So this, if we want to constrain all the movements of this part so that we can do the machining. So the machining is accurate and the inspection is also accurate. So whenever the part, let's say this is the part, and we want to I will give you the example. So we want this part to be in a stable condition. Stable condition. Why we want this into a stable condition? To machining a part or to inspect a part. So to make this part into a stable condition, we have to constrain the movement of this part. So we have to constrain the movement of the part. So if you want to bring the part into a stable condition, then we have to arrest all degrees of freedom. So in this, we have to arrest all degrees of freedom of the part by constrain the part with the reference to the plane. So we have to arrest all 60. Total, there are 6 degrees of freedom. 6 degrees of freedom. 3 are rotational. In this 6 degrees of freedom, 3 rotational and 3 are translational. Now we will understand with the help of 3D overview this thing, because in this explanation this is very important if you want to bring the part into a stable condition. Okay, so we know that there are 6 degrees of freedom, 3 are linear movement and 3 are rotary movement. Along the linear movement, totally 6 degrees of freedom are there. In this you can see, and this is the overview of this. And if you want to arrest all the 6 degrees of freedom, then you have to take the help of datums. So now we want to take a help of datums. So here I will demonstrate one model. So here I will demonstrate one model over here. So this is the model. In this model, so here I have a model to demonstrate the datum's reference frame. So in this datum reference frame, I keep this part onto one of the planes. If the another example, if we take, so in this example, if we are taking, so this is a part, and this part is having into a space. So this part can have 6 degrees of freedom. So this part can move like here in this direction. This part can move in this direction, x, y direction. This part can move in this direction. These are 3 linear movements. This part can rotate like this into the x direction. This part can move into this direction, y direction or z direction in this, and the part can rotate like this. So these 3 are the rotational movements. This part can be rotated like this also. So these total 6 degrees of freedom are there in this part. So how we will discuss this? I keep this part onto one of the plane. Let's say if this surface, let's say we are constraining this surface and this surface. We are mating this surface. So what will happen? The 3 degrees of freedom, we are able to arrest 3 degrees of freedom. What 3 degrees of freedom we have to arrest? We have arrested. In this, if we understand, so the part cannot rotate like this now. This degrees of freedom is arrested. This part cannot rotate like this. And part cannot move like this. So 2 rotary movements and 1 linear movement is arrested. So this is how we have arrested the 3 degrees of freedom of this part. Now 3 more are left. Which are left? 3 more are left. The part can rotate like this. So the part can rotate like this. Part can move in this direction. And part can move in this direction. So 2 linear motions and 1 rotary motion is left. So the 3 degrees of freedom are left and 3 are constrained. So when we join this surface and this surface of the part, so if we use this part and join these 2 surfaces, so 2 more degrees of freedom are constraints. Now in this option, 5 degrees of freedom are arrested. 3 degrees of freedom are already arrested. Now the part cannot rotate like this also. In the previous section, it can rotate. It cannot rotate like this. It cannot rotate like this. So all the 3 rotary motions are constrained. The part cannot move in this direction. Part cannot move in this direction. Only 1 linear motion is left, which is this. So the part can move only in this direction. So 1 degree of freedom is left. So after constraint, this surface with this surface, and we provide join this surface, now the part into a fully constrained position and logged all 6 degrees of freedom in this. So part can so now out of 6 we have constrained all the 6 degrees of freedom. We bring this component to arrest along the all the perpendicular surfaces of the part. So what happens? It cannot move in the any direction and rotate in any direction, nor it can rotate, nor it can move into any direction, this part. So when we arrest part of the second datum plane, we constrain 2 degrees of freedom. First, whenever, let's say this is datum, this surface is acting as a datum. So this is a primary datum. Primary datum arrests 3 degrees of freedom, 2 rotary motions and 1 linear motion. Now, this is the second datum, which is the secondary datum. We say this arrests 2 degrees of freedom, one rotary and one linear motion. And this third is the tertiary datum. So this tertiary datum arrests 1 degree of movement, which is the linear movement. So this is how we came this part into a stable condition. So now we can say that this part into a stable condition, and if we want to machine this part, we can machine this part because all the 6 degrees of freedom are arrested. Think like that we are putting a part for a machining onto a table and we have to arrest all 6 degrees of freedom that the part movement will be arrested. So this is the most important thing we can learn in this part. So this is how we can, this is called the datum reference frame. So what I'm going to do, I will put along this plane. Now, what will happen? This movement will be, all the movements are arrested. So whenever we have a plane surface, so in this condition, this surface, if we want to arrest all degrees of freedom, we have to keep on primary plane and secondary and but it on secondary plane and again it on tertiary plane. So this will become an stable condition. So the first surface what we take for resting primary datum is called the primary datum. First surface is called the primary datum. The second surface is called the secondary datum and third surface is called the tertiary datum. So this is as we put onto the, I will say, feature control frame. So this is how we will put onto the feature control frame. This surface we will write primary datum A. This we will write primary datum B, a secondary datum B. This we will write tertiary datum C. So datum reference frame is always 3 mutually perpendicular planes. So in this case, this plane and this plane, these 3 planes are mutually perpendicular and this will become the origin of the measurement. So this is the very important part. In this, you can see in this also that this plane and this plane, these 3 planes are mutually perpendicular to each other. So if we want to make this part into a stable condition, so we want to arrest all the 6 degrees of freedom of this component. So in this also you can understand in this example that we have 6 degrees of freedom. This part can rotate in this direction. This part can rotate in this direction. And this part can rotate in this direction. So these are the 3 rotary movements. These 3 are linear movement. This part can move in this direction. This part can move in this direction. And this part can also move in this direction. So if we want to arrest all the 6 degrees of freedom, first we have to put this surface and this surface join this surface to lock the 3 degrees of freedom. Then we will lock, with the help of secondary datum, we will lock 2 degrees of freedom. And with the tertiary datum, we will lock one linear movement, which is 1 degree of freedom. So this is how we will all cover the 6 movements of the part. Now we will understand the most important part of this discussion and we will move towards the implied datums. So with the help of this, we will understand that what is called the implied datums. So in this particular session of GD&T, we are going to discuss about implied datum also. So what is implied datum? To understand this, we want one example. So in this example, you can see that this is a part. This is a part drawing. In this part drawing, the we have provided the dia 7.5 to this hole, and we have provided the tolerance also with the position symbol. So whenever we are providing the position symbol, these are the dimensions of this hole. So if we want to check the dimension of this hole, we will follow these 2 dimensions. So we have a drawing on which we have a hole. To control this hole, we have a positional tolerance. So if we want to control this hole, we have positional tolerance. The positional tolerance is not having any datum. So you can see this positional tolerance is not having any datum in this direction. In the 3rd compartment, in the 4th compartment, and 5th compartment, there is no datum over here. So without datum, if we give a related feature, so this is a related feature. And whenever we give related feature without a datum, then we called it as an implied datum. So this is very important. I am writing down over here in this part. This is an important point. So if we give a related feature without datum, then it is called called as implied datum. So in this case, we are using the positional tolerance and we are not providing any datums over here. So this is called the implied datum. So after manufacturing, we may end up the part like this. So we may end up the part, I will show you into the actual case. So let's say this is the part which we are seeing the drawing. So after manufacturing, let's say this is the part, this is the part drawing we have. After manufacturing, we have manufactured the part like this. So if we want to inspect this part, that this part is manufactured in a correct position or not, if we want to check the whole position of this part, so what we will do, we do not know which is the primary datum and which is the secondary datum and which is the tertiary datum. So in this case, you can see that we don't know any type of datums in this part, in the implied one. So in this case, we do not have any datums. So we do not know that how to inspect this part. So what I do is I will rest, let's say, if we are taking this condition, so first I will arrest this surface to this surface. So the 3 degrees of freedom will be arrested. Now, what will happen? I will lock this surface and this second one. And let's say if somebody will check, I will make this position also to lock this properly. We are just coinciding. And this is how the 5 degrees of freedom are arrested. Okay. So I am taking primary datum, this surface, and secondary datums, this surface. Then I will arrest this point to this surface. So you can see that now I have arrested all the 6 degrees of freedom. So first what I have taken, primary datum, secondary datum and tertiary datum. When I have not provided in this drawing, if I have not provided any references, in this case I haven't provided a primary datum, tertiary, secondary datum and tertiary datum in the 4th, 5th and 6th compartment, what will happen? Whenever the inspector who is inspecting this part, somebody will check like this. Somebody will check like this. In this, you can see there is a gap. There is a gap over here. So when I am using primary datum this, secondary datum this and tertiary datum this, the gap is over here. So the position of the hole will be different. Let's say if another person comes and he is also going to check this part, he is going to inspect this part. If I will delete all these just to show you, let's say some other inspector came and checked this part, that this part is manufactured correctly or not. So firstly this he makes this datum with this surface to this surface and locks the primary datum, and this surface he uses as a secondary datum. Previous person used this surface as a secondary datum, but the another second person uses this surface as a secondary datum. Now let's say if I will join this properly. Oh, sorry, not like this.
if I will join properly, sorry, this, so this he uses as a secondary datum, and this surface, this part, this perpendicular surface, he uses as a tertiary datum. Now you can see what happened over here. Previously the gap is coming over here in this plane, gap is coming over here. So the whole, if somebody measure this hole from this datum to this, it will come different value. And this time the second person who measures, the gap is coming over here. So somebody will measure now, this, the value will be different. So you can see that if we are not providing the datums into the drawing, if we are not providing to a related feature into a drawing, let's say if we are not providing any datums over here, so although this is called the implied datum, but this is not the correct way. In this way, the inspector is confused that which surface I have to take it as a primary datum, which surface I have to take it as a secondary datum, and which surface I have to take it as a tertiary datum. Now, what will happen if in this case I will provide datums. So in this drawing, now you can see now now with the this, what happens, the x and y direction, in the x and y direction I have given this datums. So from ASME y 14.5 1982. So in 1982 ASME y 14.5, in 1982 standard, we are not supposed to give implied datums. From 1982, previously we used the implied datums, but from 1982 standards, we are not supposed to give the implied datums for such applications. So from 1982 by 14.5 standards, we are not able to provide the implied datum onto the engineering drawing. So this is very important part. Now, in this drawing you can see that this back surface, I have used it as a primary datum for this part. This surface, this second surface, I have used it as a secondary datum, and this surface, this bottom surface, I have used as a tertiary datum. So here you can see that primary datum, secondary datum, and tertiary datum we have provided onto this part. So first I will put this part along the way to the surface. Then I will make this surface onto the secondary datum and log the movement. And then I will put the tertiary movement. Now the steps are being, for the inspector, all the steps are being given that this is the primary datum, this is secondary datum, and this is tertiary datum. So the confusion for the persons is eliminated. So whenever the inspector will come, he will check the drawing and he will see that which is the primary datum, secondary datum, and tertiary datum. Now, the most important part over here is you can use the primary datum, this also, and this also. So in this case also, that you can give like this. If I will make 1 second. So if I give like this, so in this I can also give, sorry, I made it smaller. Let's say I will make a little bigger. In this I can also give like B, A, C. So what will happen when I will give this way? So first of all, the inspector come and this they uses as a primary datum, this surface as a primary datum, because I have given B in the first position, and the first position is for the primary datum. So this is the primary datum. Then A. So this surface he uses as a secondary datum, and this surface, which is C, we are using as a tertiary datum. So this is called the order of precedence. If we are using ACB, BAC or ACB or ABC, whatever we are choosing, so this is called the order of precedence. So whatever we are giving as per the manufacturing applications, then we see what is going to be happen like ABC or ACB. This is called the order of precedence depending upon the functionality and the assembly requirements. So whatever will be the functionality of the part, what will be the assembly requirements of the part, we have to decide whether we are going to use ABC or BCA, BAC or ACB. So whatever we are going to use, it will be depending on the requirement of the function and the functionality of the part. So this is all about the datum reference frame, implied datum and order of precedence. In the next session, we are going to cover in detailed manner about the datum types. So thank you all of you. In the next session, we are going to learn some more topics of geometric dimensioning and tolerancing. Thank you.
Hello and welcome everyone. In this session of geometric dimensioning and tolerancing, we are going to understand different types of datums. So, how many types of datums are there? With the help of example, in detailed manner, we will understand. I will also tell you about datum feature simulator and what is a datum feature. So, all these things. What is a simulator and how we can log the degree of freedoms into the with the help of simulator, datum feature simulator. So one by one, we will understand that how we should do this. So first of all, we will discuss different types of datums and in terms of features and feature of sizes. So which can be taken as a datum. So one of the very most common type of datum and very widely used datum, which is a planar datum. So first type of datum we are going to understand is of planar datum. So in this example, this is the example of the planar datum. So basically if you have any planar surface, so this is the part. So we are taking this part many a times. So this is the part and this bottom surface is the planar surface in this part, and you want to take datum and you can take this as a in the datum as a drawing. Then it is called the planar datum. This datum on which the part is placed. So whenever we take that planar datum as a primary datum, so if we are taking this as a primary datum, this is a planar datum and we are taking as a primary datum, that means in the third compartment of the feature control frame, which is for the primary datum, there we are going to arrest that surface onto the mating part. So let's say if for this part, if we see that there are all the 6 degrees of freedom, this part can move like this. This part can move in this direction, it can rotate in this direction, it can rotate in this direction also. So these are basically the 6 degrees of freedom. So this can rotate in this direction also. So what we are doing is, first of all, if we are keeping this part onto this surface, so this is a simulator surface. If we are keeping this part onto the simulator surface, so what is going to be happen? We have already understood this concept, but then we are going to rest. So the surface is going to be made with the surface. Now what happens? The surface on which it is going to be rest, the part on this surface. So this surface is going to log the 3 degrees of freedom of this part. So I have already told you that this for the planar datum will become the surface which is the origin of measurement. So from this point, this surface point, this is the origin of measurement also, and the surface is called the simulated datum. And this surface is called the simulator datum. Datum feature simulator, actually an instrument is called datum feature simulator. So this in this it is called datum feature simulator. So the surface, the plane created after placing the part is called the simulator datum. So this surface, the plane created after placing the part. One plane is created, so that plane is called the datum simulated datum. So the primary surface is the origin of measurement. So what will be the connection of this part and this surface will be the origin of measurement. So this surface will be the origin of measurement. Whenever I keep the planar surface onto the datum feature simulator, it will arrest 3 degrees of freedom. So I have already in the previous discussion we have discussed, but again I am telling you. Now 3 degrees of freedom are the part cannot rotate like this. The part cannot move like this in this direction. The part cannot rotate in this direction. So 2 rotational movement and one translational movement is arrested. Now this part can move in this direction, it can move in this direction, it can move, and in this this is how it can move, rotate. So 3 degrees of freedom are arrested and 3 are not. So by placing with the datum feature simulator, we are arresting the 3 degrees of freedom of this part. So the movement and the rotation are there. So now if you want to bring this part into a stable condition, let's say, so what you have to do, you have to arrest all the 6 degrees of freedom. So 3 are left. So for that also we need to arrest this surface and this surface connection and this surface and this surface connection. So all the 6 degrees of freedom will be arrested. Now another type of datum is there, which is frequently used into the industry, which is a center plane datum. So what is going to be happen? That means if you take feature of size as a datum, whenever you take feature of size, I am not talking about feature, I am talking about feature of size. So feature of size means if there is a rectangular part, then if you want to hold that part, you want to hold with the help of 2 planes or 2 surfaces. Or if you take an example of an industrial vise, if you are holding a part onto an industrial vise, so in that case, let's say this is the example of an industrial vise. So in this as a data, then it is called the center plane datum. So I'm opening the datums over here, so you can see in this part there is a center datum for this part also, and for this I will say vise we are taking. So in the center there is one plane. So this is called the center plane datum. If I take center plane as a datum, then the simulator will be 2 parallel planes. So we are taking this as a plane and this as a plane. So for holding this part, we want 2 planes. So we are taking on both the sides, there are 2 planes to hold this part, which is holding the part. If you want to imagine, I've already told you what it is. You can take it as an industrial vise, which the part is fixed. Now, whenever we take a center plane, it as a datum, it will arrest 3 degrees of freedom. I will let you know. So whenever I will arrest the surfaces into this, and I will make so in this case you can see, if I take this part, so in this now the 3 degrees of freedom are arrested. The part cannot rotate like this. This rotation is logged. The part cannot rotate like this. So 2 rotational movement is logged and 1 translation. In this part cannot move. So part can move in this direction only. Part can move in this direction. And part can rotate in this direction. Only this direction. So while holding a part onto the vise, onto the similar datum feature simulator we are taking, so it is arresting the 3 degrees of freedom with the help of center plane. Now, very next frequently used type of datum is axis datum. If you want to hold a shaft, so what type of datum feature simulator we have to use? So in this case, we will understand. So this is the part. If we want to hold this part, so what will be the, how we can hold the part or cylindrical part? The datum feature simulator will also be cylindrical in shape. So the axis datum. So in this, we are considering the feature of size. So for feature of size, we are considering the axis of axis datum. So whenever we have cylindrical part like this, and this is the axis datum, you can see this blue line at the center of this part. So this is the axis. So we have a cylindrical part like this, and this is the axis. We take this axis of the cylindrical part as a datum. It is called the axis datum. So whenever we have cylindrical part like this, then the datum feature simulator is also be cylindrical. So whenever we meet the axis of this we are considering the datum feature simulator, because it is also into the cylindrical in shape. So what will happen, that if we are locking this part, let's say this axis and this axis we are meeting. So what will happen, it is locked. How many degrees of freedom are locked in this case? 4 degrees of freedom are logged. In the previous case, if we haven't done this case, so there are 6 degrees of freedom for this part also. It can rotate like this. It can move in this direction. It can move in this direction. It can rotate in this direction. It can rotate in this direction. All the 3 degrees of freedom are there. But if we align the axis, if we are putting that onto the axis datum and making it, so there are 4 degrees of freedom which are logged. Which are those degrees of freedom? The part cannot rotate like this. It cannot rotate like this. It cannot rotate like this. It cannot move like this. It cannot move like this. Only one rotational movement, which is from the center axis. If we are considering, so this is how the part can rotate. So you can see that this part can rotate in at the center of its axis, and this part can move in front plane if we are not considering the friction. So in this center axis datum, and the datum feature simulator will also be cylindrical. So in this case, we are locking the 4 degrees of freedom. Or you can considering you can think of the chuck, the in which the into the lathe machine that the part is holding. So it is the good example for this condition for the datum feature simulator, because it is the movement is into one direction and the rotation is into one direction at the center of its axis. So that's the most important case. So this is the example of the axis datum. Now I will also give you one more example, which is the example for the conical. So if the part is in conical shape, the datum feature simulator will also be conical. If we want to hold a conical part, the datum feature simulator will also be in a conical shape. So let's see, this is the part. And if you want to hold this part, so how we can do this datum feature simulator? If we are considering this part, so how many degrees of freedom are arrested? The part cannot move if we are not considering this. Let's say I'm giving some space. So we have 6 degrees of freedom. Now we have arrested the 5 degrees of freedom. How we have arrested the 5 degrees of freedom in the conical shape? The part cannot move upward, downward. All the 3 movements are arrested because one is smaller. So the part has arrested. It cannot move from inside the part. So when all the 3 movements are arrested in this part, 2 rotational movements are arrested. The part cannot rotate like this. The part cannot rotate like this. Only there is a one condition. The part can rotate in its axis. The part can only rotate around its axis. Because in this case also the part, the datum feature simulator will be in a conical shape. Then only it will hold the part and locks the 5 degrees of freedom. So this is the very important part. Now, this is all different types of datum feature simulator. So these are different types of datum types which we use on a regular basis. There are a lot more other types of datum datum types are also there. So moreover, we will discuss in the next session or the another session. So this is all about the datum types. Hope you have enough understanding of the datum feature simulator and how we locks the or arrested the degrees of freedom. Thank you. Hello and welcome everyone. This side Manish Sharma from Skillable India. In today's session of geometric dimensioning and tolerancing, I'm going to let you know about the 3 to 1 principle. So what 3 to 1 principle means and how we can apply onto the planar datums or the planar surfaces. And why this 3 to 1 principle is important. So one step by step I will let you know. And in the previous sessions also, pretty much we have discussed about the 3 to 1 or the 6 degrees of freedom in or the 6 DOF or the for the part to get in a stable condition. If we want to get a part into a stable condition, we have to follow the 3 to 1 principle. So step by step, we will be discussing this in very detailed manner. So you can see that we have two objectives when the mounting a part in a fixture or machining for machining. So whenever we are mounting a part, this is a bed of a machine, and if we are mounting a part onto this machine, so there are two objectives. First objective is accurately position the part at the desired coordinates. So whenever we are mounting a part onto a machine bed, so the first thing is that the part position in a correct way. So and the coordinates should be in a match. So desired coordinates should be achieved when we are mounting a part onto a machine or onto a fixture for machining. So first we have to, let's say this is a fixture and we have to mount a part like this. Then the mandrel will come and do the machining on the surface of the part. So whenever we are putting onto this fixture, this part, we have to accurately position the part of the at the desired coordinates. Second is restricts all 6 degrees of freedom so that the part cannot move. So the second very important thing is we have to restrict or we have to arrest all 6 degrees of freedom that the part can move and rotate. So we have to arrest all the 6 degrees of freedom that the part should come into a stable condition. For to arrest all 6 degrees of freedom, we have to follow 3 2 1 principle. So when you will add 3 plus 2 plus 1, this is 6. So this is 6 degrees of freedom. So this by adding 3 plus 2 plus 1, we will get 6 degrees of freedom. So basically 3 to 1 principle is related to the degrees of freedom only. Now, the most important part is a widely used method of accomplishing these two objectives uses 3 to 1 principle to achieve these two objectives. To achieve these two objectives, we basically use the principle which is called the 3 to 1 principle. So called because it entails 3 steps that employs 3, then 2, then 1 fixed points of known location. So first of all, we will, let's say this is a part and we have to make this part into a stable condition. So first we will lock or arrest 3 degrees of freedom, 3 DOF, which is a primary datum. First of all, in a primary datum, what we will do is arrest 3 degrees of freedom. Then we arrest 2 degrees of freedom in a secondary datum. And then we arrest 1 degree of freedom DOF in a tertiary datum. In the starting of datum, I have already told you. Let's say here again I am giving you one example of a feature control frame. So in the first compartment, we usually give the one geometric characteristic symbol. Now we are taking the position symbol over here. Then we provide the tolerance. Let's say 0.1 mm of tolerance we are providing. Then we provide the material condition modifier. Let's say here I am using the maximum material condition. And in third compartment, fourth compartment and fifth compartment. This compartment is for the primary datum. This compartment is for the primary datum. This fourth compartment is for the secondary datum. And fifth compartment is for the tertiary datum. Okay. So in the primary datum, we are arresting 3 degree of freedom. In secondary datum, we are arresting 2 degrees of freedom. In a tertiary datum, we are arresting 1 degree of freedom. So one by one I will let you know that how these degrees of freedom are arrested and how we can put the part in a stable condition onto the bed or onto the fixture where we are going to do machining. If we will not make a part into a stable condition and we start machining onto the part, let's say, so the part will move with the machining. Maybe it can move like this, it can move like this, it can rotate. If the part will not be in a stable condition, then when we will machining onto the part, the coordinate gets disturbed. So to lock, to arrest all degrees of freedom to that coordinate, whatever coordinate we have set. So for that, we need to arrest all the 6 degrees of freedom with the help of 3, 2 and 1 principle. Now move on to the second part. So in order to completely specify the position in a space of a 3-dimensional. So here you can see in this example, that the part is in a space. The part is in a space. So we are considering that the part is in a space of a 3-dimensional unit. So 3-dimension x, y and z axis. So whatever x, y and z axis. So we are considering the coordinates and part is into a space somewhere here, which is not at the origin, which is 0, 0, 0. So the part is not at the origin, it is into the space. So if we want this part to be in a stable condition, we have to lock the 6 degrees of freedom. So with the help of 3D object, I will let you know each and every detail that how you can do this. So object such as a cube that's shown, we refer to the 6 coordinates. So what are degrees of freedom? 3 are translational. The part can move into the x-axis, the part can move into the y-axis, the part can move along the z-axis. So part can move upwards, part can move this side, and part can move in this direction. So x, y, and z direction, the part can move. Now, 3 are rotational. 3 translational movements are there and 3 rotational movements are there along the x-axis, along the y-axis, along the z-axis. So along the axis, it can rotate x-axis, y-axis and z-axis. So these 3 are rotational. So these total means 6 degrees of freedom. These 6 coordinates are known as the 6 degrees of freedom of the 3-dimensional object. As the double-headed arrow indicates the translational movements, you can see this is a translational movement, this is a translational movement, this is a translational movement, this is a rotational movement, this is a rotational movement, and this is a rotational movement. So if we are considering, let's say x, y, and z, and this is if we are considering x, y, and z. So 3 are rotational and 3 are translational movements. Can vary the either direction with respect to each of the 3 axes. So to completely prevent movement, all 6 degrees of freedom must be restricted. This is very, very important, and we will be knowing this in the SolidWorks example. So I'm closing this and opening an example over here. Let's say this is a part. So we are considering this part. So this is the part and we want to make this part into a stable condition. So you can see I have given this part a spherical shape. Why I have given? Because when it is touching to the surface, whenever a spherical part will touch to a surface, it will touch via point. So it will always have a point contact. That's why in all the part I have given a spherical surface that it is going to make a point contact. So let's say if I want to put this part into a stable condition. So first of all, let's say I will put 1 point. So first says 3 to 1 principle. First we have to restrict the 3 degrees of freedom. So this is a primary datum. With the help, this is a primary datum. And if we want to restrict the part, so first of all, I will give 1 point. Now you can see the part is not in a stable condition. Although point is touched in this part, but it is not in a stable condition. If we will see from the right view that it is touching at the one point from this part, but still it is not in a stable condition. So minimum now I will provide the second point touching this datum. Now I have provided the second part touching this datum. Okay. Now you can see that still the part is not in a stable condition. So thirdly, we will put again third point. Now we have touched 3 points of the part with the primary datum. So now I have touched 3 points of the part with the surface. So these 3 points are touching the surface. So first of all, in the primary datum, to stabilize the part, we have to provide at least 3 points. More than 3 points are very good. There can be any number of points, but minimum requirement to stabilize a part in the primary datum is of 3 points. So this is a 3-point contact for the primary datum. If we are considering as a primary datum, so I have provided 3 points. In this, you can see that it is touching there, here, and here. These 3 points are touching the surface. So now you can say this part is in a stable condition. Now, in the secondary datum, we have to provide 2 degrees of freedom. So in this condition, now this part, if I will make this on, so what happened? The part cannot move in this direction. So one translational movement at y-axis. You can see this y-axis over here. So now the part cannot move in y-axis. Part cannot rotate in this axis. So in y-axis, the part cannot rotate. The part cannot rotate in the x-axis also. The part cannot rotate in the x-axis. And part cannot, the 3 degrees of freedom are logged. Now, what other 3 degrees of freedom are left? The part can move in the z-axis. The part can move in the x-axis. And part can rotate along this center axis. So one rotational and 2 translational movements are remaining. So first of all, to restrict the secondary datum, we have to give 2 degrees of freedom. So again, we will provide 2-point contact with this surface. So first of all, this. Now you can see that still this part having the movement like this. So to stabilize this part, we have to provide the one more point of contact with this part. Now 2 degrees of freedom in the secondary datum. When this is the secondary datum, this is the primary datum, and this is the secondary datum we have provided. So by applying secondary datum, we have restricted 2 more degrees of freedom. Now you can see the part cannot rotate in any direction. Now the part cannot rotate in this direction also. And what other movements is restricted? The part cannot move in the z direction also. Previously, part can move in the z direction and rotate along this axis. But now these 2 movements are also restricted. Now only 1 degree of freedom is left. The part can move along the x-axis. So to restrict this movement, we have to provide for tertiary datum. This is the tertiary datum. And we have to give 1 point of contact. In the primary datum, we have restricted 3 degrees of freedom. In the secondary datum, we have restricted 2 degrees of freedom. And in the third part, tertiary datum, we are going to restrict the last degree of freedom, which is the movement of x-axis along the x-axis. Okay. So I am giving 1 point of contact like this. Now this part is fully constrained and fully in all the 6 degrees of freedom are restricted. Now this part cannot move in any direction. You can see all the degrees of freedom are there. You can nor it can rotate in this direction, nor it can rotate in this direction, nor it can rotate in this direction. Not it can move in this direction, not in this direction, not in z direction. So all the 6 degrees of freedom are restricted or arrested with the 3-2-1 principle. So this is the very important thing. Again and again I am saying it is not required. The minimum 3 points are required to arrest first of all. So more than 3 there can be any number. Minimum 3 points are required to make a part into a stable condition in the primary datum. So this is the first part. Now the question arises, can we make a cylindrical part with the help of 3-2-1 principle? No. Can we make a conical part with the help of 3-2-1 principle? No. Why it is? Because in the previous section I have already told you about the datum feature simulator. So when we have to arrest the degrees of freedom of a cylindrical part, let's say this is a shaft, and if I want to arrest a degree of freedom, so it is not going to, I am not going to put onto the planar surface. I am going to arrest by moving a cylindrical datum feature simulator only. So I have to provide the cylindrical part to arrest the all degrees of freedom of the I will say cylindrical part. So only, so that's why the 3-2-1 principle is only applicable for the planar surfaces or the planar parts or the part which need to be arrested in that condition. If there is a spherical part, so how we will arrest the spherical part of this? So I will say, if I will if let's say this is a spherical part, so there are two conditions. If I have to make this spherical part, which is a ball in this case, to in a stable condition, what I have to do is I can provide the 3-point contact. If I will provide the 3-point contact, and if I will give the datum targets in the coming section, we will understand about the datum targets in very detail. So if we give the datum targets, so with the help of 3-point contact, we can restrict all 6 degrees of freedom. So in this part, we can check the 6 degrees of freedom in a very detailed manner. And the second thing, to arrest all 6 degrees of freedom of this spherical part, I can give a spherical datum feature simulator. So if there is a simulator which is datum feature simulator of a part which is into a spherical shape, so I can lock all the 6 degrees of freedom. So this is how we provide the, this is why we understand about the datum feature simulators. Now we will move on to the next part. I will give you brief understanding about this. So while giving example, so you can see the chair. I am giving you an example of a chair. If I want to make a stable, at least 3 legs are required in a chair to make into a stable condition. One leg chair will not sustain. 2-leg chair will also not sustain onto the floor. At least 3-point contact is required for the chair to come into a stable condition. So this is the primary case. More than 3-point contact is very good. We also know we have 4-leg chair. We have the 5-leg chair also available, which is into the base, in which the casters are there, movable chairs. So in that case, we provide more than 4 arms for the stability of the chair. So these are the cases where minimum 3 points of contact are required in the primary datum. More than 3 datum, you can give any number of points of contact. Let's say in this case only you can see that there are 6 legs in this table. If the length is much more bigger, then we have to increase the points of contact of that part. So that's why it is just an example that why we need 3 point of contact to get into a stable condition. So here it is an example of a table. For table also we require at least 3 point of contact. More than 3, it is a very good number. Any number that is touching. So let's say this is a table and this is a part. The part can have ups and downs like this. So maybe these are the 3 top points of this part. Let's say So here you can see that 3 top points will touch the surface, and more than 3, any number of point can touch the surface. So to make this part onto this table, if we put this part onto a table, at least 3 point contacts, minimum 3 point contact is required. More than 3, any number of, there can be 100 points, there can be 1,000 points, or the whole surface should be there. Minimum 3 point of contact is required to make part stable in a primary datum. 2 point contact is required to make part in a secondary datum stable, and 1 point contact for to arrest all 6 degrees of freedom in the primary datum, secondary datum, and tertiary datum in the feature control frame. So this is all about the 3-to-1 principle. If you have any confusion, you can write it down to one note section. We will definitely try to give answer. Trying to give you answer. In our book, we have shared this in a very detailed manner. If still you have confusion, you can ask us. So this is all about the 3-to-1 principle. Thank you. Thanks a lot. Hello everyone, this is Manish from Skillable India. In this session of geometric dimensioning and tolerancing, we are going to understand about the datum targets. So we are going to learn and discuss about the datum targets. In the previous session, we have already discussed about the how many datum types are there, what is the datum features are there, how can we use a feature and feature of size as a datum. So, but in few applications, when we have a raw material as a cast surface or a forged surface or a molded surface, so molded part, then we will not get a planar surface or a cylindrical surface. In that case, how can we use as a datum it as a datum? So in all such applications, we have to use something called the datum targets. So in all such applications, we have to use the datum targets. In GD&T, our datum target may be used to specify a point, line, or area on a part to establish a datum. So I will give you one example. If I want to bring this part into a stable condition, so first of all, what I will do is I will put this part onto a datum feature. Oh, sorry, datum. But still you can see that this part is not coming into a stable condition. So to make this part into a stable condition, what I have to do is I have to provide some points onto this part. Let's say 3 point contact onto this part to bring this part into a stable condition. So here I have given 3 point contact to come this part into a stable condition. So to all such applications that to make these part into a stable condition, what we do is first of all, in depth we will go. So this is sometimes necessary when a part feature is too large or naturally irregular. So it is already said that when we have to use feature is too large or naturally irregular. So here I have already given an example of a forged surface or cast surface or molded parts. So in all such applications we use this. So parts are to create a datum, or when a parts has an irregular contours, part that are cast, forged, or molded often benefits from the use of the datum targets. So the datum targets is to be place of contact, support of the workpiece for the manufacturing and inspection equipment. So what actually datum targets are? They are actually the support of contact, which are contacted with the contact with the workpiece. So how many types of datum targets are there? Datum targets are points. It can be a line or it can be an area. So basically 3 types of datum targets are there. First considered to be a points, line, and area. In area can be a circular shape. This can be an area. It can be a rectangular shape. This is also used as an area, and area can be a square shape also. So this can also be used as an area. So basically 3 types of datum targets are there. With the help of example, we will understand that how we provide the point, line, and area onto the engineering drawing to understand easily. So we will move forward. So I have already told you there are 3 types of datum targets. First is point datum target, line datum target, and area datum target, which can be a square, circular, or rectangular. Now, this is the symbol we use for the datum targets. So whenever we are using a point or a line type of datum target, we will use one circle and divide it into a two half. First half will be empty for point, it will be empty for point and line. In the second part, it will be written A1, X1, Y1, V1, any alphanumeric number any is given for point or line contact. For area, the same symbol is denoted. It is divided into two half. The circle is divided into two half. First of all, we will write let's say B1 for the area. In the upper part, let's say the area is a circular. So circular area has some diameter. Let's say dia 3. So what will have? I will write over here dia 3. In case it is a square shape, so I will write over square 3 like this. So this is how we should write the symbol onto the engineering drawing. Now one by one we will understand about the point, line, and area, and how we can, with the help of these three datum targets, point datum target, line datum target, and area datum target, how we make the part in a stable condition. So in this example, this is a 3D example in SolidWorks. I will show you in a very detailed manner. So in this example, you can see this is the example I have taken. So in this is the part. First of all, I will remove this part from here. Now, here three types of pins you can see. The first type of pin, which is in a pink color and having a spherical surface. So spherical surface making the point contact. So whenever it is touching to the surface, they are having the point contact. So these three pins having the point contact. Whenever these two pins which are touching the edge of the part, so these two pins are touching the edge. Edge means the edge of the part, the side of the part. So they are making the line contact, and these two pins, this pin and this pin, is making the area contact. So this whole area, the full top surface is touching the part. Now I will make the part visible and trying to make you understand that how all this is happening. So this is the part. Now you can see, first of all, we will see about the point contact. So I will make this part transparent. So you can see in this that this part is touching the point contact, having this part with the part. So with the part, these 3 point is touching. So it means this is the point target, point datum target. So in this you can see these 3 pins making this part in a stable condition. So already we understand that with the 3 to 1 principle that minimum 3 points are required for the primary datum to make the part in a stable condition. Now we will understand the line contact. Now till now we have understand about the point contact, that to make this part in a stable condition we are making the point contact. Now what is the line contact? When the pin is touching the side at a line. So you can see that this line is this point is touching over here. So if we see from this view, so from this view you can see that this is the line, this pin is touching at this line, this part. So this whole line is touching this part. Similarly in this case also, this pin is touching the part from this side. If we will see into this side, so you can see this is the part touching at this point. So in this blue, this pin is touching this part in this whole line. So this is the line datum target. This is the line datum target. First of all, we have understood about the point datum target. In this condition, one point is touching the part. Points are touching the part. In this, the line making this part in a stable condition, touching at 2 points. Now, now we will understand the third one, which is the area. So these two areas are touching the whole part, whole circular area. So you can see that this part is touching the whole area, not the point, not nor line. It is touching full area. So the part from the bottom, it is stable with the area. So as many as area we want, as per the requirement, we can use the datum target area to stabilize the part. So this is how, this is the three ways. It can be a square shaped area also, rectangular area also, to make this part stable. So however we use, so this is just an example to showcase that if I want to make this part into a stable condition. So how we can make this part into a stable condition? With the help of point contact, with the help of line contact, and with the help of area contact. So this is the area which is touching the part from the bottom. So if we want to make this part, so these are three datum targets, three types of datum targets to make the part into a stable condition. This is all about the this. Now we will understand with the help of engineering drawing. So here these are whenever there is a point contact. So point contact in terms of so I will make one line over here. So you can see okay, sorry. So you can see in this example that these are the 3 points. So this is the point, this point, and one more point is there. So this is the point, this 1 point, 2 point contact, 3 point contact. So here A1, A2, and A3 is shown by the point contact. A1, A2, and A3 is shown by the point datum target. These 2 points, B1 and B2, are the line. This is the line contact and this is the line contact. Okay. So in this case, B1 and B2 are used as a line datum targets. You can see that the upper part of the circle is empty. In this case, whenever we use the point datum target or the line datum target, the upper part of the circle will be empty. Only in case of the area, you can see these two examples, C1 and C2, where we have used the datum targets. If I will make, sorry. So you can see this, that these 2 points, one over here and one over here, we have used the area datum target. So in area datum targets, we are using the dia 5 mm, which is showing by this symbol. So these two, in this upper is the area. In this also area is showing. C1 and C2 is the number of this datum targets. So here in this condition, C1 and C2 are used as the area datum targets. I hope that you have the now the better idea about the datum targets, how we use the datum targets to make our part into a stable condition. And basically, when we use this for the in the case of forged part, casted part, or the molded part, we use these type of datum targets to make the part into a stable condition to do a machining onto the surface. So this is all about the datum targets. If you have any confusion, please write it down in the notes. We will definitely going to come up with the solution. So this is all about datum targets. Thank you. Thanks a lot. So hello everyone. In today's session of geometric dimensioning and tolerancing, we are going to understand about the topic which is about the angularity. So we are going to learn about the angularity tolerance. Angularity tolerance is the first tolerance in the orientation control. So this is the first orientation control, tolerance, which is angularity. Before getting into the angularity tolerance, please let us understand about the orientation control. So first of all, we will understand the orientation control. So whenever we have a feature or a feature of size, so whenever we have feature and feature of size is having angular relationship with the neighboring feature. So in that case, then we called it as a orientation control. So whenever feature and feature of size is having a relationship with the neighboring feature, angular relationship with the neighboring feature. So then we control it with the orientation control. If the angle is other than 0 degree, 30 degree, or 90 degree, 180 degree, and 270 degree, other than this, these angles, then that angle is called angularity. If these are angles are not there, so we can call it as a angularity tolerance. We can consider it into this. So in GD&T, the angularity is a three-dimensional GD&T callout that helps maintain a specified angle between a feature, line, or surface. Between feature and feature of line or surface, and a reference feature. So angularity is a control used to tolerance frame or feature control frame in the GD&T. It can be applied to a feature, surface, or to an axis. So angularity can be applied to a feature and feature of size for both, and it must be defined relative to a datum. A surface on its own cannot have an angularity with no other reference. So at least two features are required to provide the angularity tolerance. Angularity is the deviation from an ideal target angle, unlike perpendicularity and parallelism, which are specific cases of angularity. That angle can be any numerical value. So this is the GD&T symbol we use for the angularity, like this. A typical angularity callout is shown below the note that there must always be some reference in the third right box. So datums is the requirement. At least one datum is required to form to have a angularity tolerance callout. So here it is a datum A. This is the important for the practical application of GD&T. So datum is must required to apply the angularity or callout, because how you have to define and measure that datum could have a major impact on angularity control. So at least one datum is required for the angularity. From that, any angle can be measured. It can be 30 degree, 45 degree, whatever. So with the help of example, we will understand this. So an angularity callout can also be shown within the 3D model view. So in this is the example. This is the example we can discuss in very detailed manner. So let us take an example of angularity. Here is the planar surface, which is a feature is having a angle of 45 degree. So you can see this 45 degree angle between this surface. So this is the surface we are having 45 degree angle. So for this we gave the angular tolerance. It is other than the 0 degree, 30 degree, 90 degree, 180 degree, and 270 degree. So it is having 45 degrees. So we can consider it as a angular tolerance. So it is a related feature. So orientation is having a related feature. So this surface is having relationship with this surface. So these both the surfaces of the part, this surface of the part and the bottom surface of the part is having an inner relationship with each other. So this is a related feature. So we have to give the datum. So we have provided the bottom surface to the datum A. So we have given primary datum A. So this is considered to be the primary datum, because whenever we have to do a machining, whenever we have to inspect the part, we will take this datum into consideration. This is why into the orientation control, we have to provide the datums. So in this case of angularity, we have given the datum A as a primary datum. When we give like this interpretation, is there are two parallel lines. So in this example, you can see over here, there are two parallel lines, this parallel line and this parallel line. there are two parallel surfaces which are 0.01 mm apart. So in this, there is a tolerance we have given 0.01 mm apart. So this is the distance between these two parallel surfaces apart at an angle of basic of 45 degree. So I have already told you this is the angle which is 45 degrees. The actual surface lies within these two parallel surfaces. So this is the tolerance, and within this tolerance, the actual surface is lying within this tolerance. So here, can we have the surface like? So you can see it can have a surface like this in between this, but it should be within the tolerance zone, within these two parallel surfaces, which are apart 0.01 mm over here. Any tapered surface can be considered to be right if it is within the tolerance zone. So you can see in the middle line is the actual surface of the part, which is not exactly at 30 degree, because if it is in any angle, it will be not in a 45 degree. Some angle will be different, but it is into a tolerance zone. So, but the surface lies within the two parallel planes, which are 0.01 mm apart. Then we consider that the surface is maintaining the angularity. So then we can consider that this this center surface is maintaining the angularity tolerance, also controls the form in this case. So this surface is also controls the form. Why? This seems the surface is a planar surface. You can see this surface is a planar surface. It will control flatness of the part particular surface. So it will also control the flatness of the part. So here we can have an example where it is a plane surface with different angles. And one problem is also there, that the consideration is also there, that the surface can be like this. After manufacturing the part, in the two middle planes, we can have end up with the surface like this also. So here also again there are two parallel planes. So this parallel plane, which is 0.01 mm apart. The actual surface lies within the two surfaces. So the flatness maintaining between these two surfaces, and angle is also maintained at 45 degree. So this is about applying the angularity to a feature. So in this case, we have applied angularity to a feature. We have already learned that angularity can be applied to a feature, and angularity can also be applied to a feature of size. So now in this case, we have understood about the feature, that if the within the tolerance zone, if then the angle is considered to be in a right. So this is for the angularity to a feature. Now we will understand angularity applied to a axis or to a feature of size. Whenever we are talking about the axis, so we are talking about the feature of size. So in this case of a circular feature of size, such as a cylindrical pin or a hole, the zone is expressed as a cylindrical zone. So in this example, you can see that this is a hole, and this hole is having an axis at the center. So this axis, this axis is having a cylindrical zone, tolerance zone. So in this case, dia 0.01 mm is a cylindrical tolerance zone around the axis of the solid feature. This zone is aligned to a basic angle with respect to the datum. So in this case also, the bottom surface, we have given it as a datum surface. So in this case, you can see that this is the primary datum. We have given into the feature control frame also. So here in feature control frame, we have already given the datum. So in this case, what we have, there is a hole at an angle of 45 degree. So you can see this angle, we have provided 45 degree. So this angle is at 45 degree. And so for that, we can apply the angularity tolerance, which is 0.01 mm apart. So in this case, this tolerance zone, which is in pink color, so this is the tolerance zone, which is 0.01 mm apart, which is having a reference of datum A. So whenever we give like this, then we get a cylindrical tolerance zone of 0.01 mm in this drawing at the center, which I have represented over here. So the actual whole axis lies within this cylindrical of 0.01 mm. So wherever the axis will lie, but it should be within the tolerance zone. It can be in a taper, but the axis should be in a tolerance zone. So here the actual axis of the hole is not exactly at 45 degree. So this axis will not be at 45 degree, but the axis is within the diameter cylinder of 0.01 mm, which is this. So this is how we get the angularity of a feature of size. So so you can see over here in the feature control frame, angularity which is maintaining at this. So whenever we apply the angularity to a feature of size, then we can write it, use the material condition modifiers. Then we can use the material condition modifier. So in this case, if we are using plus minus dia 15 plus minus 0.01 mm. So in this case, you can see that at maximum material condition at 15.01, we have the tolerance zone of 0.01. At 15.02, we have the tolerance zone of 2. And at, when we move towards the tolerance zone, when at 15, we have the tolerance zone of 0.02, and at 14.99 we have the tolerance zone of 0.03. So as we move from maximum material condition towards least material condition, we get the more tolerance over here, because we have applied the maximum material condition modifier over here in the feature control frame. So this is how whenever we apply the angularity to a feature of size, we can apply the material condition modifier. So when the diameter is at mmc, so it will have 0.01 mm, and when it will move maximum material condition to the least material condition, the tolerance zone will increase. So this is all about the angularity tolerance when we apply angularity to a feature and when we apply to a feature of size. So this is all about the angularity tolerance. In the next discussion, we will learn about the second tolerance in the orientation control, which is about the perpendicularity, and next parallelism. So this is all about in today's session. Thank you. Thanks a lot. Hello and welcome everyone. In this today's session of geometric dimensioning and tolerancing, we are going to learn about the second orientation control, second tolerance in the orientation control, which is the perpendicularity. So first of all, we will discuss about the how to applying the perpendicularity to a planar surfaces. So in this then we will discuss how to apply perpendicularity to a feature of size. First, we will apply that how we can apply the perpendicularity to a planar surface or feature. Then we will understand about the feature of size. So first of all, what is the definition? In this, perpendicularity is a fairly common symbol that requires. So whenever we are talking about perpendicularity, we are talking about 90-degree angle or 270-degree angle, which is perpendicular. So whenever two surfaces are perpendicular to each other, this is called the perpendicularity. So perpendicularity is a fairly common symbol that requires reference surface or line to be perpendicular or 90 degree from a datum surface or line. Perpendicularity can be reference a 2D line, but more commonly it describes the orientation of one surface plane perpendicular to the another datum plane. So with the help of example, we will understand that how one surface can be considered as a datum and the other surface as with reference to this surface can be perpendicular. So we will understand with the help of example. The tolerance of perpendicularity call out indirectly controls the 90-degree angle. So the most important part is to control the 90-degree angle between the parts by controlling the location where the surface have to lie. now see the tolerance zone below for the details. So perpendicularity does not control the angle of a reference feature. The tolerance is in the distance unit. So it is a relative to datum. Yes. So this is a relative feature. Perpendicularity is a related feature. So MMC or LMC is applicable, yes. In the case of when we apply the perpendicularity to a feature of size, the maximum material condition and least material condition is applicable. So, and this is the symbol for the perpendicularity. So whenever we are using the symbol like this in the feature control frame in the first compartment, this is the perpendicularity. This is and we can provide with the reference to datum. So whenever we are applying any orientation control tolerance, so in that case we have to apply the datums. Datums are the required because datum this is a related feature, related tolerances. So for related tolerances, at least we required one reference. So at least one datum we required for the relationship with for the surface or the feature. So this is the most important part. Now in this example, you can see this feature is at 90 degree. So this is the line. So this is the of the feature of the line. This is the center line, and this is the datum surface. Okay, so we have provided the datum A to this surface, to this bottom surface we have taken as datum. So now in this example, so here I should not show the 90 degree angle. Why I am not showing the 90 degree angle over here? Because as per the fundamental rules in the second section of GD&T, we have learned that if you remember the fundamental rules that tells whenever there is a 90 degree angle or a perpendicular angle between the two surfaces or the two features which are right angle to each other. So other than we are not supposed to show the angle. So it is the default understood that there is a 90 degree angle. So this is a default. We understood that if there are two perpendicular feature, so they are at 90 degree. So whenever we have surfaces at 90 degree or 270 degree, so here and just for the showing, we are talking about this 90 degree. So whenever we are talking about 90 degree or 270 degree, then we can apply the perpendicularity tolerance. So in this case, we can apply the perpendicularity tolerance. So in the feature control frame, I have used the perpendicularity tolerance. So if we have like this datum surface A, so in this case, this datum surface A. So in this case, you can see this is the datum surface A. There are two parallel planes. So in this case, there are two parallel planes, this plane and this plane at a distance of, this is the distance, so 0.01 mm apart. So these two planes are 0.01 mm apart, perpendicular to the datum surface A. So always whenever we are talking about this, this actual surface takes any shape with these two parallel planes. Okay. Maybe between these two parallel planes, a surface can lie between like this. It should be within the two parallel planes, but it will be under the tolerance zone. So if you see this middle line, which is not exactly perpendicular, it is in taper. So you can see this line is in taper, but this line is between the two parallel planes within the tolerance zone. So, such surfaces are considered to be perpendicular. Okay. So although this is not perpendicular with the datum, but if this is under the perpendicular tolerance or the, I will say, the control which we have provided, so the surface is considered to be perpendicular to the datum surface. So now we will understand. So I think you understand about the two parallel planes. So whenever the tolerance, the surface is within the tolerance zone, and within the tolerance zone, so here the tolerance zone is 0.01 mm. If the surface is within the tolerance zone, it is perpendicular or not, it will be considered perpendicular with the datum surface. Now we will understand. So in this case, we have applied perpendicularity to the surface to a feature. Now in this example, which is perpendicularity applied to a axis. So in this case, we are applying perpendicularity to a axis or a feature of size. So this is a feature of size. In this case, we are applying feature of size. So access control can also be called out for the perpendicularity and is one of the more common forms of access call out. So in this case, sorry, this size is taken as the 15 plus minus dia 15 plus minus 0.1. So in this case, this is the size of the hole. And at the center of this hole, there is one axis. You can see this axis. So this is the axis and we are controlling the this axis. So when it is referenced for a circular feature, so in this case, this hole we are controlling the perpendicularity of this hole we are controlling. So as we control the axis of the hole, the perpendicularity will be in control. So the feature control frame will contain the diameter over here. So in this case, I haven't used diameter, but there is diameter 0.01, or you can say for understanding, I am taking another feature control frame, let's say. So I am using the first of all, in the first compartment, I am using the perpendicularity symbol, which is a geometric characteristic symbol. Then we are using 0.1 mm of geometric tolerance. Then we are applying the datum. So this is the datum A, which is this surface. So we are taking datum A as a primary datum. Now, as we are applying the perpendicularity to a feature of size, so this is very commonly known, and I have already told you a lot of times that whenever we are applying any geometric characteristic or geometric tolerance to a feature of size, then it is possible that we can apply the material condition modifiers. So in this condition, we can apply maximum material condition and the least material condition. So when the axis perpendicularity can be applied to a positive feature when or was, or a negative feature, a hole. So when perpendicularity is referenced for the axial control or a feature, a symbol now specify a cylindrical boundary. What this cylindrical boundary means, you can see this red over here. So this is a cylindrical boundary. So if we see from the top, so this is the axis, this point you can consider as an axis, and this is the tolerance zone. So in this case, this is the axis, this point can be considered from top view if we see, and this whole diameter, we can say 0.1 mm, which is over here. So we can say this is the circular tolerance zone. So in this case, you can see this is the circular tolerance zone. So this is the cylindrical boundary where the axis of the reference feature must lie. This cylindrical boundary is formed by taking a line that is directly perpendicular to the datum feature. So when this version of the perpendicularity is called out, it is to be used with the maximum material condition to enable easy gauging of the part. So in this case, I have already told you, you can use maximum material condition modifier and least material condition modifier. So whenever this hole is manufactured at maximum material condition. So in this case, maximum size of the hole is 15 plus minus 0.1. So maximum material condition of the hole is 15.1. So at 15.1, the tolerance is 0.1 mm. As we move from MMC towards LMC, LMC is dia 14.9. So sorry, we are talking about hole in this case. Sorry. So in this case, maximum material condition will be 14.9. So at 14.9, when there is a maximum material condition, the tolerance zone will be 0.1 because this is a hole. And whenever when the size is 15, the tolerance zone will be 0.2. So when we are at LMC, which is 15.1, the tolerance zone will be 0.3. So as you can see, we are moving from MMC to LMC. The tolerance zone is increasing. This circular tolerance zone at 15.1 dia will be 0.3 mm. So as we move from maximum material condition to the least material condition, we should increase the material condition modifiers. So this is the very important part of perpendicularity tolerance. So the meaning of this is that the cylindrical tolerance zone we are getting, which is I have already told you. So this is all about the perpendicularity tolerance. When we apply perpendicularity tolerance to a hole, we are controlling the axis of this hole with the reference to the datum feature. So this is the datum surface and this is the axis. So let's say if it is in taper also, let's say this is in a taper. So axis is in taper, but it is into the tolerance zone. So if it is in a tolerance zone, this is the tolerance zone 0.1 mm. So this 0.1 mm. If it is in taper also, it will be considered to be a perpendicular because it is in a tolerance zone, this axis. So if it is out of the tolerance zone, then we can say that the perpendicular is out of this hole. So this is all about the perpendicularity tolerance. I hope that you understand the topic in a very detailed manner. If you have any confusion, you can also write it down for the in the notes section. So definitely we will try to answer that. So this is all about. Thank you. Thanks a lot. Hello and welcome everyone. This is Manish from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to start with the parallelism. So in this particular session, we are discussing about the parallelism. Whenever the relationship between the feature is 0 degree or 180 degree, then we can apply the parallelism. So we can only apply at 0 degree or 180 degree. So we can apply the parallelism. So parallelism is the third geometric control under the orientation control. So this is very important. And with the help of definition, we will understand this, that parallelism is a 3D geometric dimensioning and tolerancing orientation tolerance, which maintains that two part features are parallel to each other. So why we are saying that two part feature, we are talking, when we are saying two part feature, we are talking about the surfaces, two parallel surfaces. So whenever there are two parallel surfaces of the part, let's say these are two parallel surfaces. So these can be considered as two parallel surfaces, and one we can take it as a datum. So at one, we can use it as a datum, and with reference to datum A, we can check the parallelism of this surface. So we can apply the parallelism tolerance in case of with the reference to datum A. So you can use it to control center lines. So we can use for this center lines, center planes, cylindrical or and planar surfaces. So not only for planar surfaces, we can use this tolerance for the cylindrical surfaces also. Surfaces parallel to datum elements. So one reference element is required. In this case, we are using the datum reference. So any feature is going to be parallel with another feature. So this is a related tolerance zone. So this is the related tolerance. So here related to the datum, yes. So we know that orientation control, all the three orientation control, either it's angularity, perpendicularity or parallelism. So all the three tolerances are in the related tolerance zones. So they are relative to the datums. Maximum material condition or least material conditions are applicable because this orientation controls in this parallelism can be applied to feature or feature of size. So whenever we are talking about the feature of size, then we can apply the maximum material condition or the least material condition modifiers in the feature control frame. So in the second compartment of the feature control frame, we can apply the maximum material condition or the least material condition modifiers. This is the symbol. So whenever we are using two lines under the square, so this is the symbol of parallelism. So this is the most important part. Now with the help of example, we will understand. So this is a top surface. You can see in this is the top surface of the part. Feature is having 0 degree with the bottom surface. So this surface, this top surface is at 0 degree with the bottom surface. So you can see these both the surfaces of the part are parallel to each other. This surface and the bottom surface of the part are parallel to each other. Now in this case, what we are going to apply, so you can see This surface can be applied with parallelism. So we have already know whenever there is a 0 degree or 180 degree, so we can go with the parallelism tolerance geometric control. With 0, you can see that with 0.1, this is the feature control frame. In this feature control frame, we have used the parallelism, and 0.1 mm of tolerance we have given over here with reference A. So you can see the bottom surface of this part I have used as a datum, because this is a relative feature related tolerance. So we want the datum. So in this case, the bottom surface I have used as a datum to check the parallelism of this upper surface. So whenever we have a drawing like this, the interpretation is from the datum surface. So this is the datum surface. There are two parallel planes parallel to datum A. So you can see that this 0.1 mm, so this 0.1 mm apart. So there are two parallel planes. So these I have shown over here in this line. So these are the two parallel planes parallel to datum A, which are 0.1 mm apart. The actual surface have to be within the tolerance zone. So when whatever the tolerance will be, the tolerance should be within the tolerance zone. It can be anywhere between 0.1, but it should be in, it can be in taper position. It can be like this also. But the thing is, it should always be within the tolerance zone. So the center is actual surface, which is not exactly parallel. So if this is a taper surface, so it is not going to be parallel with this surface. But it is within the two parallel planes. This parallel plane and this parallel plane. So the surface is within the two parallel planes of 0.1 mm apart. The actual surface is considered to be parallel with the surface A. So this is also considered to be parallel with the datum A surface, because it is within the tolerance zone. So tolerance zone for parallelism applied to a surface, two parallel planes. So this is very important. So whenever this is a case, if it is in a bit within the tolerance zone, so it is acceptable. So the parallelism tolerance we have applied in the first compartment of the feature control frame. In the next compartment, 0.1 mm tolerance, and with reference to datum A. So this is the most important one. Now this is for the while we are applying parallelism to a surface or a feature. So when we are applying parallelism to a feature, we don't have want the we cannot take the maximum material condition or the least material condition or the material condition modifiers. In the next example, when we are applying parallelism to a axis or to a feature of size. So for if we are applying axis, so this is the feature of size. So whenever we are applying parallelism tolerance to a feature of size, so here we have an example. So with this example, we will understand of parallelism applied to a feature of size. So there is a hole. You can see this hole. In this example, you can see this is a hole over here. This is a 2D overview. So the axis of the hole is parallel to the datum A. In this case, also the bottom surface we have used as datum A. So it is shown over here datum A. So the axis of the hole is parallel to the datum A. So what the axis of the hole is going to be parallel with the datum A. Then we can apply the parallelism, because this is also 0 degree with the it. In this case, this hole which is having 0.1 mm of tolerance. So this 0.1 mm having a diameter 0.1 mm diameter. This is tolerance zone 0.1 mm diameter. So to the actual meaning of this, there is a cylindrical tolerance zone. So in this case, this is whenever we are talking about the whole axis, so there is a cylindrical form of tolerance zone, not two parallel planes. In the previous example, we have seen two parallel planes are there, but in this case, there is a diameter 0.1 mm of tolerance zone. So you can apply like this also over here, diameter symbol. So which is parallel to datum A, the zone dia is 0.1 mm. The actual axis of the hole must lie within the cylindrical tolerance zone. So whenever, if there is a axis deviation, let's say, sorry, there is a axis deviation. it is in taper size. But if it is within the tolerance zone, if this tolerance is within the tolerance zone axis, so it will be considered as a uh, parallel with the datum A. So the axis of the is now considered to be parallel with the datum A if it is within the tolerance zone. As usual, parallelism is applied to a feature of size in this case. So we can apply the maximum material condition over here. So this is the symbol you can see over here. We can apply the maximum material condition or the least material condition modifier. So in this case, if the hole is produced, let's say if I am using plus minus 15 plus minus 0.2, let's say we are applying. So at for hole, maximum material condition will be 14.8. So when 14.8, tolerance will be 0.1 mm. The geometric tolerance will be 0.1 mm. When we will move from MMC towards LMC condition, which is 15.2, the tolerance will be 0.5 mm. As we move from MMC towards LMC, we will get more and more tolerance because we can apply the maximum material condition modifier. So we are getting the bonus tolerance, and I have already told you that how we can calculate the bonus tolerance by adding up the geometric tolerance to the size. So this is all about the parallelism we can apply to a feature or a feature of size. So if you have any confusion, you can write it down to the notes, and definitely we are going to discuss that problem. So this is all about parallelism. In the next section, we are going to move towards the position tolerance. So this is all. Thank you. Thanks a lot. Hello and welcome everyone. This is Manish from Skillable India. In today's session, we are going to learn about the very important geometric tolerance, which is the positional tolerance in the geometric dimensioning and tolerancing. So now we are going to discuss about the positional tolerance. One of the first, I will say, geometric tolerance under the location control. So first of all, we are starting from the location control. This is the first tolerance, which is the position tolerance. This is one of the most important geometric tolerance out of all the 14 geometric tolerances. So in this discussion, for the positional tolerance, first you have to be understand totally about the coordinate tolerancing system. So I will recommend you to just go through with the my session, which is I have conducted on the coordinate tolerances. So now we have to start with this. So we are going to start with the definition. So true position or just a position as per the ASME by 14.5 standards calls it is defined as the total permissible variation. Here from the total permissible variation that the feature can have from its true position. So this position means that the total permissible variation, how the feature, in this case, I will consider a hole as a feature. So if we considering hole as a feature, so a hole is what type of total permissible variation of that a hole can move from its true position. Let's say if I'm making here one part and this is a hole inside that part. So in this definition, it is trying to say the total permissible variation. So the total permissible variation is for this hole that a hole can have from its true position. So let's say this is the true position. If I am giving the size, let's say from here and at the center of here is 25 mm, and from here also from center, if the distance is 25 mm. So if it is moving, how much permissible tolerance we can provide it to this feature that the it should be not it should be functionally acceptable. So this is most important part. The true position is the exact coordinate. So in this case, true position is the exact coordinate. So if I am moving, let's say this point is considering I am 0, 0, and the coordinates at the center of this hole will be 25, 25 for this coordinate tolerances. If I am considering that, so that these 25, 25 is the exact coordinates or the location defined by the basic dimensions. So whenever we are not giving like this, so we are putting, I will show you in the steps that how we provide the basic dimensions inside the box. or other means that represent the nominal value. In other words, nominal value is the exact value. I have already told you what is the nominal value in the geometric dimensioning and tolerancing or the dimensioning system. Nominal value is the exact value of the dimension. So in other words, the geometric dimensioning and tolerancing, position tolerance is how far your feature location can vary from its true position. So how much tolerance we can provide it to this feature, to this hole, that this hole is functionally acceptable, or it should be made with the other mating part, like shaft. So it should be like pin. So pin should be enter into this hole in the in the proper tolerances. So it is a related tolerance. Yes, the position is a relative tolerance. So we have to provide the datums. So primary datum, secondary datum, and tertiary datum, all three we can provide in case of positional tolerance, because it is a related tolerance. MMC or LMC applicable? Yes. So as we all know that if we are providing the tolerance to a feature of size, in this case, if we are providing for a hole, so it's a feature of size to the axis, because axis of the hole is moving. So whenever we provide the tolerance to a feature of size, we can apply maximum material condition or least material condition modifier to the hole into the engineering drawing. So yes, we can apply the maximum material condition and least material condition. This is the symbol for the positional tolerance. So whenever we are making this symbol in the feature control frame, so first of all, in the first compartment of the feature control frame, we have to make one symbol. So this is for the position tolerance. Now here we have the now here with the help of we will understand that how we can steps to convert coordinate tolerance into a positional tolerance. Whenever we have to convert a coordinate tolerance drawing into a positional tolerance drawing, so what are the steps we have to follow in the conversion? So one by one we will in the first of all, what we have to do is give the dimensions with the feature of size, convert it into basic dimensions. So the coordinate tolerance dimension, we have to convert it into the basic dimensions for the feature of size. I will let you know with the help of example only. The second step is position tolerance is a related feature. Positional tolerance is a related feature. So we have to provide the datums into the drawing. Now the third step is we have to provide the feature control frame, because whenever we are converting coordinate tolerances into a geometric dimensioning and tolerancing positional tolerance, so we have to provide the feature control frame. Now with the help of example, we will understand. So this is the example. This is a coordinate tolerance example, and this is how we convert it into the positional tolerance. So where all the tolerances are given in plus one minus, in this you can see in coordinate tolerances, all the tolerances given in plus and minus tolerances, 100 plus minus 0.1, 50 plus minus 0.1 in this case also. So all the tolerances are given into the plus and minus tolerances. Now we have to convert these tolerances into a GD&T. So how we can convert this into positional tolerance? So we all know that if you want to overcome all the shortcomings which we face into the coordinate tolerancing system, the positional tolerance is the only way by which we can come out of it. So the positional tolerance is something to get the position of the feature of size. So in this case, if we are talking about the axis, so axis is considered to be a feature of size. So to get the position of the feature of size, in this case, it is a hole. This is a hole. So here I want to get the position of this hole, let's say. So here, then I have to use the positional tolerance to do so. So for this hole, these both the drawings are similar. So for this hole, first of all, we are talking about. So you have to convert the coordinate tolerancing system into a positional tolerance system. So what you have to do is, there are three steps which I have already told you that involves. The very first step is give the dimensions. So if we are converting this into this, so first of all, we have to provide the dimensions. So 100 plus minus 0.1, we will similarly write into the drawing 100 plus minus 0.1. For this also, let's say 200 plus minus 1. In this drawing also, overall size we will write same 200 plus minus 0.1. Now So the overall dimension remains same of the part. In the coordinate tolerancing system and the positional tolerancing system, overall dimensions of the part always remain same. So these are the overall dimensions. 200 plus minus 0.1 and 100 plus minus 0.1. Next is the coordinate for the whole. So you can see 50 plus minus 0.1 and 50 plus minus 0.1 are the coordinates of this whole. Coordinates of the whole. When it comes to the coordinate, there is a small change. Instead of giving same tolerances, we have to put the dimension inside the box. So you can see this box. We have put these dimension inside the box. Inside the box, which is called the basic dimensions. So this is the very first step, that we convert these coordinates into a basic dimensions and put these without tolerances. We have put this into the box dimensions. This is the first step. First of all, this is the first step to convert the coordinate tolerance drawing into a geometric tolerancing or the positional tolerance. Now, second step is in this positional tolerance is a related feature. We all know that the positional tolerance is a related feature. So first we have to provide the datums. In this case, datum, primary datum A, secondary datum B, and tertiary datum C. So in this case, there are no datums. So in this coordinate tolerancing system, there are no datums. So I have to take 3 datums in this particular case. So the back surface, you can see the back surface of this part. So this is the, I will say this is the back surface of the part. This is the part side drawing. So this surface is taken as the primary datum. So I have written over A over here. Now this surface is, we are considering this surface of the part, we are considering it as datum B. And this surface of the part, the bottom surface of the part is considering we are datum C. So this is how we can provide the datums. In the case of primary datum, secondary datum, and tertiary datum. So now we have given all the datums into the part. So this is the second step. In the first step, we have converted the dimensions into the for the coordinates of the whole. We have converted into the basic dimensions. So that is the first step. In the second step, what we have done is we have provided the datums to the part. In the third step, which is third step, is to give the feature control frame. So this is the feature control frame. In this case, you can see there are no feature control frame, but in geometric dimensioning and tolerancing, you can see that we have to give the feature control frame. So first of all, we will write down the positional tolerance symbol. So this, in the first compartment, we have written down the feature control positional tolerance symbol. In the second compartment, you can see there is a tolerance. Now I will show you that how I have calculated this tolerance. Then there is a material condition modifier, because it is a related feature and we have provided the tolerance to a feature of size. So we can apply the maximum material condition and least material condition. And other 3 compartments, 4th, 5th and 5th, 6th, third, 4th and 5th compartment are for the primary datum, secondary datum and tertiary datum, which we have provided into the drawing. So first of all, how do we decide this value? How do we decide this value of 0.28? So in this case, I will let you know that in this case for coordinate tolerancing system, the center have square shape tolerance. So in this case, you can see that it is plus minus 0.1. So the tolerance is of about 0.2 mm. In this case, also 0.2 mm. So there is a square of tolerance which is 0.2 and 0.2. So this is a square tolerance zone. This is a square tolerance zone which is 0.2 mm in this side and 0.2 mm this side. Now, how we calculate this 0.28? We have to, this is a 90-degree angle. So what we have to do is we have to measure this diagonal. So we can measure this diagonal, and with the help of Pythagoras theorem, this as a perpendicular you can take, this is a base, so hypotenuse you can calculate. So in this case, the diagonal of this square is equal to 0.28. Sorry, 0.28. Now what we do is we will make through this diagonal, we will make one circle in the tolerance zone. So in this case, you can see how we have converted this square shape tolerance into a circular tolerance zone. So you can see this tolerance zone. Now I have made the with the help of this diagonal, I have created a circular tolerance zone. So this is a circular tolerance zone which we have calculated over here. So now we get more tolerance. In the red area, you can see this is the more tolerance we are getting. In this case, in the coordinate tolerance system, if the point lies over here, something here, x is over here, the part will be rejected. But in this case, when in the case of positional tolerance system, you can see when the part lies within the red circle, the part will be accepted. So that's why we are getting more tolerance in the case of positional tolerance, because we are using the diameter all over the circle. So 0.8, similarly, we are using this as the positional tolerance. So this is the positional tolerance. We have converted the square shaped tolerance zone into a circular tolerance zone. With the help of this, we get more tolerance out of it. So here we have a, you can see this. So this is how we calculate the circular tolerance zone. So in this case, we have written over here 0.28 mm, or if we round off, so you can use the 0.3 mm in this case also. So then ambiguous instruction for inspection is not required. So ambiguous instruction, we don't have to write notes onto the drawing for this. It is clearly shown that for inspecting the part, what we have to do is just if we have to measure this hole, so it is clearly shown that first of all we have to put the part with this side primary datum, and if I will tell you check the value of x direction we get the different value. So in this case, if you measure the center axis of this hole, so there are no datums in this part. You can measure it from here also, and you can measure it from here also. So both the things can happen, or you can measure it from here also, and you can measure the center axis from here also. So there are four ways. So somebody will measure from here or here, so the value will come different. So that's why to resolve this problem, so we have provided the datum. Now if somebody has to inspect this part, where in case of positional tolerance, if somebody has to inspect this part, if the inspection is done, so with the help of feature control frame, a person will dedicatedly know that first of all, we have to put the part from the primary data. Then we have to check from here, from this position, because I have written over here, this is the secondary datum. So this surface is the secondary datum. So first of all, he has to measure from here. Then this is considered to be the tertiary datum. So then the person will measure from here, the part. So it is clearly shown by this datums. In this case, there are no datums, and there is a confusion for the inspection of this part. But in this case, all the datums are provided. So we know that we have to measure it from the left side and from the bottom to top. So from left to right and bottom to top. So we cannot check from the other sides, because I have taken the two surfaces as a datum. This surface as a datum and this surface as a datum. I have already taken. So if I add over here maximum material condition modifier, because it is a we have provided the tolerance, positional tolerance to a feature of size, which is only the case. So we can provide the maximum material condition and least material condition modifier. So in this case, I have used maximum material condition. So I will get flexibility also. So if the part is produced at a maximum material condition, so in this case, maximum material condition will be 39.9. So if the part is produced at 39.9, the tolerance will be 0.28 or 0.3 if we round off this tolerance. If the part will move from the maximum material condition towards the least material condition, let's say 40.1 will be the least material condition for this hole. So it will add up 0.48 will be the tolerance zone. So this is how we get the more and more tolerance zone with the help of maximum material condition modifier. So this is all about the positional tolerance. With the help of one more example, we will be discussing about in detail that how we can calculate the positional tolerance with the help of formula also. So this is how this is all about the positional tolerance system. And in the next discussion, we will discuss about the verifying the positional tolerance. So thank you. Thanks a lot. Hello and welcome everyone. This is Manish from Skillable India, and in today's session we are going to discuss about the projected tolerance zone. So in most of the cases we use positional tolerance, but just giving positional tolerance is not sufficient in many cases. So here we have example. We will learn about the projected tolerance zone. So what is the projected tolerance zone and why we use the projected tolerance zone? So all the things with the help of example also we will understand this. First of all, I will be discussing about the definition. So the projected tolerance zone symbol is used. This is the projected tolerance zone symbol. Okay. So whenever we are using P in a circle, so this is the symbol of the projected tolerance zone. Projected tolerance zone symbol is used in geometric dimensioning and tolerancing to indicate the tolerance zone of a feature is to be assessed beyond the surface extent of the feature. Means this is trying to say that and the tolerance zone of a feature is outside the feature, not inside the feature. Whenever we are using the word projected tolerance, so it is not inside the feature. The tolerance zone is not inside the feature, it is outside the feature. That's why it is saying assessed beyond the surface extent of the feature. In most of the cases, this symbol is used to verify that the fastener will still clear a mating part during assembly, regardless of how thick the assembling part is and the orientation in which the fastener is assembled. I am just giving a simple example. Let's say there is a fastener, there is a bolt, and there are two parts. Part 1 and another part, which is the part 2. These both are having, this is a free hole in this part and this is a threaded hole. So in this, there are two holes are there. There are threaded hole. This is the threaded hole part and this is a free hole part. And one fastener is need to be assembled. One fastener is need to be assembled with one another. So let's say there are two plates and we need to join these two plates with the help of fastener. So what are the problems we will face in this projected tolerance? Why we use this projected tolerance zone while this assembly with the part 1 and part 2. So this is with the threaded hole. So this is a threaded hole plate. And this is a free hole. And we need to assemble this fastener. Let's say this is a M6 bolt. M6 bolt we need to assemble within this. So there can be a problem that this hole are not in a position. So the position and the axis of the hole, let's say these both hole are having axis. These both the holes are having geometric tolerances. So circular tolerance zone is there. We already have discussed that whenever we are providing tolerance to a hole, we are providing to a feature of size which is a axis, and axis will have a circular tolerance zone. So in this case there is a circular tolerance zone. So whenever there is circular tolerance zone, the axis can be in a taper also. So let's say this is a circular tolerance zone. So axis can be in a taper also. So if the axis of the hole will be in taper, when we fix the fastener with the within the plates, so it will also go in a taper position. So let's say with the help of example we will understand. So this is the example. So in this is the part plate 1 with the hole. This is a height of 20 mm. Then this is a second plate, part 2, which is having a threaded. These are the threads. So this is having a threaded hole in this case.
So one part with the free hole. So this is one part with the free hole. This is with the free hole. And one part with the threaded hole. So this is with the threaded hole. And we need to assemble a bolt. We need to assemble a bolt within this. Uh, so we have given the positional tolerance by using the fixed fastener formula. So in this case, what we have used is fixed fastener formula to assemble this bolt. We will discuss in a later stage. So if you see, you can see this for the free hole, the positional tolerance is 0.3 mm, and we have used this is the positional tolerance. And in case of threaded hole, there is a M6 hole and positional tolerance is of 0.3 mm for both the holes. So in spite of giving positional tolerance and controlling the position of the hole, after manufacturing, we may end up part like this. So this is the condition. So you can see this is the condition that after manufacturing, there is a interference, okay? Because if we see from the top, this axis having 0.3 mm of tolerance zone. We are having 0.3 mm of tolerance zone. Dia 0.3 mm for this axis. Okay. So if we are considering, let's say this is a, I will take little big to understand. So it is like this. This is the tolerance zone, let's say. This tolerance zone, this is the axis. So axis make in a taper position. If the axis will be in taper within the tolerance zone, it will be accepted. But if it is a problem that it is not in a tolerance zone and the part will interfere, here it will interfere, it will not bolt it properly, and it will interfere here also. So when we try to assemble bolt, the bolt may not enter properly. So this may fall with this part here. So you can see that it can be fall in here, it can be fall in here. So the proper bolting is not be done. So in this case, just by giving positional tolerance, we are not able to assemble this bolt. Just by giving positional tolerance, we are not able to assemble this bolt properly. So in such cases, we have to overcome the issue by two methods. So to overcome this issue, we have two methods. So we have two methods. One by one, we will understand these two methods. So first method is we can use projected tolerance zone. So in this case, we can use the projected tolerance zone, or the second one, we have to increase the diameter of the free hole. So in the first case, we can provide the projected while manufacturing the part 2, we can provide the projected tolerance zone. This is the method 1. Projected tolerance zone to this part. How we can do this, we will understand. In the second case, in the second method, we can increase the size of this free hole. How we can increase the size of this free hole in the second method, and how we will calculate that what should be the diameter, exact diameter that the part that the bolt should be assembled easily. So we will also know with the help of I will say with the help of formula. So we will understand that how we can calculate the diameter of this free hole to enter the bolt properly. So first, in the first method, this is the first method. In this particular session, we will discuss the first method of how to give projected tolerance zone to overcome this problem. So whenever we give the positional tolerance, in this case, you can see that we have given the positional tolerance 0.3 mm to this whole threaded hole. This will understand the what is the meaning of the first before getting into the projected tolerance zone. So here you can see that this is the part. So if we are manufacturing this part, and this hole is manufactured like in taper shape, this is threads. So the axis will be also in taper,
And the tolerance zone, what is the tolerance zone for this? The tolerance zone for this circular tolerance zone will be 0.3 mm because we have written over here. So for this whole manufacturing, for this whole, we have tolerance zone of 0.3 mm. So this is the meaning of this feature control frame that with the help of that we are manufacturing. And this surface we are taking it as datum A. So we are using this datum A. So here is the part like this. Then we have the tolerance zone of 0.3 mm diameter. The axis of the threaded hole must lie within this 0.3 mm. So because of which the threaded hole will be at some angle. So the orientation will or the perpendicularity in this case is 0.3 with reference to the datum A. If we are taking datum A like this, so the orientation or the perpendicularity of the in this case will be 0.3 with reference to the datum A. Because of this, only we are facing the problem of bolt not sitting with the mating part. So you can see that in the previous case, the bolt is not sitting properly with the mating part. To avoid this, what we can do is add a modifier. So in this case, what we will do, we will add one modifier in this feature control frame. We will make one another feature control frame. So in the first compartment, the positional tolerance 0.3 mm maximum material condition. One more modifier we will use, which is projected tolerance zone modifier with datum A, B and C. So we have used the one more modifier, which is projected tolerance zone modifier. What does this mean? That whenever we are manufacturing the part 2, so for this just putting a symbol is not enough. Then we have to give the height for which the tolerance zone must be projected. So in this case you can see that we have already used the projected tolerance zone modifier. So dia 0.3 maximum material condition, projected tolerance zone, datum A, datum B, datum C, primary datum, secondary datum, tertiary datum. So in this we have given that at some height, initially what we give is the height will be equal to the mating part. So here the mating part height is 20 mm. So whenever we are manufacturing the part 2, so we will give the projected tolerance zone at a height of 20 mm, so that the axis of this hole will be in a position. So at 0, this is a cylindrical tolerance zone 0.3 mm, but it will be through 15 mm plus 20 mm. So 15 plus 20 mm, it will maintain the axis orientation. So it will be within the tolerance zone. So at whenever we are manufacturing, the axis of this hole, axis of threaded hole will maintain the positional tolerance till height of 20 mm. So it is not within the part, it is outside the part. So this 20 mm of tolerance zone is outside the part. So this 15 mm of tolerance zone is within the part of 0.3 mm diameter. This is the geometric tolerance value, and 20 mm outside the part, because we need to assemble the bolt, and so the axis of the this threaded hole will be in a within the tolerance zone. So this is how we have to give the projected tolerance zone. When we give the projected tolerance zone modifier like this, what is that? We are maintaining some tolerance zone within the some height. So now the tolerance zone is not inside the part, it is outside the part. I have already told you for height of 20 mm. So this dia nothing but 0.3 mm now. So in this case also axis is not straight. In this axis, this is the axis which can be vary at 0.3 mm dia, within the 0.3 mm dia. But compared to the previous case, it is improved a lot. It is towards the true center hole. So from the previous case where we are only maintaining the two hole positions, we are in this case we are maintaining the at some height. So in this projected, with the help of projected tolerance zone, we are maintaining the assembly of the bolt within the two parts. So when we have two, whenever we have a part having projected tolerance zone, to given a part, axis is improved. So in this case, axis is improved a lot. So in this situation, when you try to assemble the bolt, you will be able to assemble it properly. So now we will understand in the further session. You can see when this is in the tolerance zone, so that the fastener, this bolt is assembled properly with the two parts, because we have maintained the project for this hole. We have maintained the projected tolerance zone for the height of 20 mm. So outside the part. So that's how we can maintain the assembly of the bolt with the two parts. So this is all about the first method, that how we provide the projected tolerance zone and how we ensure the assembly of the bolt with the two parts. So this is all about the first method. In the second method, we will understand that how we can increase, how much we can increase the diameter of the free hole, and with the help of fixed Flatner formula. So with the help of formula, we will try to understand that. So this is all about projected tolerance zone. Thank you. Thanks a lot. Hello everyone. So this is the continuation session of the projected tolerance zone. In this session we are going to understand the second method, that how we can calculate the free hole diameter to get to ensure the assembly of the bolt with the part 1 and the part 2, with the free hole part and with the threaded hole part. So there is one common understanding. So whenever we give the projected tolerance zone modifier, so whenever we give the projected tolerance zone modifier, then we are projecting the tolerance zone outside the part. So whenever there is a outside the part, then manufacturing of the threaded hole, for the manufacturing of the threaded hole, but manufacturing the threaded hole with more accuracy is difficult. Normally manufacturing a threaded hole with the more accuracy is very difficult, and having the tolerance zone outside the part, it is then the manufacturing of the threaded hole will be much more difficult. So instead of using projected tolerance zone modifier, which is P inside the box, P inside the circle, we are going to use one formula to calculate. So in this case, you can see that projected tolerance zone is outside the part, which is very difficult to manufacture. So to overcome this problem with the in the method 1, in this projected tolerance zone, it is very difficult to manufacture the threaded hole with more accuracy is difficult. And to overcome this problem of the method 1, then we are going to use the method 2. In that method, what we are going to do is we are going to increase the diameter of the free hole. So this is the part, this is a free hole, and this is the threaded hole. So in the second method, what we are going to do is we are going to increase the diameter of the free hole. So increase the diameter. So what does this mean, increasing the diameter of the hole, and how much we can increase the diameter for the hole? So for this, there is a one formula. So instead of using, here you can see that instead of using the projected tolerance zone, increasing the diameter of the free hole would have be more easier and cost effective. So it is easy also, and we are ensuring we are reducing the cost of it also. So it is cost effective also. So there is a formula for this. So you can see there is a formula which is H is equal to F. So in this case, H is the diameter of the free hole. So this is maximum material condition, MMC of the hole, of the free hole. So this is MMC of the free hole. F is the diameter of the threaded hole. So F is the diameter of the threaded hole at MMC. H is the diameter of the free hole, which is at MMC, and F is the diameter of the threaded hole at MMC. Positional T1. What is T1? T1 is the positional tolerance of threaded of free hole. So here 0.3 mm is the diameter having the positional tolerance of free hole. T2 is the positional tolerance of the threaded hole. So T2 is the positional tolerance, which is also 0.3 diameter, will is the tolerance of threaded hole. P is the thickness of the part 1, and D is the thickness of the thickness or height of the part 2. So in this formula, if we write it down, so H is equal to F. F is the 6. Or 6 is at maximum material, because M6 is the bolt we are using. So 6 is the maximum dia. MMC. T1 is 0.3. T2 is also 0.3. 1 plus 2 into P, 20 upon 15. So this is the case over here. So what we are going to get is 40. So in this case, 5 into 4, 5 into 3. So 2 into 4, 8 plus 1, 9. 2 4 is 8. Sorry. So 1 plus 8 by 3. So if we calculate this, so 3, if we calculate this as 1, so 3 will be there. 3 is 3 plus 8. So it will be 11 by 3. So 3 3 is a 9. 0. So it will be something like 3.92. So 3 5 is 15, 3 6 is 18, 3.61. So 3.6 something it will come. So with this, we are just adding like this here, over here. So 6 plus 0.3 into 0.3, sorry, plus 0.3 into 3.6. Let's say for just fast calculation, we are using 3 over here. So what we can do is, so with the formula, what we will do is, we will make H is equal to F is the diameter of the threaded hole, which is 6 in this case. T1 is the tolerance for the free hole, geometric tolerance value for the free hole. T2 is the geometric tolerance value of the threaded hole, which is 0.3 as well. Then 1 plus 2, P is equal to the 20 upon 15. T is in the case of thickness or the height of the part 2. So if we calculate this, so it will come 6 plus 0.3 plus 0.3 in this case. So 5 4 3 2 8, 8 plus 3 11. So 11 upon 3. So 6 plus 0.3 plus 0.3, and this will come 3.6. Okay, 3 3 is a 9, 2 6 3 is a 18. So almost 3.6 it will come. If we multiply with this, so 6 plus 0.3 plus 0.3 multiplied by this, it will come approx 1.1. If we add up all these things, so it will come 7.4 mm dia. So the H value which is coming over here is 7.4 mm dia. So the maximum dia of this free hole can have is 7.4 mm. So 7.4 mm will be the diameter of the free hole. So in the, that the minimum diameter of the free hole will be 7.4 mm, and plus if we say, so plus 0.1 and 0. So this can be the tolerance over here can be the tolerance. And so without giving the projected tolerance zone itself, we can ensure that the fastener will definitely get assembled with this, both the part. So the part is assembled, the fastener properly. So we can ensure this. If the part is manufactured, if the free hole is manufactured at 7.4 mm of diameter as a free hole diameter. So this is how we calculate with the help of formula. So this proper hole we can calculate. So this is all about the second method, and this is the cost effective method also for the calculation. If we increase the diameter of the free hole to get the fastener easily assembled. So this is all about the second method. So thank you. Thanks a lot. Hello and welcome everyone. This is Manish from Skillable India. In today's session, we are going to learn about the concentricity tolerance under the location control. So this is the second tolerance under the location control. So in this, this is the very important. This is the geometric control, which is we are understanding this with the standard of ASME by 14.5 2009 standard. So concentricity is in ASME by 14.5 2009 standard, because in 2018 standard concentricity has been removed. We are just trying to understand about concentricity, that how we apply it. So in this particular session we will discuss about concentricity, the second geometric tolerance under the location control. So here we have an example, you can see. So this is the symbol of concentricity. So this symbol we are going to use into the feature control frame. So whenever we are using two concentric circles within the first compartment of the feature control frame, that means we are using the concentricity. It is related to a datum, so it is a related feature. So whenever we are applying concentricity, we require datum features, so datum symbols. So in this example, we will, with the help of example this, we will understand in-depth concept of concentricity. Concentricity with the definition called coaxiality in the ISO standard. So we are understanding, we are learning the ASME standard. ASME standard, it is known as concentricity, but in I will say in ISO standards, it is called as coaxiality. So coaxiality basically means when the two features have the same axis, which is in line. So the axis of one part and the axis of the other part are in line, so it is called coaxiality. And concentricity is a tolerance that controls the central derived median points. So in this, the median points are there. With the help of example, I will let you know that how these median point plays a role, and why we face a lot of problem in the time of inspection the concentricity with the help of these median points. So we face a lot of problem with these median points of a reference feature to a datum axis. So whenever we are providing a datum axis with some reference, so it is a related feature. So for in this control, these two are feature. This feature 1 and feature 2. This is a related feature. So we have provided datum to this feature A. So datum A, you can see in this here over, we have provided datum A. So concentricity is a very complex feature. I have already told you that concentricity is a complex feature because it relies on a measurement from derived median points as opposed to a surface or feature axis. So this is very important because in this we are not aligning, we are finding we are relating with the median points, derived median points. So in this you can see that we have two cylindrical feature of size. There are two cylindrical feature of size. One is this and second is this. So whenever we want the axis of the first, let's say this we are controlling seeing first feature and second feature in this case. So whenever we want the axis of the first cylindrical feature, in this is the first cylindrical feature, to be in line with the second cylindrical feature. So the axis of this feature should be in line with this feature. So this is a condition. But in actual manufacturing, when we manufacture the part, so we want some tolerances, because manufacturing exactly according to the drawing is impossible, or taking a lot of cost is involved in that. So cylindrical feature to be in line with the datum axis. So in this case, this is the datum. This feature we are using as a datum, because you can see over here, I have write it down over here, datum. So this surface we are using as a datum. So this axis is a datum axis. This axis we called as datum axis. Now, in all such situations, we can give concentricity in the feature control frame. So we can use the concentricity. So here concentricity through give a dia symbol. You can see if we are providing dia symbol in the feature control frame, so it is a feature. It is regardless of feature of size symbol, because which means that it can only be applied to a feature. So this is very important note. So this note you can write it down, that concentricity can only be applied to a feature. We cannot apply concentricity to a feature of size. So we cannot apply concentricity to a feature of size. If we cannot apply concentricity to a feature of size, that means we cannot use the material condition modifier. So in concentricity, we cannot use maximum material condition and the least material condition modifiers in the feature control frame in the tolerance compartment. So this is very important. It is not applied to a feature of size. So we will not be able to apply the MMC or LMC. So this is one of the drawback of the coordinate tolerancing system. So you can see this is one of the drawback of concentricity, that we cannot apply the MMC or the LMC. So whenever we give concentricity like this, so like this we use in the feature control frame, whenever we are giving concentricity into the drawing, then the actual meaning is from datum axis A. So this datum axis, we are using this axis as the datum axis A. There is a cylindrical tolerance zone. So of 0.1 mm. So you can see that from till here, there is a cylindrical tolerance zone, which is having dia of, I will say here, which is having a dia of 0.2 mm plus minus 0. So this is there is a tolerance zone over here. So whenever we take 2 points measurement, whenever we are measuring 2 points from here and here, whenever we are measuring with the 2-point measurement, we will get the center point, which is from here to here. Whenever we are measuring, which is we will get the center point, which is nothing but the median points. So whenever we are measuring with this at different point measurement, let's say here or here, we get different median points. So there are different median points over here. So it is a cylindrical feature, and whenever we are taking measurement at from 2 points, like here and here we are measuring, here and here we are measuring, and different points if we are measuring, so the median points at the center axis will come different at different points, because this is in the same I will say point. If we are in the same plane, we are measuring from different points. So at center also we are getting different median points. So this is the drawback of using the concentricity, that median point must lie within the cylindrical tolerance zone. So these median points should lie between the tolerance zone, cylindrical tolerance zone. So if this condition is satisfied, we can use the concentricity. So the part is concentric with the datum A. If the median points are lying within the tolerance zone, so it means that it is concentric with the datum axis A. So in this condition, this is the first condition. So the first disadvantage of using concentricity over here is to apply it can be applied to a feature only. First drawback is that we cannot apply the concentricity to a feature of size. It can be only be applied to a feature, so we are not able to get benefit of maximum material condition or the least material condition modifier. The second disadvantage of using in the checking methodology, the second disadvantage of concentricity is in the checking methodology. So what the checking methodology or inspection, when I take 2-point measurement, so I have already told you, whenever we are taking 2-point measurement at the same plane, I may get different median points in this position. I may get median points in this position. If I take at this point measurement on different plane of same axis, if I am taking on different plane, I may get different median point. So at different planes, let's say here different plane, here different plane, here different plane. So different planes, we are getting different median points over the length of the feature. So that's why connecting a single axis which should be in line with the datum axis, which is the datum axis. The part 1 is having the datum axis, so it should be within the in line with the datum axis. So this is the second disadvantage of the median points may not be in the same direction. If it can be somewhere else in the on the axis, so like that, though the surface, the median points may vary. So if the surface median points will be varying, so you can say because of this difficulty we are facing at the time of inspection or checking. So of checking, most of the time we don't prefer concentricity. So in using in the feature in the engineering drawing, we do not prefer using concentricity. So as I have mentioned this previously also, that updates of the by 14.5 2018 standard, the concentricity geometric symbol has been deleted or has been removed. So whenever we required for this, so whatever we are discussing till now is in the accordance with ASME Y14.5 2009 standard. So this discussion is as per the 2009 standard. In 2018 standard, it has been already removed. Okay, and it in this 2018 standard, in the 2018 standard, it is been replaced. The concentricity is replaced with the position tolerance. So in such situation, whenever we require such a situation, we can use the position modifier over here. What is the benefit of using the position symbol here? So this is itself will control the concentricity also cylinder with reference to the datum. So in this condition, position will control the concentricity of this with the in line with the datum axis. The benefit of using position here over here is, the advantage over here over using concentricity is, we can apply it to a feature of size. So position tolerance symbol can be position geometric symbol we can apply to a feature of size. So whenever we can apply to a feature of size, it here over axis, so we can use the maximum material condition and least material condition modifier. So we can get the bonus tolerance over here. So that's why in this drawing we can use the position symbol, so that we can use the maximum material condition and least material condition modifier as per the 2018 standard. So I have already told you that the position tolerance is one of the most important tolerance in the out of all 14 geometric tolerances. So this is all about the concentricity, using concentricity over position. Using position instead of using the concentricity tolerance. So this is all about the concentricity. In the next session, we will be discussing about the symmetry. So thank you all. Hello and welcome everyone. This is Manish from Skillable India. In today's session, we are going to cover the topic which is symmetric tolerance, and this is in terms of standard. So we are in terms of standard, we are going to learn this as per the ASME Y14.5 2009 standard. I have already told you in the previous session also in the concentricity that two tolerances are being deleted as per the ASME Y14.5 2018 standard. So the two tolerances are concentricity and symmetry. So why they are removed and what are the problems we have faced while using into the engineering drawings the symmetric tolerance symbol. So in this discussion, we are in accordance with ASME Y14.5 2009 standard. I am trying to cover you that how we use this the geometric symbol. So this is the geometric symbol of symmetry, that whenever we are using this symbol, it means this is a symmetric symbol. This is also a related feature related to datum. Yes, it is related to datum. So whenever we are using symmetry tolerance symbol, we are with in line with the some datum. So in this example, with the help of example, we will understand this symmetry. So with the definition, GD&T symmetry is a three-dimensional tolerance that is used to ensure that two part features on a part are uniform across the datum planes. In the concentricity, we are talking about the axis, but in this, we are talking about the planes. We are talking about plane. If we are talking about plane for the this to this, if we are talking about from here to here, there is a different plane. And for this part, if we are measuring from here, it is having one plane. Let's say this is having one plane and this point to this point is having one plane. Just to understand a clear concept. So why it is important that if we are taking 2 point measurement, so we want this plane to be in line with one another. Then only it is called symmetry. So then only it is called symmetric. So an established true central plane. So this plane should be a central plane is established from the datum. So if we in with the help of example, I will let you know that how we from the datum and for the symmetry to be in tolerance. The median distance between every point of the two surfaces features need to be fall near the central plane. Each set of point on a reference feature would have a midpoint. So whenever we are providing tolerance, so there is a tolerance plane, tolerance zone. So there is some tolerance zone, some height, maybe it can be 0.1 mm apart. So whenever we are checking with the different points, so we are getting some median point within this tolerance zone. So some median points we are getting within the tolerance zone, and which is in right with between the two. If you take all the midpoints of the entire surface, this must lie within the tolerance zone to be in specification. Symmetry is not a very common geometric tolerance dimensioning and tolerance call out. Since it has very limited functional uses, centering location is done with the position. So I have already told you that symmetry is not one of the tolerance which we used regularly in the engineering drawings. Because if we want inline with the center, if we are talking about the center plane and we want an inline, we are definitely going to use the position tolerance to make the plane in line with the other datum plane. So this we will understand with the help of example. So in this example, we will understand this that whenever we have a part like this, you have center plane. So this is a center plane. Here I have shown you one center plane throughout the part. But if I am considering this in one feature, this part, feature 1, and this part as feature 2. So both the part is having planes, different planes. In if they are into the drawing, into the CAD drawing, which is exact drawing. So in this you can see there is only one center plane. But whenever we are manufacturing this part, whenever we are going and manufacture this part, I have used one term over here. You can see this. I have used datum. So for this, I have already used datum A. So for this part, this measurement, I have given this center plane. This is a center plane, and this center plane we have used as datum A. So the primary datum this plane we are using as a datum plane. So this plane is called datum plane. And here we have given the feature geometric tolerance, which is 0.1 mm apart. So whenever we are talking about this, so it is showing that there are two planes which is 0.1 mm apart, which are 0.1 mm apart according to this geometric tolerance value. Now, in this also, in symmetry also, we can only apply symmetry to a feature. Symmetry can only be applied to a feature. We cannot apply symmetry to a feature of size. So in this case, if we cannot apply symmetry to a feature of size, then that means that we cannot use the material condition modifiers, which are maximum material condition and the least material condition. So if you want to maintain the symmetry between the two feature of size over here, two center planes, that means the center plane of the first and center plane of the second must be on one plane. In all such cases, we can use symmetry. So if you give like that, means from the datum plane A, like this is the datum plane. So this is the datum plane A. You have two parallel planes. These two parallel planes of which are 0.1 mm apart. And whenever we take 2-point measurement, let's say we are measuring this part from here to here or from here to here. Whenever we are taking 2-point measurement of slots, you get derived median points. So different median points we are getting over here. At different points, we are getting different median points. So that median points must lie within the two parallel planes, which is 0.1 mm apart. So as I have already mentioned that in concentricity, getting derived median point of different location. So getting these derived median points of different locations is very difficult, and we may end up with so many different median points. So that's why, again, though we apply symmetry to for a feature of size, it is a feature control. Although we are applying to a feature of size, but this symmetry is a feature control only. So it is a feature control. So we will not be able to apply the maximum material condition and the least material condition modifiers. So same reason as concentricity, that because this can be applied to a feature only. So for us, checking method is also difficult because there are different median points at different locations. So this geometric tolerance symmetry is also deleted from as per ASME Y14.5 2018 standard. So this symmetry has been removed. Symmetric tolerance symbol has been removed from the ASME Y14.5 standards. So again, it is being replaced. This symmetric symbol is being replaced with the position symbol. So I have already told you that in position we can apply to a feature of size. Whenever we can apply to a feature of size, that means we can use the bonus tolerances. That means we can use material condition modifiers, which is maximum material condition and the least material condition modifier over here. In this condition, you can see that as per datum A, so this plane is datum A, datum plane A, which is in this case we are using the position. So means we are getting the more tolerance zone because this we have applied to a feature of size. So in this case we are using the plane as a feature of size. So we can control the position of the center plane in this case, which is 0.1 mm apart. And the checking methodology is also easier in the position as compared to the symmetry. So this is one of the very common reason that we use position in accordance with the ASME by 14.5 2018 standard. So the concentricity and the symmetry has already been removed. So this is all about the as per the today's session. Thank you. Thanks a lot. Hello and welcome everyone. This is Manish from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to discuss most important topic in GD&T, which is circular tolerance, circular runout and total runout. So in this session, we will discuss about runout, both circular and the total runout. First, we will start with the circular runout. So what is circular runout? Circular runout, basically it is also called the radial runout. So here is a example of a drawing. I have taken one example over here. So before going into the example, first of all, whenever we give a circular runout, it should have a datum. So it is related to the datum. So whenever we are using the circular runout, this is the symbol of circular runout. So whenever we are using this symbol inside the box in the first compartment of the feature control frame, that means it is a circular runout. In this, the maximum material condition and the least material condition are not applicable. So runout is how much one given reference feature or feature varies with respect to another datum. When the part is rotated 360 degree around the datum axis, it is essential to control of a circular feature and how much variation it has with the rotational axis. Runout can be called out on any feature that is rotated about an axis. What does this mean? We will understand in a detailed manner. So whenever we give circular runout, it should have a datum. So first of all, whenever we are giving circular runout, it should always has a datum. So datum is a must because it is a related feature. Whenever there is a related feature, we have to take datums. So always the datum should be a regardless of feature of size. Why it is regardless of feature of size? Datums only. We cannot apply the maximum material condition or the least material condition, or we cannot apply the maximum material boundary or the least material boundary and to the datums. So here we cannot apply the least material boundary or the maximum material boundary over here. So second thing is, this is a circular runout. It is a two-dimensional entity. So circular runout, I will write it down over here. Circular runout is a two-dimensional 2D entity. Two-dimensional entity. Why we are considering that two-dimensional entity? Because whenever we are checking the part, so we are checking at only one plane. So at let's say this is a circular plane. So we are checking at only one plane. So this is the one plane. If we are taking it from the perpendicular, let's say this is the perpendicular plane. So only at from the dial indicator, putting dial indicator, rotating this part and checking only at this circular profile, not over the length. So for the circular runout, we are only checking for one plane. So which it means it is also applies to a plane, single plane which is perpendicular to the datum axis. So this plane is always perpendicular to the datum axis. Okay, so in this case, you can see that this is perpendicular. This plane is perpendicular to the datum axis. In this datum is considered, because I have taken primary datum over here. So we have taken this primary datum as the datum axis. So this is taken as a datum axis. And this plane, this circular profile over the part, this circular profile at one plane is always perpendicular to the datum axis. So if you want to check the radial runout or circular runout, it is independent. You have to take it n number of times. So if we want to check multiple times, so let's say first we will check at this plane, one reading is coming, then we will check at this plane, one reading will calculate, then we will check at this plane, and multiple times we have to check over the length. So multiple times we have to check the circular runout because it is two-dimensional entity. So towards the length of the cylinder, for checking this circular runout, what is the most important thing? That when you have the drawing like this, whenever you have a drawing like this, I will erase all the things like this. The meaning is, when I told the cylinder, this small large cylinder, I get the datum axis. So when we hold, let's say there is a V block, let's say there is one V block, and we have kept this part onto the V block, this large part. So this large part is kept onto the V block. And when we rotate this part, so when we rotate this part, the axis is used as the datum axis. So the datum, this is when we hold this part from the air and rotate this part from the datum axis. So I get the datum axis at this condition. When I put the dial indicator on the second cylinder like this, when we put the dial indicator on the second cylinder and then rotate the component, the full indicator. So this is a dial indicator. Let's say this having a there is one dial indicator. If this indicator, this pin is rotating, this pin is rotating 360 degree, or the movement value should be equal to the 0 point less than 0.1 if it is rotating. So which is given in the feature control frame. It is 0.1 mm in this case. So if it is rotating full, then we are considering. If it is not rotating 360 degree, means it is less than the 0.1 mm. So it is acceptable because the tolerance which we have given is over here is 0.1 mm in the feature control frame. So now, as I said, this is a two-dimensional entity. The tolerance zone for the radial runout is two coaxial circles which are perpendicular to the datum axis. So there are two coaxial circles which are perpendicular to the datum axis. Apart from this, we call radial runout as composite tolerance. Why we call this as composite tolerance? The question arises that why we called it as a composite tolerance. Because in this you can see, because it controls form, it is also controlling orientation. And as well as it is also controlling the location. So that's why it is called as composite tolerance. So here what we are getting is circularity. So while rotating, we are checking the circularity of the cylinder with reference to the datum axis. At the same time, location of the center of the circle and perpendicular plane coincident with the datum axis, which is nothing but the location. When we convert this into a total runout, let's say, first of all, before going into the total runout, I will show you the measurement. So circular runout measurement. Runout is measured using a simple height gauge. So let's say this dial indicator is fixed on the some height gauge on the reference surface. The datum axis is controlled by fixing all datums points and rotating the central datum axis. So this part, let's say we have placed this part onto the V block. So this part is fixed and the datum axis is logged. So what has happened? That the circularity of the cylinder with reference to the datum axis, at the same time location of the center of the circle at this perpendicular plane. So coincident with the datum axis, which is nothing but the location. So here you can see that this is the dial indicator, and if this dial indicator is rotating 360 degree, it means it is considering 0.1 mm. And if we have given 0.1 mm as the in the feature control frame, let's say 0.1 mm with datum A. So means it should not rotate 360 degree. If it is rotating, then we are out of circular runout. So the part is usually constrained with V block. So here V block, we constrained this part, or we kept this part onto the V block or a spindle on each datum that is required to be controlled. The part is then rotated around the axis. So now this part is being rotated around its axis. So this is the axis. So at this axis, this part is being rotated, and when it rotates 360 degree, this dial indicator dial should not move 360 degree circle. It always bubbling between 360 degree only. So the variation is measured using the height gauge held perpendicular to the part surface. As long as the gauge does not vary by more than the runout tolerance, the part is in the specs. Let's say if I am talking about, if I have given that here 0.2 mm, means this dial indicator should rotate 2 times. If it will rotate more than 2 times, then only it will call out of the circular runout. That the runout is out for this single profile. You can see it is the perpendicular plane. So this is just a perpendicular plane, and this is why this is it. This is because it is called 2D entity. So now I think you should know that how we check that the circular runout of the part. Now we will move on to the next part, which is total runout. What is different between circular runout and total runout? I will tell you. So first of all, symbol, this is the symbol of the total runout. We use like this in the feature control frame. Total runout is how much one entire feature or surface varies with respect to the datum when the part is rotated 360 degree around the total axis. So in this, we are not checking only at one point. We are moving the dial indicator throughout the length of the part. So in total runout, we are not checking at only one point. We are checking the whole length, total length. And we are moving this dial indicator at over the length, and we are checking that it is the whole length is under the 0.1 mm of tolerance. If the dial move more than 360 degree over the length, over the whole total length, that means that it is out of the tolerance. So total runout controls both the amount of the variation in the surface. So it is just controlling the amount of variation in the surface. Let's say if surface is like this. So it is also controlling the variation. So this is the variation. This variation always be within the tolerance. In the axial dimension, both radial variation and axial variation. So both the things in this radial variation, because the total length we are measuring, and the axis variation, axial variation where the axis is should be checked. So in this, we are not only checking the axis of this part, but also the radial direction, and held within the tolerance. So total runout is usually called on a part that is rotated about an axis where the entire surface is critical. So let's say if this whole surface is critical and we need to check this surface that it is within the tolerance zone or not. So we will check with the help of total runout. With the help of example, we will understand this. So total runout is measured by fixing the datum feature, typically an axis, and rotating the part along the rotational axis. So here also, first of all, what we will do, we will put this part onto a V block. This is a V block. So we will log the axis of this part and then rotate this part along the datum axis. So here it is datum A fixed at plus rotated. Now this dial indicator is moving here and in this direction over the length. So what is doing? The part is usually constrained with a set of V blocks or a spindle of some sort of that will constrain the part while allowing it to rotate. To measure total runout, a series of gauges must be linked to that to take care measurement in reference to each other, similar to how cylindricity is measured. So another method of measuring total runout is to take one gauge held perpendicular to the surface of the part and slowly move it across the surface of the part axially as the part is rotated. So while rotating this part, the dial indicator is moving. So in this, while dial indicator is moving, it is checking the radial variation as well as as well as axial variation. Axial variation. So this is why it is very important that we are checking both the things in this particular uh, total runout. So this is all about total runout and the circular runout. Thank you. Thanks a lot. Hello and welcome everyone. In today's session of geometric dimensioning and tolerancing, we are going to discuss one of the most important tolerances, which is profile of a line. And the second one, which we are discussing about, is a profile of a surface. So in this particular session, we are going to discuss about the two most important tolerances because they are considered to be the more versatile and powerful in terms of geometric tolerancing system. So in profile tolerance, I have already told you, we have two types of tolerances, profile of a line, and one is, the first one is called profile of a line, and the second one is called profile of a surface. So this is the symbol of a profile of a line. So whenever we are using in the first compartment of the feature control frame, the symbol like this, that means we are using profile of a line tolerance. Now, when a profile of a line tolerance is specified, the tolerance zone is a space within uniform two-dimensional boundary. So, profile of a line, we have two-dimensional tolerance. Two-dimensional tolerance, or we have two-dimensional boundary. So, with the help of example, we will discuss this thing. So if I will go with the definition, so it is related to the datums. Yes, it is related to the datum. So we require datums in the feature control frame. In this, there is no MMC and LMC are applicable. So LMC or MMC modifier, material condition modifier, we don't use in this profile tolerance. So, profile of a line describes a tolerance zone around any line in any feature. So, profile of a line describes a tolerance zone. So, whenever the line like this, you can see this line. So, there is a line like this on any surface. It can be surface like this. It can be surface like any other surface. It can surface like this also. The part can any type. Just what we are showing is that the tolerance zone around any line in any feature. So it is a two-dimensional tolerance. So that's why we are talking about. So profile of a line is a two-dimensional tolerance zone. Two-dimensional tolerance range that can be applied to any linear tolerance. So in this, we can apply to any linear tolerance. If it is called out on a surface, let's say in this case, this is a surface. So this surface we called out profile of a line. You can see this symbol over here, profile of a line. So we called out this profile of a line at one plane. So if we cut this part at one plane, the line which comes out, if we do a section view from the center, this line we will get the curved line, and that is the profile of a line. It should be within the tolerance zone, whichever tolerance we have provided. Here we have given 0.1 mm. So if it is called out on a surface, like radius on a part, profile of a line would specify how much that cross section could vary from a true curved radius. So profile of a line takes a cross section at any point along the surface and sets a tolerance zone on either side of the profile. So in this, what we are finding out,
we are just checking that what is the right, this is the right surface, and this is the tolerance zone what we have, which is 0.1 mm. So this is very important that we should specify in a correct way. Now we will understand when as you see in this diagram. So in this diagram you can see particularly this phantom line. This is the point. So at any given cross section, what we are going to get in a plane, at this plane, let's say this is a single plane, and sorry, this is a straight line. Actually, you can think like this is a straight line, and we are cutting this part from this in a cross section, and we are checking at this plane, and this cross section we are checking that either it is properly curved or not. So we are going to have a profile of a line, that is profile of a line within the 2D boundary. So in 1997 standard of GD&T, ASME GD&T, what we give is we provide this phantom line. Okay, this phantom line we provide, unlike the other geometrical tolerances, when it comes to a profile of a line or profile of a surface, we have to specify which surface from where to where it is considered as a profile. So in this you can say that this symbol we are using C to D. What it is defining, so in this example we have 2 points C to D. So in drawing also we have specified that this is C and this is D. So if I will change the color, so you can see this, that here C point is given, here D point is given. So in this feature control frame in the bottom we have specified that from C to D. So this profile has a tolerance of 0.16, which is from the distance of from C to D, between D. So this is the between symbol. I will tell you in detail about between, that why we use this between. So profile of a line within the 0.16 with reference to the datum A and datum B. So here datum A and B is already given between point C to D. So here in between symbol, between modifier. So there is a between modifier. Between modifier which we used uh, in the feature below the feature control frames. This is the major difference compared to the other geometrical tolerances, because in other geometrical tolerances we don't have to define the distance in between the points. We don't have to define the points that from C to D we have this tolerance zone. But in profile tolerance, whenever we are talking about the profile of a line or profile of a surface, we need to define these things. In the second major difference in this is here 0.6 mm geometrical tolerance is already given, that can be defined in which the direction this allowed. So this is also very important, that this 0.16 in which direction it is allowed. So this 0.16, that direction is also very important. For example, here you can see in this example, here is a line which is put here. This tells us that profile of a line. This tells us that the profile of a line must be within the inside the actual part. In this side, this phantom line, you can see this phantom line is showing. This phantom line is showing the deviation which is allowed, and this is the actual part line. This is the actual line, and this is the phantom line which is showing the deviation. Deviation which is allowed is 0.16, the tolerance which we have given into the feature control frame. So now we will see some example of a in this. So if we move, how to measure the profile of a line of or a measurement. So basically profile of a line and the measurement is done with the help of CMM. Profile of a line is measured using a gauge that is reference to the true profile at the given specific cross section. So whatever 3D model we have created, with the help of that 3D created model, we can specify that this is the profile, and this we need to check, because there are an infinite amount of 2D cross sections
of any part, the number of locations of measurement points can be specified on the drawings. So we can specify onto the drawing that this position I want to check, this position I want to check, this position I want to check, this. So multiple positions we can check that these are the positions which we have to check for the profile of a line. Profile is usually measured using a CMM for more complex geometries. So whenever there are complex geometries, we use CMM. What is CMM? I have already told you this thing, that coordinate measuring machine. Coordinate measuring machine. With the help of coordinate measuring machine, we find out the exact coordinates of the profile. So with the help of probe, we check these points and collect point cloud data. In this, with the help of probe, we collect point cloud data. And this data we match up with the 3D CAD model. If that matchups, the profile matchups, that means it is within the tolerance zone. Or if it is varying within the tolerance zone, so in this we can check particularly. So this is the main way of measuring the profile of a line. Now we are moving towards the profile of a surface. So in this is the symbol. This is the symbol we are using in the feature control frame, in the first compartment of the feature control frame, that this is the symbol of profile of a surface. It is related to the datum. It is an optional. Yes, it is related to the datum. Whenever we are using primary datum and the secondary datum in this, so it means that it is related. We cannot use maximum material condition or the least material condition in this case, or for datum, we cannot use maximum material boundary or the least material boundary. Now, profile of a surface describes a three-dimensional tolerance zone. You can see that profile of a line is a two-dimensional, but profile of a surface, in this, the whole surface, you can see this whole surface over the part we are taking into a consideration. So in this profile of a surface, it is a three-dimensional tolerance zone around the surface, usually which is an advanced curve or shape. If it is called out on curved surfaces like a fillet or a welded part, the entire surface where the radius is has to fall within the tolerance zone. Profile control all the points along the surfaces within the tolerance zone range that directly mimics the designed profile. Any point on the surface would not be able to vary inside or outside by more than the surface profile tolerance. So usually when surface profile is required, whenever surface profile is required, let's say we have surface profile, it is required over here, and we have mentioned over here 0.1 mm apart, mean it is a bilateral tolerance, which is 0.05 above inside the part and 0.05 mm outside the part. This is also very important thing. This we will discuss in a very detailed manner, that how we showcase into the feature control frame. So usually when the surface profile is required, there are no tolerance on the dimensions that describes the surface, that use the GD&T callout to give the acceptable range. So basically what does this means? That we provide the basic dimensions. So we provide in this case the basic dimensions. Now, in this you can see when it comes to a profile of a surface, also we have different ways of specifying. So in this case, you can see that we can specify. So here in the previous case, if you see, this was the older, in that case, it was the older practice in the 1994 standards. We were specifying the deviation with the phantom line. In this case, this phantom line, as we showing this phantom line, this is as per the ASME Y14.5 1994 standard. So now it had been removed in 2009 standard. As per ASME 2009 standard, this phantom line concept has been removed. How it is removed? So you can see in this that it was a very difficult to show this on a 3D model. So that phantom line showing is very difficult. So how it is removed? In 2009 we come out with the new modifier, which is called the unequally disposed or unilaterally disposed modifier. Unilaterally disposed modifier. I will write it down over here. Unilaterally, it is already written over here, but unilaterally disposed modifier. So what does this mean? And how we get help and how we have removed that phantom line. So what does this unilaterally disposed modifier means? This is the U symbol inside the feature control frame. So whenever we are using like this is the feature control frame. In this feature control frame, first we have defined the profile of a surface. Then we have defined the tolerance 0.3. Now we will show the symbol U and round circle. U under the circle is showing unilaterally disposed modifier. And if we are showing 0.3 mm again, means it is outside the part. Then we write it down the datums A with respect to datum A, with respect to datum B, with respect to datum C. So first of all, we will see profile of a surface with unilaterally outside. So whenever we written 0.3 mm after U, the same tolerance if we are writing over here after U means that the profile unilaterally out, it is outside. So in this case, if I will make one diagram over here. So what does this means? That what we have tolerance, let's say the tolerance which we have is outside the part. If it is written 0.3 mm over here. Now we have two types of unilaterally disposed modifier. One is unilaterally outside and one is unilaterally inside. Unilaterally inside modifier. So in depth we will see. So in this you can see that whenever we are giving unilaterally outside modifier, let's say this is a part. This is a part. In this part we have given unilaterally outside. So tolerance zone, it is written over in this, you can see this is the feature control frame. It is written 0.5 mm U, 0.5 mm A datum. So in this case, it is saying that this tolerance is outside 0.5 mm because 0.5 is written after it. So this is outside case. Similarly, for the internal feature, this is for the external feature. For internal feature also, in this case, same, it is written. So this is for the surface. This is for the surface. And this is for the hole. So in this also, it is written like this, that 0.5 U, sorry, 0.5 and datum A. What does this mean? It is also saying that it is outside the part. In this case, for external feature, the size is increasing. In this case, material is increasing. Material is increasing. In the whole, in the case of whole, it is, in this case also material is increasing and it is small becomes, the whole becomes smaller. So in this case, whole material is increasing, whole material is increasing and it is become, whole is become smaller. Whole is become smaller. So this is how we give the unilaterally outside for a profile of a surface. Now for the inner, for the, I will say, if we see unilaterally inside. So if we are providing, let's say if we are providing that in this case for the whole, you can see that 0.5 U0. If we are using 0 means that it is outside. Oh, sorry, inside the material. So in this case, you can see that this is for the unilaterally inside example. Profile of a line unilaterally inside. So whenever we specify the profile of a surface 0.3, the total value will be 0.5. in this case will be inside the part. So in this it is inside the part. So we are using 0.5 mm inside the part. So this is very, very important. So here we have an example of an external surface and the internal surface applied unilaterally outside and unilaterally inside. Similarly, for the hole we have understand. For the if we make 0 over here. So what does this means? That it is inside the part. The tolerance zone will be inside the part. So this is how we say we write it down into the second compartment, the unilaterally inside and unilaterally outside. Whenever we are making 0 over here means it is inside the part. If we are with the help of examples, I will let you know that profile of a surface how we define it with the examples. So profile of a line, profile of a surface. Oh, sorry. In this case, there is a surface. How we measure the profile of a surface? So profile is usually measured using a CMM due to the complexity of some of the surfaces that are called out. The CMM would compare the 3D scan of the profile to the dimensions called out on the drawing to see if it was in specs. If a simple surface is called out, such as a radius or on a corner, a height gauge can be used to trace the part as long as the gauge can stay the same distance away from the surface as rotate around the surface. So multiple times point cloud data, multiple times we check on the surface, and this data we rotate this part along that. So gauge must follow the true profile. So profile is usually measured with the help of CMM. So as the it is rotated, the part is rotated and go and fro. So it is then the profile would be checked with the help of 3D CAD model. So we can compare with the help of 3D CAD model. In this case also we are calculating the point cloud data. With the help of that point cloud data, we create a profile, and that profile should be matched with the 3D scan model or 3D CAD model. So that's how we can measure the profile of a surface. Now, in this, you can see that profile of a surface in a equally in this. So here, the phantom line is inside the material. So in this, there are 4 examples. So there are 4 examples in this. One by one, we will understand. So next, we have the profile of surface, unequally disposed profile. Firstly, we will discuss about the bilateral tolerance. So what is bilateral tolerance? Whenever we have the 0.8 mm and we haven't shown any unilaterally inside or outside, so that means that it is inside also and outside also. The tolerance zone 0.4 mm is inside and 0.4 mm is outside with reference to datum A. So in this first bilateral tolerance example, if we are showing 0.8 mm in the tolerance zone in the feature control frame, that means that 0.4 mm is outside and 0.4 mm is inside with reference to datum A. In the second example, it is clearly shown this is the this practice is of as per the 1994 standard. So in that standard, this is how they show the phantom line. So this phantom line has been removed. This practice has been removed. Now we show like this. As per the 2009 standard, we use this 0.8 and U0 with reference to datum A. It means that it is inside the part. So whenever we are using 0 over here, that means it is the tolerance zone is inside. All 0.8 mm is inside the part. So this is called unilateral tolerance inside, and this is how we show into the feature control frame. So the datum with reference to the datum A. Now we will see unilaterally outside. unilateral tolerance outside. So previously it is shown with phantom line outside, but this practice is already deleted. So we don't use this phantom line. We show like this into the feature control frame that 0.8 U unilaterally exposed outside 0.8 means that all the 0.8 mm of tolerance is outside the part. So in this case, it is showing that 0.8 mm of tolerance is outside the part. Now, in this bilateral tolerance unequal distribution, this is very, very important to understand that how we show the unequal distribution. So previously we show like this with the two phantom lines, but in this the practice has been deleted. In now how we show this is how this. So first we provide profile of a surface, then total tolerance what we have is 0.8 and unilaterally disposed 0.2 mm. 0.2 mm is outside. So here we can see that this 0.2 mm is outside the part and 0.6 and rest 0.6 mm. Rest 0.6 mm is inside the part. So what if we are writing over here 0.3 mm? Let's say if in one other feature control frame we write 0.8 total tolerance, unilaterally exposed surface 0.3 mm means here it will 0.3 will help and here it will become 0.5 mm with reference to datum A. So whatever dimension written after U, it is for the outside. If it is written 0 means all 0.8 mm of tolerance is inside. If it is written 0.8 over here means all the like this means all the 0.8 mm of tolerance zone is outside the part. Outside the part. So now I hope you that you understand about the profile of a surfaces that in bilateral tolerance how we show that like this. In bilateral tolerance it is shown like this. In unilateral tolerance inside case we show 0 because it is nothing outside, all inside. So all the 0.8 mm of tolerance is inside the part. In this case for the outside the part we show all the 0.8 mm after U 0.8 mm means 0.8 mm out of 0.8 mm of tolerance is outside the part. In this unequal distribution what we say is we show what is outside over here and this outside will be minus with the total will remaining will be inside. So if we minus 0.8 mm minus 0.2 mm means 0.6 mm. So in this case, you can see that 0.6 mm tolerance is for the inside and 0.2 mm is already shown for the outside. So I think this concept has been clear about the unilaterally disposed modifier for the inside and outside and for unequal distribution. Now the most important part of that is profile of a surface. We use the symbol like all around. So in this case, all around, we use this symbol like this. So this is a symbol what we use for the all around. So this is the symbol of all around. And what this means, what this all around means that the surface of the part, in this case, the surface of the part, profile of a surface. So which means this to say that the object line perimeter. So perimeter entire object considered as a single profile. So all the object, this all object is considered to be a single profile. The profile of a surface applied to the entire surface with reference to the datum A. With reference to datum A, we are providing this. So I will change the color to understand properly. So in this, so this is the interpretation of this. So all the actual surfaces most lie within the 3D dimensional uniform boundary. So after manufacturing, it will become like this. It should be within the tolerance zone of 0.6 mm.
all around. So all the part surface should be within the tolerance zone. This should be within the tolerance zone. So all around the part should be within the tolerance zone. In 2009, one new modifier was added. In 2009 standard, one new modifier is added, which is all over. So what does this means about all over? In the previous example, you can see that we have used datum. So this is with reference to the datum. But in all over you will see that we are not using any datum over here. Why we are not using, I will let you know. So this is the symbol of all over. So whenever we are using the symbol like this, two circles, that means all over. This is the symbol of all over. So this means that all the surfaces of the part is considered for the profile tolerance. All the surfaces of the part is considered to be a profile tolerance. One question is, whenever we have all over, will not have any datum, because all the surfaces are bound to within the profile tolerance. So when all the surfaces are within the profile tolerance, we don't require datums, because datum surfaces are also be taken as the profile surfaces. So this is how the interpretation is actually done, that all the surfaces are 0.6 mm apart. In this case also 0.6 mm. So all over symbol means all over the part we have. So in this case we don't have to use the datum references. Datums we don't require. Now in this next example, we have the between symbol. In the starting of the session, I have already told you that we used the between symbol because the profile of a surface, in this case we provide in between. If we have multiple let's say tolerances, let's say from datum A, from point A to point B, we have 0.2 mm of tolerance. So in this position, this is for this position, this part profile, we have tolerance of 0.12 mm. From but in this case, from B to C, from B to C, this profile of the part having tolerance of 0.1 mm. And from C to D, from this point to this point, I have tolerance of 0.05. So this is how we divide the tolerance zone within the same part. So we use this in between symbol. Symbol if we have a critical part, and we can give different tolerance value for different position of the part using between symbol. So this is the so I have already told you this example. So after manufacturing, the tolerance zone can be within the tolerance zone. So it should be like this. So transition between tolerance zone can be abrupt. So whenever we are having like this condition, so there is there are other modifiers also overcome this problem, like form 2 modifier. In other session, I will discuss that modifier form 2. So this is all about the profile of a surface and profile of a line. So I think all the doubts, all the problems has been solved in this topic. If you have any doubt, you can write it down into the note section. We will definitely come up with the solution. Thank you. Thanks a lot.